is for classification models, so that we have not only the signal processing part up to date, but also the machine learning stage as well. We were lucky to have some experts in both in neuroscience and in machine learning in our team for a while, so just made a fusion of these things. Then we just push play, and all this pipeline is executed. We can see the in this window what's going on while the signal is processed. I won't wait while it goes up to the end to save our time. So what we have after the model training, it is validated. One moment. I'll show what the experts look like for a sample subject. We can evaluate the confusion matrix just after the first run for the mental states that we tend to recognize. And also, if we have different kinds of stimuli, as in our research, which I would mention a bit later, we can see the statistics for each of the stimuli separately. So it's also a confusion matrix, but a more detailed one. Also, we implemented some interesting kinds of expert to help researcher have a more practical look of what's going on with the subject's mind. Here we have the stimulus, the pictograms of the stimuli, which we presented to the subject, and the recognition timeline. So here we got, for example, a burning house with around six sliding window classification results that fit to the presentation of the stimuli. And we see when the recognition went right or wrong. For example, we could have the situation when a subject did not react to the stimuli at the first time, and then he got into it through the experiment. So we may have bad metrics, for example, for this patch, but we could explain it that the subject got distracted on this point of time. Also, of course, we have the topographies, if we use ICA or CSP, and we also export the features in NPY so that we could just take the feature matrix and play with it in Python or somewhere else. Unfortunately, I don't have the real amplifier here in my isolated home, so I could just, as I mentioned, that our software is capable of running in real time. I can show you the video how it goes. So we switch to the online mode here, and via labstream layer protocol connect to the amplifier. Select for example, the images that we would like to present our subject as a feedback, and run our pre-trained model in real time, just the several seconds after we actually trained it. So here we have the class label and the image. We also implemented some strange and some people said it's weird algorithms for feedback presentations. We have some deep learning methods here and use the generative models to create to reconstruct the images as the feedback this is if someone remembers the last year's work, which was about natural image reconstruction, something like this. So when we try to reconstruct the natural images based on the actual images database and the EEG signal, I won't talk much about this here. It's a lot of fellow researchers considered it as controversial work, but we actually have all the code now open in our software, and you can see that the images we decoded in this study, here's the link for that, are really not the averaged and noised source images, but actually the images produced by generative networks. This is in brief what our software portal is all about. To summarize, what novel features we have implemented in this. Not of them, unfortunately, I have time to show you in real time, but still I'll mention. A major thing is the BCI personalization tools. So you have seen the detailed confusion matrices, and we have other specific tools to compare the efficiency of presentation of different stimuli to the subject, so that we could, for example, in motor imagery paradigm, select the actual motor actions that are most relevant to the subject's experience, which produce the best results in BCI, which could be crucially important for actual feedback while rehabilitation protocol, because there is a big problem now with the selection of these motor stimulus. We have also of course, the channel selection tool, the most informative channels and feature bands, and also the assessment of feature importance. And a wide variety of machine learning tools are implemented, all the different linear, non-linear models, neural networks, and also custom models that can be easily implemented because the software is quite scalable. It's in Python, it's have model structure, it's very easy to add some custom modules. What applications do we see for the portal in the future? Unfortunately, our team now has no resources just to make it a huge commercial program, wrap it up and sell it. And we don't think that there's much, there would be much request for that, as any research team prefers to have their own guys who code some algorithms. But still, we assume that it could be useful for some applications where just a model should be, a BCI model should be set up quite rapidly, implemented in real time with no much time left on the exploration of implementation of different processing algorithms which are already implemented. And we could help the research community to process the data if there are some requests from the researchers to work together on some data processing routines. And this is just the background that we could use to make the process more efficient. And also, we think it is a great software for educational pipelines, for hackathons, just to train students to get along with signal processing and to build some simple or not so simple pipelines and see the results. And the next thing we are intending to do is to implement multimodal signal processing, so to enable our software not only for EEG analysis, but also for synchronously recorded EEG, eye tracking, some EMG signals, and so on, because the model structure of the software is just quite good, optimized for such kind of performance. So I think that's it. Thank you very much for your attention.
So thank you very much for your talk. Very interesting information. Please, questions?
May I ask 2 questions?
Yes.
Yeah.
So the first question is that you probably know that there exist many different packages with similar purposes. For example, there is a platform developed at High School of Economics, Center for Bioelectric Interfaces. And you probably know that the users have usually high threshold when there are many existing software, and to entering something new, especially when they already used something. So some laboratories use their custom software, as you mentioned, and some use already existing packages. So what is the key feature or features of your software which will be attractive to the users in such a way that they will try to use your one?
Well, the major concept in that is that we try to create the bridge from the between the software which is more neurophysiologically oriented, so to say, when there are not much mathematical algorithms or machine learning techniques for classification, but a lot of modules for visualizations, data cleaning, and so on. And the mathematical packages such as EEG Lab, when there is a lot of classification methods, but it's not convenient to actually build a working model rapidly with it. So what we can offer is both the sufficient signal processing part and the thoroughly designed machine learning part.
Thanks. And the second question is, you mentioned slow waves. Which one do you mean? Because it's they are not very often used, and also there is usually big problems with classifying them, because you need to remove slow artifacts, which is not so easy to remove, and also you have usually slow response time because you need to collect data to differentiate it from background. What kind of paradigms do you mean?
Sorry, I may have used the wrong word for that. I just wanted to say that we, as for now, we don't work with ERPs with eventuality potential. We just work with long mental states. I just sorry to confuse. No, not the slow waves, but just the lengthy states. So the sliding windows and this paradigm.
Okay. Other questions? Okay. The next. Thank you very much again. And the next next talk, Lev Yakovlev from Lomonosov Moscow State University. The title of talk is How to Enhance Sensomotory Performance in eSports.
Здравствуйте, это я. Коль, проверь, там видно меня?
Презентация видна.
Второй экран видно?
Yes, we can see your slides on the screen. Left.
Коллеги, я хотел бы обнародовать
Good morning,
проект, который посвящен
everyone. I would like to tell you about our project, which is a neural project. It's an e-boy platform for esports. So basically, we're trying to improve esports performance by e-athletes. In my talk, I will tell you about our initial experiments using the eBoy platform, and I'll be very happy to get your feedback. Motor imagery learning, motor imagery in part is a mental technique which is used by musicians, which is used during meditation and so on. Motor imagery is one of the dominating paradigms in BCI technologies. And it is it is based on a specific reaction for the synchronization of sensory motor rhythms. So different methods I use, MRI, EEG, EMG, and so on. These methods tell us that when we imagine motor movement, we activate different areas: supplementary motor area, premotor cortex, primary motor cortex M1, and parietal associative cortex. Based on this, motor imagery-based BCIs are very interesting for neural rehabilitation, which would stimulate plastic reorganizing in both hemispheres. All of these processes are also the foundation of motor training that we can find in all areas of human life. Therefore, neural retraining allows e-athletes to memorize a lot of different motions. As I said, it is very useful in neural rehabilitation as well. BCI, based on motor imagery, allows us to combine different approaches and come up with a qualitative assessment of motor imagery. So Lev Yakovlev proposed to use this idea to create a training tool for e-athletes. So we decided to look at the possibility of using this tool for e-athletes because, you know, their performance is linked to sensory motor coordination. Therefore, our goal was to study motor imagery training and its influence on sensory motor performance. As you know, e-athletes need sensory motor coordination when they work with computer mouse. Therefore, in our experiments, we had 11 healthy volunteers. So they were imagining different motor functions. And in the control group, our participants did not get any feedback. So we used EEG, 30-channel EEG. We gave our users certain tasks to measure their reaction speed and so on. And to this end, we use the eBoy platform. Regardless whether our volunteers were in the training group or in the control group, they had to do certain tasks. Say one of the buttons on the mouse would light up and they had to press it really fast, either using their index finger or middle finger. So we registered each attempt. The second task was that a person needed to do fast clicking, or as many clicks as possible during 1 minute. Fast clicking is one of the training exercises for e-athletes. After each task, we performed pre-test before the task and post-test after the task during the training. Our participants imagine different motor movements, the movements which they needed to complete the task. So in the context of the first task, our volunteers needed to click on one of the buttons of the mouse, and during the second task, they had to imagine that they are doing fast clicking using their index finger. Once the motor imagery has been completed, our participants were given the feedback, which was related to the depthness of visualization and its distribution, both spatial, and temporal. So you see the peak range, and we calculated desynchronization as a difference percentage. After that, so we mapped all of the differences to evaluate reaction time. As you can see, almost all of the motor tasks evoked standard bilateral desynchronization patterns. So therefore, in the left hemisphere responsible for the right hand, which is characteristic for regular visual imagery, and was also characteristic for the manipulations with computer mouse. There was finger tapping, mouse button finger click, fast mouse button click, and just mouse button click. The only option when we had zero desynchronization was in the control group. Having analyzed results reaction time for the choice between one or the other mouse buttons, we got a statistically significant results for the reaction time for the middle finger, which was clicking the mouse button. So you see the results that we achieved, and for half of our participants, the results were statistically significant. For the desynchronization, which we obtained during the training, was the synchronization which was also obtained during motor imagery. So the second task, we came up with a curve, and on the x-axis you see interval between clicks, and on the y-axis you have interclick interval, on the x-axis you have total amount of clicks. So you see the pre-test and post-test results. We were able to come up or define a fatigue phase. So looking at that, so we were able to calculate a certain rate of clicking, which has increased after the training was complete. Therefore, you also see the representation of clicking imagery. Therefore, we came up with several conclusions, but do keep in mind that it was a pilot project, but still we believe that kinesthetic motor imagery can improve the sensory motor performance in esports, and e.g. BCI controlled feedback is a great way to control kinesthetic motor imagery quality, and we are planning to continue our research in this field, and we're also planning to increase the sample size.
Спасибо большое. Пожалуйста, вопросы.
Thank you very much. Do we have any questions?
Комментарии.
Questions, feedback? Anyone?
Так, ну, вопросов, комментариев нет.
Well, since we have no questions, no feedback, thank you very much for a very interesting speech.
И у нас последний. So the last, but not least, talk in this session, morning session, Andrei Volobuyev from Samara State Medical University. The talk is Information Flows in the Brain and Artificial Intelligence, the Stochastic Function of the Brain.
Меня слышно?
Да, хорошо слышно.
Can you all hear me? Yes, we can hear you
Да, да,
really
да.
well.
Хорошо.
Oh, that's wonderful.
Тогда войдем.
So let me just share my screen. I don't know why it's not working.
Демонстрация экрана должна быть.
Пока нет.
It looks like you should have my slides on the screen. Nope, we don't.
Есть. Презентация. Вот она. Видно ее?
Can you see my slides?
Нет, пока не видно.
No, we cannot.
Выходит у меня.
I can see my slides.
А почему он отключил-то демонстрацию экрана? У меня написано, что организатор отключил демонстрацию экрана участия. Что это такое?
Не
Зачем
знаю.
они-
Это... А есть кто-то из организаторов конференции, как это включить?
Зачем он ее отключил-то? Так, надо включить демонстрацию экрана.
Я, судя по всему, не могу
I
это
don't know
сделать.
what's
Это должен
happening,
организатор
but I cannot
конференции
share my
включить.
screen. Let's ask the organizers of the conference to give me the rights to share the screen. So, brilliant.
Ага, все, теперь видно. Теперь видно. Спасибо большое.
Thank you very much. Thank you very much for helping us out.
Так. Значит, тема моего доклада информационные потоки в мозге.
I will talk about information flows in the brain and the AI, the stochastic function of the brain. Now, how do I make it full screen? Oh, wonderful.
Ну, полный нельзя записать. Значит, давайте начнем. Актуальность исследования головного мозга исключительно высока вследствие...
All right, of course, we need to study brain because there are lots of diseases in the brain. Among those diseases are those disorders that lead to memory loss, such as Alzheimer disease. We also need to understand how the brain works to eventually create the AI. Cyclical neuronic links, chains, and the cells of memory. Of course, we have the cyclical neuronal loop, something that's called neuronal loops. When there's an idea in your hand, it's because some cyclical neuronal loop is excited. All these loops are keepers of information. Determined and stochastic connections in the cortex. In the hippocampus, there are addresses of all those cyclical loops. Unfortunately, the method of coding in hippocampus is not found yet. These gentlemen are dealing with that. They have reached something, but so far the coding method have not been found, and the links between the loops in the hemispheres could be divided into two groups, the one based on traces, otherwise determined one, or accidental or stochastic ones. Brain uses determined links that come up as eased up pathways of conducting excitement between neurons since there was the previous experience or learning. But the stochastic connections or links are also very important. They come up as accidental contacts of different loops that are far from one another. And normally these contacts make no sense, but sometimes they can lead you to an insight or discovery. That's what we call insight or intuition in creative activities. Stochastic links in those loops ensure that there is scientific and technical progress of humanity, which means they are of particular importance. A computer works based on determined links between memory cells and the central processor, which processes information. There are no stochastic links in the computer. And when there is a stochastic link, for example, when it goes to the wrong file, as opposed to where the cursor points, is identified as an error. But for a brain, it's a normal, a very important mode of work. That's why a computer cannot be performing creative activity. And that's the main obstacle on our way to creating a full-scale artificial intelligence. That's for AI. Currently, what they mean by it is a software which is capable of learning and also capable of making good decisions based on the information received. But the Michelson-Morley experiment, a real intellect, can set up a special relativity theory. The current AI is unable to do it. There's no intuition in it. There are people who are like computers. They can multiply 5-digit numbers in their mind, but these people could never create something new. They have no creative thinking. Some principles of how the cortex functions stochastically. These are basically creative principles. The three-dimensional structure of the brain is quite complicated for the analysis, so let's look at the one-dimension system of memory cells, the so-called one-dimension brain. In this system, the memory links, the cyclical neuronal loops are connected in a linear way and are placed along the line of the x-axis. And as any cyclical loop is excited, it's done by accident from one of the adjacent loops. Let's say we have probability of 1.5 of 0.5. You can excite the loop on the left-hand side from the already excited loop, which is located in the beginning of the coordinate axis. And this is well-known Poiret problem. I'm just showing you the key points. After the t time, the loop at a distance of x from the beginning of coordinates with the probability that can be calculated using this formula in the screen, where the angle value is the argument for this transition. The information from one loop to another is sent through electric impulses or potential or action potentials. The set of the impulses can be identified with some electrical current E. This is the Ohm law, where R is the resistance between loops. If current is sent to the central loop when x equals 0 and is spread to all neighboring or adjacent loops, exciting them gradually, you can determine this current using this formula where there are two adjacent loops, and R is the resistance, and all other parameters are also shown here in this slide. As I said, we can calculate rather well one-dimension brain, nothing that we can do well with two-dimension brain because there's resistance between diagonally located loops, and that's a rather complicated formula, which is really hard to find analytically. Average difference in potentials between symmetrical electrodes of EEG, depending on distance x, can be found in the one-dimension case. You can find using this formula for one-dimension brain. It's transformed into a simplified form. Here we show the potential difference between symmetric electrodes in one-dimension brain. The excitement is spread at the speed of 20-30 meters per second in the human brain. Due to x equals vt, the image reflects the temporal character of spreading of excitement, which can be identified or with alpha rhythm of human brain. This is your alpha rhythm. This is spontaneous excitement of the cyclical loop. In principle, it cannot be in a calm state. It has to be excited from time to time, the cyclical neuronal loop. If there's no processing of information using this loop, it excites spontaneously. And at this, I thank you for your attention. If you have any questions, I will be willing to take them. This is how information is sent from sensors to neurons to hippocampus, and then entorhinal cortex, and the new cortex, entorhinal cortex, is very important. It is combined with hippocampus, and it's a filter. For example, when we sleep, this entorhinal cortex keeps the information within the new cortex. Do you have any questions? If we have no questions, then I'm done with my presentation. All right, I cannot hear whether you...
Добрый день.
All right.
Можно мне вопрос задать?
I actually have a question.
Да,
All right,
вот
right, great.
по поводу, вот вы сказали очень
You're
интересную
talking about-
информацию, что нельзя, как бы искусственный интеллект
You
не
said that
может
AI
стимулировать работу
cannot,
реального мозга, потому что у него
copy
все
the work
процессы
of a real
детерминированы.
brain because all
А
processes there are
ввести
determined.
искусственные какие-то стохастические процессы,
Could
шум,
there be
чтобы
some
приблизить
artificial
его именно к
stochastic
реальному,
processes like noise
реальной
to make it
работе.
closer to real work? But noise is not a stochastic process, but in principle you are quite right. You can introduce some noise-like processes and attempt to come up with artificial intelligence using accidental excitement of cyclical loops in certain parts of the cerebrum, which gives us new information.
Да,
I have
да, ну
answered
и
your question.
попутно, значит, в общем-то, если говорить вот о работе мозга,
If we
то,
talk
скорее
about
всего,
how
это
brain
система
works,
мультистабильная, которая
this is a
имеет
multi-stable
множество
system
решений, и
that has
в
lots
этом
of
случае шум
solutions.
просто меняет, является как бы перебрасывает систему с одного состояния в другое.
This
То есть,
system changes from one
если
state to
если
another.
искусственный интеллект тоже реализовать таким образом, чтобы решения были неоднозначны, то в этом случае, я думаю, что
And these were not
возможно, он тоже
simple
будет
solutions.
как-то
Perhaps
приближать эту систему
this
к реальному,
could
к
be
реальной, более-менее реальной. Как
getting
вы
the system
считаете?
closer to something real. You are right in a sense, because the real brain works in an accidental way, connecting information between different cyclical neuronal loops. Only in that case you can get new information in the new cortex. Can that be done using noise? That deserves additional research using mathematical modeling. I have been involved in mathematical modeling of stochastic brain function. It is a rather complicated problem. Look at the article in in nano micro system technology. There's this article about brain stochastic function. It's a relatively large article. We're looking at 1-dimension, 2-dimension brain, but it's not a topic for a brief discussion.
Спасибо. У нас
All right,
время уже,
we're out
так
of
сказать,
time.
завершается, поэтому огромное спасибо
I'd
за
like to
интересный
thank
доклад с
all of you for your
интересными
interesting
такими
presentations
продвижениями.
and with
So the
some
first part
new
of
ideas.
our program is over. Many thanks to all participants and speakers for very interesting, very exciting talks. Unfortunately, we are a little off schedule. As I understand it, the second session starts right now. I transfer session control to Dr. Denis Kulishov. So thank you very much for all for participation. Thank you very much.
Yes, hello everyone. I'm Denis Kulishov. I will be a director of this symposium, the second part on brain-computer interfaces. And we're going to learn much more about signal processing through neyrophysiology and clinical applications. In this particular session, I think there'll be a lot of examples of real clinical applications and also some really, really great thoughts about the deepest understanding on neurophysiology itself. So BCI Samara goes every year, such an amazing event. I would like to mention that all the participants should check the website and all the satellite events and the huge agenda which organizers made for this year. It's such an amazing opportunity for all of us to speak today and to share our thoughts. And I would like also thank Samara State Technical University, IT Universe Company, all the sponsors and partners of this event, because I think that right now, Samara, for me, for example, is the top conference, I think, on neuroscience in Russia, because such a great atmosphere and a brilliant autumn in Samara and a beautiful scenery of Volga River, which we all see next year, I'm sure. Okay, we need to cover a small handicap. So I would like to ask all participants to be real tight and extremely careful about the time for their talks. We have 10 minutes. We have no problem at all with translation because everyone could check at the bottom of Zoom the button for translation into English and or into Russian. So 10 minutes for talk, 5 minutes for questions and answers. And also we exceeded, organizing committee exceeded one talk. It would be Stefan Ehrlich. He'll be speaking for 20 minutes. And also at the end, we have Giovanni Mirabella video. Sadly, he won't be able to speak himself, but he recorded for us a video yesterday and we played. Okay, let's start. We have a lot of interesting talk to do. I would like to ask all the participants just one more time to mute their microphones, then you're not speaking, and to be really careful about this because otherwise participants will hear bothering noises and etc. And the first on the virtual scene would be Victoria Dimova from Technical University of Munich, from Germany. She will cover the topic of ERP components of self and agent-related errors in human-agent collaborations. This topic actually, from one side, is well discovered, but also there is so much to do in these fields. And of course, ERP components give us so much data to analyze and to improve our systems. So I would like to give a stand to Victoria. Please, Your time starting.
Okay, yeah, thank you very much. Hello to everyone. Unfortunately, we didn't have a break, but I hope you still have energy to follow all the presentations of this session. So as announced, my name is Victoria Dimova, and today I'm going to present the work that I did for my master thesis under the supervision of Stefan Ehrlich and Professor Gordon Cheng. I will first start talking about human-robot interaction, because this is a field that's rapidly growing, and it's a field where brain-computer interfaces do have their contribution. One example for contribution is human-robot co-adaptation, for which Stefan Ehrlich is going to say a bit more later in this session. And I'm going to talk about human-robot collaboration. When human and robot are working together to finish some task, there are different ways how they could finish the task. So, for example, the robot could do his job, could finish his job and then hand in the object to the human, and the human would continue working on it. Or they could, for example, as it's shown here, hold the object at the same time, and they could both work on it. And while doing this, everything that the human is doing is for himself a self-related action. And everything that the robot does is agent-related action. And now I asked the question, okay, what would happen if in this collaboration some error occurs? Like, would we be able to observe, are the observed errors with self-related actions different than the observed errors from the agent? And if so, would we be able to understand the error type? And earlier I mentioned the human-robot co-adaptation because if we are able to distinguish the errors that are self-related and agent-related, we would contribute to a more efficient adaptation from the robot. To study this, an experiment was designed where there were two different scenarios. Simulating human-robot collaboration, and for simplicity, there was no robot involved in the experiment, but it was modeled with an agent. And in the first scenario, that's called shared workspace, both the human and the robot could control only one part of the area, so only one color that we can see here, and then the other one controls the other one. And so one controls is in their own area and then observes what the other does in the other area. And the second scenario is called shared responsibility. And here they both control the object at the same time, but out of the 4 possible directions where the object could move, like up, down, left, and right, they can control only 2. And an immediate action is required. And by the way, the task actually in the, so yeah, I guess I can admit. So the task is to bring this object from its starting position to the goal by following the trajectory that's given by these dark tiles. And I mentioned that, I mean, the errors are important in this study. So there were 2 types of errors. Interface errors, which means that when the human was giving a control and this control was misinterpreted, the interface misinterpreted the command, and because of that it's called interface error. And then when the agent was in control and an error happened, it's agent error. And actually there is also a 3rd type of errors in this experiment that comes directly from the users when they send the object to some wrong direction where they shouldn't have, but because the experiment was not designed to make the subjects do mistakes, they are not studied, they are not analyzed further. And here you can see the experimental setting. We used the EEG to collect the data from 8 subjects that did 12 blocks in total that gave around 2,400 trials per subject. And the time between 2 movements of the object was between 700 and 900 milliseconds. And the average error probability was 23%. So now I'm moving to the results. And first here we can see the average of all trials of all subjects of all conditions. So with green, we see actually the average of all correct or non-error trials. Red indicates the average of all error trials, and then the blue is the difference between the two. And for the people who are not familiar with this field, when we're working with event-related or error-related potentials, we're working with some components that we know that were already studied in research years ago. There are different components, and they are typical by some negative or positive like peaks that we see in the signal at some particular time or some time window. And there is also some characteristic voltage distribution on the scalp of the head. So here on the top plot, we see the voltage distribution on the skull at this time stamp that are related to these components that we studied. And also here we can see the results of the source localization for the mentioned components. So these areas that we see that are active are typical areas that are active when, during error processing, I mean when errors occur. Okay, and here we see the average per condition. So we can see with green that we have the results, the average of the errors for the shared workspace, that was this one. Then blue is the shared responsibility, and the dashed line is indicating the average of the errors for the interface, and dotted is for the agent. And visually, we can see that there are some differences. And indeed, the analysis of the interface, the dashed, and the agent, the dotted line, showed that there are statistically significant differences between the two. While when we look at the differences only between scenarios, so here these signals are computed as average of both the interface and the agent error, we don't see some big differences that we previously had. So because we were able to see that there are differences between the agent errors and the interface, which means self-related errors, we also tried to classify them, and the classification was done in 2 steps. So first, we wanted to see if just from every single trial, we can understand if this trial was error or non-error, and we were able to classify correctly with accuracy of around 81%. And then we tried to see if from the error trials, we can see if it was agent or interface error. And we got accuracy of around 71%. And now I will sum up. So we saw that there were different components that we could observe from the data from this experiment. And the components were produced in some typical areas that are well known for error-related potentials. And we saw that the self and the agent-related errors are different. And they're in particular different in the time window between 200 and 600 milliseconds. And we also saw that they're well separable. So this leads us to the conclusion that the results allow distinctive machine adaptation based on the subjective perception of the human. What does that mean? That means that when we have a robot and a human, and when they should co-adapt to each other, if we record error-related potentials for the human, and we want to use them to adapt the robot to the human needs, we will know if in that particular situation, the robot should be adapting to the human, or the human will adapt to the robot. And with this, I will finish, and I'm happy to take your questions.
Thank you much. I'm sorry. Thank you very much, Victoria. That was an extremely efficient and interesting report. If we have any question, please put the line of your question into the chat, or you can just speak freely, activating your microphone. While the people thinking about this, I would like to ask like a more general question, not about the details, but could you specify like top 3 clinical applications in the future for these methods? How you see what we can improve?
So after yesterday's talks from all the experts, I don't feel very confident to give such comments as a young researcher. But if we talk about clinical applications, I think, as it was already talked a lot yesterday, the communication and control are very important and probably the most promising. And concretely, this work that I showed is very applicable for control and correcting errors.
Yeah, okay. Do we have any other questions? Yes, yeah. Sergey, please.
You have quite a good classification rate for 80%, but still there are some errors. So in how you view the use of such technology in practice, because probably in recognition of error-related potentials, we will always have some errors, maybe just a few, but there will be some. So there will be error in recognition of error, and so the situation will become complicated. So how it will actually work?
Mm-hmm. Yeah, okay. Yeah, I agree. I mean, it depends also on the optimization of the algorithms. So we could work towards optimizing them, or we could maybe work towards designing experiments that will really give us very clean data, because it can happen that although I tried to design the experiment in a way that everything is clear and there might be no misunderstandings with the subjects, there still might be some cases where what the subjects thought is not what we expected them to think, and that's already the first step for making errors. Well, for the classification, I already said, I think that we should work on the optimization of the algorithms.
Do we have any other questions?
Yes, I may have a question, if I may.
Yeah, please.
So, and what type of features actually did you use to for the classification of the two errors potentials?
Mm-hmm. So I used only, so I extracted the features with PCA. I cannot tell you, I mean, I cannot say that I used just some component, let's say, because that's not what I did. I just used the features that describe the most of the variance.
Thank you.
Hello. Could you tell me if it would be possible to use this SVM online, or it's only designed to be used in offline applications?
So this was an offline application, but I do believe that it can be used online, which of course would have some time delay, because if we need at least 1 second to, 1 second after the stimulus to extract features from that post-stimulus time, then we would have at least 1 second of a delay.
Okay, there is no any other questions as I see. Victoria, once again, thank you very much. It was the first, and that was the brilliant report. Thank you.
Thank you.
Never mind, we're all remote and sitting probably at our home, maybe at our offices. Please do not miss the opportunity to network with each other, and just put in the chat for speakers, for example, the link to your LinkedIn account or maybe your email, saying that you will be glad to send all the materials or some papers. I think that will improve a lot of our communication. Also, you can use Zoom to chat directly to a speaker. Okay, let's move on. The second report, this research is made by the team of different researchers. It's Maria Volodina, it's Nikolai Smetanin, Alexei Alexentsev, Olga Turina, Mikhail Lebedev, and Alexei Asatchi. And this team is from the Center of Bioelectric Interfaces. It's National Research University High School of Economics from Moscow, Russia. And their topic is meditation in masters and novices, brain activity, autonomic function, and prospective biofeedback systems. We all know how much the biofeedback means for good rehab, and also of course the meditation is one of the crucial parts in the whole process. So I would like to invite Maria to speak. You have all the time you need. Thank you.
Okay. Hello, can you hear me? Huh?
Yes, we can hear you well. Yes.
Okay.
Perfect.
So then the presentation. My name is Maria, and I'm from Moscow, from the Center for Bioelectric Interfaces, and I will tell you about one more research about meditation. There are a lot of studies about meditation, and most of them tell about beneficial effects of long-term meditation, including increase of well-being, increase of memory, prosocial behavior, decrease of cardiovascular risk, and inflammation, and a lot of others. Much less studies talk about side effects and adverse effects of meditation. Hopefully this is because such effects are really quite rare. EEG studies about meditation are very controversial, but I would say that the most of researchers of at least mindfulness meditation tell about simultaneous increase of alpha and theta power during meditation. And it can be considered as a sign of relaxed alertness state. So the state when your mind is concentrated and your body is relaxed. There are also
Maria, I'm sorry. Could you please check for me? Do you have any slides?
Yes, you can.
Okay. You need to share the screen.
So sorry.
I'll tell you, then they'll see it.
Yeah, sorry. Can you hear it now?
Yeah, well, we can see it now. Please full screen. Yes, perfect.
Yes,
thank you.
Okay, then it was about EEG during meditation. So this kind of summary of previous researches that in most studies you can see simultaneous increase of alpha and theta EEG power, and is considered as a relaxed alertness state. There are also a lot of consumer biofeedback devices for meditation, and also neurofeedback devices based on EEG. I guess the most popular one is Muse headband. And the limitation of all these devices, they usually don't tell what kind of feedback they give and what is the target signal they use. And actually it looks like most of them just use alpha power as target signal, and they tell this is meditation feedback, but actually it looks like just relaxation biofeedback. By the way, about the adverse effects of meditation, here in the center, you can see the picture. This is a screenshot from promo video of one of meditation applications. And probably 3 of these children will have some problem with their lower back as they're sitting in the wrong position. And this is really serious limitations that you you can't use some device just instead of teacher, instead of person who will say you are doing right or wrong or what happens. Otherwise, you can have some side effects instead of benefits. I can remove it, but anyway, yeah. So the question of our study was, do we really need EEG to say if person is meditating or not? So there are a lot of neurofeedback devices for meditation, but it is still the question. So one of the hypotheses of Alex Osachi, my chief, was that we don't need EEG, that it's just enough to have peripheral measures like heart rate, respiration, galvanic skin response for such feedback devices. So the aim of our study was explore the dynamics of central nervous systems and autonomic nervous system activity during guided meditation, compare dynamics in experienced meditators and novice subjects, and to find the modality that is the most informative and that should be used in biofeedback systems. Okay. We had two groups of subjects. The first one was were experienced meditators. They had experience of regular meditation practice from 2 to 32 years, and the median experience was 8 years. And all of them had experience in different kinds of meditation. We especially didn't limit them to some special kind. We didn't took just Buddhist monks or something like that. And the second group were novices without any experience of intentional meditation. All of them performed the same meditation. They got guided through earphones. And this whole session was 37 minutes. And during this meditation, we recorded respiration rate, respiration wave amplitude, galvanic skin response, and heart rate variability, and also recorded EEG. What we had? We had the signs of relaxation in experienced meditators. We weren't surprised about it. It was what we expected. We could see increase of heart rate variability in this Erasmus coefficient operation, decrease of stress index. It is also index calculated from heart rate variability, decrease of respiration rate, and increase of respiration amplitude compared to novice subjects. At the same time, we didn't see difference between these two groups in EEG. Both experienced meditators and novices had U-shaped decrease of alpha and beta EEG power. The dashed line mean baseline. So all values are normalized to individual baseline of the person. And the effect was the same. And so on this point, it looked like we really don't need EEG, as we could see just concentration maybe in novice group and a kind of relaxed alertness. So simultaneous concentration, decreased alpha and beta, and increased body relaxation in experienced meditators. We also performed representational similarity analysis and had found interesting point. We found that in experienced meditators, it was highly significant representational similarity between heart rate variability indices and respiration indices and alpha and beta power. It goes in line with previous studies that have shown a higher connection between brain and peripheral nervous system in experienced meditators. So what we got? We got that we could see really relaxed alertness in experienced meditators and just some kind of concentration in novices. And we don't need EEG at this point. But to check this hypothesis one more time, we introduced index of relaxation. It was calculated as a scalar product of coefficient operation, it is heart rate variability index, and prefrontal alpha to theta ratio. So idea is in case of relaxation, it will rise. In case of concentration, it will go down. And we expected to see something about unit in experienced meditators, as they have simultaneous relaxation on the body level and concentration on the mind level. But apparently we have seen another picture. We found clear split of experienced meditators group into two supergroups. In one group, this index of relaxation rose, and we call these persons relaxed meditators. And in another one, it was clear decrease of this index of relaxation compared to baseline. We call them concentrated. Then we performed detailed analysis of these subgroups and found that in these concentrated meditators, there was increase of delta power and strong decrease of alpha power and alpha to theta and alpha to beta ratio during meditation. In relaxed meditators, we could see oppositely some increase of alpha power during the last stages of meditation. At the same time, in relaxed meditators, there was increase of heart rate variability indices, decrease of stress index, and decrease of respiration rate, and not so much effects in concentrated meditators. To summarize, we found that there are two groups of experienced meditators in one subgroup, concentrated one. There was strong decrease of alpha power, increase of delta power, and just slight changes of heart rate variability and respiration rate. In another group, relaxed meditators, oppositely, there was strong increase of heart rate variability, decrease of respiration rate, and quite slight increase of alpha power. So actually, we got not relaxed alertness state in all meditators. We got one group of relaxed and one group of alerted meditators. And to conclude, so we have found that experienced meditators during meditation had different physiological changes from novice subjects. We found two meditation strategies. One subgroup had signs of relaxation and another one had signs of concentration. This meditation strategy was independent on previous meditation experience, age, and some other parameters measured. There was no such split in novice subjects. And this is really important, I think, that we should consider such splits, such different strategies when we're designing our biofeedback meditation devices. As in case this person seems start to concentrate when he start meditating, it will be silly try to increase his alpha in this moment. And this index of relaxation, this index of relaxation we introduced can be used as metric to determine individual strategy of meditation. Okay, that's it.
Thank you very much, Maria, and thank you for being in time. Do we have any questions from the audience, from the participants? You can put it in the chat or activate microphone and speak just right now. During your talk, I just figured out the topic which somehow related to you, but it's not particular about your paper. Do you have any correlation, as you think, between the index of relaxation and the probably index of stress, which also can be measured using different techniques regarding the pulse, regarding the EEG and other things?
I don't know what kind of index of stress you're talking about. There is kind of a stress index of Bayevsky that is calculated from heart rate variability. It's related as our index of relaxation is the product of heart rate variability and prefrontal alpha to theta. So it will be correlated definitely. But maybe there are some other stress index you're talking about.
Okay, no, I think. Thank you for this answer. But also we have a question from Ivan. I'll read it for everyone. Can this difference in meditators be explained by different techniques used by the experienced meditators?
Yes, it's a very good question, and it is a very good idea. So actually, it can be explained by different techniques that usually use these meditators. But at least in our study, I have analyzed the data about previous experience and didn't see such correlation. But maybe we need more people, more subjects to say it to be sure.
Yeah, thanks. I guess Ivan is satisfied with this answer. Yeah, he's thanking you. Do we have any other question, colleagues? If you have, please write down directly to Maria, and I'm sure she'll be happy to answer you and talk more about
Thank you.
her study. Yes, thank you very much. So we're moving to the next speaker, and this is also the whole team of researchers. It's Svetlana Kim, Ilya Ganin, Olga Fedorova, also Mikhail Lebedev and Alexander Kaplan, and that's the team from Lomonosov Moscow State University and also Higher School of Economics, both institutions from Russia. And of course, BCI is actually easy to use, relatively safely compared to other neuroimaging techniques right now. And it gives us the whole information of brain activity and the whole visualization, which we could use during the sessions and post-session analysis, especially in this important topic as speech restoration. So Svetlana, please, you can go.
Thank you, Denise, for the nice introduction. Hello, everyone. My name is Svetlana again, and I'm a PhD student at the Laboratory for Neurophysiology and Neurocomputer Interfaces at Moscow State University, and I'm supervised by Professor Kaplan and also Olga Fedorova, who is a professor in linguistics. So language disorders are one of the most disabling consequences of brain damage, and left hemisphere ischemic stroke often leads to language disorders such as aphasia. People with aphasia suffer from the poor or no ability to speak, to understand speech, and write and read. So aphasia affects more than 20 million people worldwide. Restoration of communication is available for such individuals via voice synthesized speech or text based on brain or muscle activity alone. I'm sure you've heard a lot about it yesterday during the speech of Sanwan Lee about imagined speech. And there are also going to be some other talks about it in the next presentation of my colleague. It was previously showed that it's feasible to reconstruct intelligible speech from brain activity alone. But not only speech can be reconstructed, we can also reconstruct handwriting solely from the muscle activities of hands and forearms. The visual P300 speller allows the users to type texts without using movements and voice. And more recent research also showed the possibility to create neural interface speller prototypes for clinical and real-world applications. Sorry. So P300 BCI spelling paradigm looks like this. We have a matrix of letters and symbols that are arranged in rows and columns. The user reacts by counting silently whenever the target symbol flashes. The software detects the target letter and identifies the target letter and displays it on the computer screen. Our lab took part in the development of a neural interface set called NeuroChat. It is designed for communication of individuals with speech and motor impairments, and It is also designed for easy use in clinical and real-world applications. It consists of hardware with a wireless cap with 8 electrodes, and also software for decoding brain signals and web communication. So we conducted a pilot study with post-stroke patients with aphasia using this NeuroChat system. The results were published recently in the Journal of Higher Nervous Activity. Restoration of communication using B300 BCI speller can be beneficial for individuals with speech and motor disorders, for socialization, thus promoting their rehabilitation, and also it may be possible and it may be beneficial for their cognitive functions. But there is still few studies with small sample sizes of post-stroke patients and or a small number of BCI sessions. The objective of our study was to test the NeuroChat system in a clinical environment with the post-stroke patients with aphasia. And among the tasks, there were identification of performance indicators of how patients master the technology, study possible dynamic effects of the long-term use of such system, and identify potential training effects. So 19 patients with post-stroke aphasia of mild to medium severity took part in the research while they were undergoing rehabilitation at the Center for Speech Pathology and Rehabilitation in Moscow, which is probably one of the major places in Russia for rehabilitation of patients with speech and language pathology. There were 9 females, and they all had ischemic stroke in the left middle cerebral artery, and time since stroke was 77 days. So each patient took part in 6 to 11 BCI sessions, depending on how good they felt and the duration of their treatment, an average of 8.8 sessions. We assessed their performance during their BCI sessions. Those indicators, performance indicators, included spelling accuracy, time of spelling a letter, and a number of letters that were typed during the session. Patients also underwent a comprehensive neuropsychological and neurological testing before the first and after the last session. So each session was divided into 2 phases of classified training followed by spelling. Not every training session ended up in spelling. It depended on how high results the patient achieved. So spelling included a spelling of 5-letter words, at least 3 per session, and average of 7.9 sessions ended up with a spelling phase. These are results over the course of 10 sessions. So we see that the spelling accuracy increased by 29%, the spelling time by 1.5 times, and letters per session that were typed doubled. The attention assessment also showed some improvement. The work efficiency and psychological stability increased after the end of the last session comparing to the beginning of BCI sessions. Neuropsychological evaluation also showed that there were higher scores and regulatory and background components, including neurodynamic aspect, and auditory verbal memory was also improved a bit. So we also found correlation between neurodynamics, auditory verbal memory, and efficiency of using the BCI speller. So the conclusions are the following: that most post-stroke patients with mild to moderate aphasia and motor impairments were able to master the technology, and they could type words. And there was a positive change in spelling performance over the course of 10 sessions. And the greatest increase in accuracy and the greatest decrease in spelling time were observed within the first 5 sessions. There were also preliminary improvements in scores for some aspects of cognitive functions and executive functions, and also verbal auditory memory after the BCI speller sessions. So we need some further studies to deepen this knowledge. There's some acknowledgement. So there are my co-authors and contributors, and also some people who gave me some insights for preparation of this presentation. So here we have the Center for Speech Pathology and the Neurotrend, who designed the NeuroChat. My colleagues from Lomonosov Moscow State University, including my scientific supervisor from the Department of Theoretical and Applied Linguistics, and also Mikhail Lebedev, who gave very precious insights into this presentation. So thank you. Do you have any questions?
Svetlana, thanks a lot. Audience, do we have any questions for the speaker? You can use chat, you can use activate your microphone and just ask directly. From my point of view, I know very well the NeuroChat technology. It's such an amazing thing. You mentioned that you think about going more deeper in the research in this field. What do you have in mind? What kind of opportunities do you think you can study here? Would you like to improve accuracy of this method, or to make it more easy to use for these patients?
Well, I think we need to study further this adaptation process of these patients, because actually, I mean, their experience in using this kind of technology is very different from those who don't have any impairments. I mean, healthy subjects. Yeah, sure. So we want to. I think we are eager to make sure that those improvements in the cognitive functions and some aspects of those cognitive functions and its correlation to the performance they had during the BCI sessions, so we want to build a cause and effect relationship between this. I mean, to make sure that it's really affected. So we probably would have some control group for this to compare the results of people who didn't have BCI sessions, or who were undergoing also all only some rehabilitation treatment alone, or with the BCI speller without any feedback. So these are some of the ways we can continue this study.
Yeah, thank you. I think this is an amazing plan. You think about not only figuring out how to make the algorithm better, but also to make the user experience better, which in this thing, of course, is quite crucial, because they are part of adopting this technology into the patient life is really hard for most of the cases. Okay, thank you once again a lot for your work and study and speaking today. I think that we'll move to the next speaker, and it is Aska Takai. And Aska works at the Department of Brain-Robot Interface, Computational Neuroscience Laboratories. It's actually from Advanced Telecommunication Research Institute International in Kyoto. Also, Department of Physiology at the University of Tokyo, and Department of Cognitive Neuroscience, Brain Information Communication Research Laboratory Group from ATR from Kyoto, Advanced Telecommunication Research Institute International, ATR, Kyoto. And the topic is neuro investigation towards motor skills improvements through brain-computer interface-based training. Aska, are you here? Hello? Dr. Takai, are you here?
Yes, sorry.
Oh, great. Great to hear you. So that was a long introduction because you're a really busy person with all the work and institutions that you attend to. The floor is yours. You can start. You have 10 minutes. And I remind you to share your presentation.
Okay. Sorry, please wait for a second.
No problem. We have time.
Okay. Okay.
Yeah, we can see that you studied this and we can see your presentation.
Oh, great. Okay. Thank you for your kind introduction. Good afternoon. I'm Asuka Takai from ATL Japan. So it's a great honor for me to have this opportunity to present our findings here in International Conference of BCI Samara 2020. So let me start talk on behalf of my co-authors. So growing number of literature have been developing BCI computer interface training for rehabilitation of patients with motor impairment. The efficacy have been started to prove, and these are two BCI-based robotic assisted motor training system from my laboratory. And like other BCI rehabilitation systems, we use an EEG cap and then decode the motor intention and then activate the robots to assist upper or lower limb motion. And we have been evaluating this rehabilitation effect at hospitals in Japan. And we see the improvement in upper limb clinical scores. So various studies have also revealing these clinical scores are improved by such BCI-based rehabilitation. But in order to use their impaired limbs in daily life, the ability of good limb control is required. So we decided to investigate whether the BCI systems can also go a step further to improve motor performance. So here are some example studies which observe the magnitude changes in EEG caused by the different strengths of movement. And the last one, but not least, is another study reporting actively modulating the motor cortex by TDCS that also enhances the sequential trial tasks, the motor tasks. So these previous studies report correlation of neural modulation and movement features, but however, the effects of neural modulation on precise motor performance are not well understood. So towards the improvement of precise movement by BCI-based motor training, we test this hypothesis by analyzing the runner's brain state during motor training. So we designed a drawing experiment, and in this experiment, the subjects were asked to memorize circle drawing movement. And in order to train subjects in consistent manner, two link manipulum showing right side guides the subject by moving their arms along the circle trajectory. And also, during this haptic guidance, the subject's EEG was acquired for offline analysis. And also, in order to maintain consistency among subjects' training condition, only the haptic modality was maintained by keeping the task workspace visually hidden. So the subjects undergo this experimental protocol. Firstly, they perform the motor task 15 times in order to define the initial performance. It's on the left side. And in the haptic training session, subjects rest for 5 seconds and then receive haptic guidance from the robot. And once haptic guidance is completed, the subjects rest for another period of 5 seconds and subsequently reproduce the target movement. And during the rest condition, subjects are explicitly asked to relax and avoid motor-related thoughts. And easy signals are collected throughout the haptic training session. And the experimental was conducted on 10 healthy right-handed subjects. Okay. So let me move on to talk about the results. Let me start with the data inclusion. The measurement of motor reproduction is stopped when the end effector exceeds a specified safe area, and such trials are not evaluated. And the average number of trials that are kept for evaluation are shown in a table, and the average are nearly the same. And for the purpose of evaluating drawing accuracy, the motor performance is evaluated as positional distance from the target circle. So it is evaluated while the robot guided the subjects on the target movement at constant velocity, and that traveling time takes about 1.5 seconds. And the average difference of motor task error between initial and reproduction is computed according to the following equation shown here. So based on the motor performance, we grouped the subjects in 2 groups. Well, this graph in left side shows the difference between the initial positional error and that of post-training. So the negative value of the difference means the performance improved. So from this figure, the 6 subjects were labeled as improved and the 4 as not improved. And the 2 sample t-tests between these groups indicates a significant difference. And according to the 1 sample t-test, the improved group got significantly better at performing the task, while the not improved group, their performance did not get significantly worse. So let me move on to talk about EEG processing. All subject EEG data are processed through the same pipeline. All the 90 EEG channels are initially bandpass filtered in the 5 to 48 Hz range, and all the channels are epoched from -3 seconds to 3 seconds with respect to the haptic guidance onset. And at each time step, the outlying channels are removed using a deviation criterion based on the modified Z-score. An average number of removed channels across subjects about 1.25. And once the outlining channels at time t are removed, the mean of the remaining channels at time t is subtracted from the all channels to compute the common average difference in the car. And after such pre-processing, we focus on electrode C4. For each subject, the trial averaged and baseline collected event-related spectral perturbation, ERSP, is computed. And we apply a single trial full epoch baseline correction before averaging across trials, and then removing the trial averaged pre-stimulus. And corrupted single trial time frequency representations, TFR, are removed from the computation of the ERSP. And for each epoch, we compute the mean power over the whole TFR. And subsequently, we use the modified Z-score to find and remove the epochs with an outlining mean power. An average number of removed epochs across subjects is shown in the table. So in order to compute statistics across groups of subjects, we need to obtain two values representative of the strengths of mu and beta ELD respectively. So for this purpose, we compute the mean of the trial averaged baseline corrected ELSP. The black boxes depict the two frequency bands where the ELD strength is evaluated. The obtained mean values of mu and beta ELD are then log transferred. So here's the result. We computed the statistical tests using mu and beta power strengths over the respective ROIs of the both subjects groups. And the figures shows a clear trend that the beta band of the improved and not improved groups are significantly different. The effect size of the difference in the beta band is 0.83, which is greatly considered, generally considered a large effect. So on the other hand, the mu band does not show any interesting trends. Okay. So these preliminary results shows suggesting maybe that people who improve their performance also exhibit a stronger beta ELD over the contralateral hemisphere during the haptic guidance. So these new findings among pure haptic guidance training is in agreement with previous studies with active motor training. That is Nelson and Corrigius done, and they confirmed that the beta SMR over the contralateral sensory motor area significantly increased as their subjects execute the reaching task more accurate, more faster. Okay. So in conclusions, the strong brain activity during haptic guidance entail improved motor performance with respect to initial performance. So this correlation does not imply causation. So therefore, it is not possible to say that a stronger ELD caused the improvement. But nevertheless, our result represents the accumulating evidence that beta modulation is associated with improvement in motor parameters. Okay, that is all of my presentation. Thank you for listening. If you have any questions, please ask me.
Thank you very much. Do we have any questions? Just to wait for a few seconds.
Yes.
Because I saw the participants who may be actually extremely interested in this field. Mm-hmm. Maybe they have questions for you.
Sure.
Yeah, I'm not actually myself a specialist in the BCI interfaces for motor in the motor field and motor activating skills. But do you think, is there any promising results will be in the future? Then we can use the implanted EEG electrodes probably.
Sorry, implanted EEGs?
Yes, yes. Do you think that how can this affect your study in this field?
Mm-hmm. I'm not a specialist in implant easy or equal kind of equipment, but I heard that it can correct more detailed motor intention of the patient or maybe the person. So it could be, I don't know. Current research is focusing on classifying how the hands are moving or doing this or kind of classification. But but my interest is in motor learning or training. So maybe the capturing only the signals from the motor sensory area is not much enough for the motor training. Maybe we need some more active way to, I don't know, more active way to interact to that area to enhance the motor training or improvement procedure must be needed. I hope I answer your question.
Yeah. In general, yes. Thank you very much. If you don't mind, could you please share in the chat your contact, email, and information?
Okay,
I guess
sure.
that some of the participants would also like to write to you directly.
Okay, sure.
And thank you very much for your study and your work. Thanks.
Thank you.
Okay, let's move on to the next speaker. But before that, I would like to remember you that you miss an opportunity if you're not participated to any of Facebook accounts of BCI Samara, because there are a lot of information and also live stream from all the session. To do that, go to your Facebook, type BCI Samara, click support, like, share. This is extremely important for us to share the information of all this research and all these great people who participate to this conference. Okay, next team is from Lomonosov Moscow State University, which is in Russia. It's Andrei Kitaitsev, Ilya Ganin, Rafael Grigoryan, Anatoly Vasilyev, and Professor Alexander Kaplan. And the topic is P300 BCI speller with human faces, with human face images, the effects of stimuli variability. Well, I do not think that I have enough knowledge on that topic, so I would just give the word directly to the speaker. And I think it will be Andrei, right?
Yeah, that's right.
Yeah, okay, you can share your slides and go on.
It says that host disabled participant share screen sharing.
Let us do something with that. Just 1 second. Just 1 second. I guess I need to make you an organizer to do that. Okay, try it now. Yeah, perfect. We can see it. Full screen, and you can go.
Well, hello everyone again. My name is Andrei Kitaitsev, and me and my colleagues collaborated to work on the project on P300 BCI speller with human face variativity, with human face images to create stimulus variativity. So the basic of P300 BCI was already presented by previous speakers, so I will very briefly touch this matter. So we have a screen with a matrix of symbols, which are column-wise or row-wise highlighted, or they may change size or whatever change is possible. And then it is being perceived by participant. and via EEG, or actually here it could be also MEG or fMRI or any other brain imaging technology. The signal is being classified, and the stimulus to which participant attend elicit higher P300 amplitude than the stimulus to which participant does not attend. And this is used in many clinical and practical and theoretical applications. And there are different strategies to modify this technology because of its omnipresence. The first one is to enhance the difference between stimuli, so to make stimulus classes more different per participant. And the second strategy is to modify classification algorithms and pre-processing of the signal. The idea of this research was to create modification in stimulus. So in conventional P300 BCI stimulus, there are generally two groups of stimulus: target and rare. Target rare and non-target frequent stimuli. And so rare stimuli elicit higher P300 than frequent stimuli. And the idea of this research was to further exploit P300 BCI principle to make target group heterogeneous. So to create target rare stimuli into frequent target stimuli and rare target stimuli. And we assumed that this might modulate or facilitate attention of a participant and thus result in BCI incremental BCI efficiency in terms of classification and so to say typing speed. So here you could see the basic metrics we used. We decided to exploit images of human faces as stimuli because it was shown in multiple researches that it is more efficient than to use just highlights. And we used different types of stimuli, the images of emotional, or on jargon, happy faces, and images of neutral faces. And all these two types of stimuli were presented on the background of meshed pixels contributing to these images to account for brightness change. And also the experiment consisted of 2 sessions, but of this I would speak a bit later. And so we could see how it was implemented. So the participant observed some letter, let's say B, and was given a task to, for example, calculate or count number of times which this letter was highlighted. And experimental design was the following. We had 2 sessions with different number of participants, and each session consisted of 2 blocks. The first block is classification training, during which 5 symbols were selected. And the second block is actual choice of symbols when the classifier is trained. And for each symbol, usually these were letters, we used different groups of stimuli. So in this example, the black squares
Andrei, are you here? I think we have some technical problems here. We can see your presentation. Now you can activate your microphone and after that speak.
Oh, yeah, sorry for
Thanks.
interruption. So there were different classes of stimulus, and here you could see that there are non-target stimulus and then frequent target stimulus, for example, images of neutral face.
And I think once again we have a technical issue here. Andrei, we cannot hear you. Okay, Andrei is connecting. Okay, Andrei, let's try to continue your talk.
Yeah, sorry. So
maybe you could not activate your video for right now if we have like a channel problem or something.
Yeah, if I would be
we can see the presentation. Yeah, you can go on.
Okay, so could you see it now still? Okay.
Yes, right now we can see it.
Mm-hmm. So the experimental design consisted of 2 sessions. In the first session, we had 4 different modes, different in amount of target stimuli of specific emotional valence. So, for example, here we can see that the first mode consisted only of happy facial images. The second mode consisted of only neutral facial images. The third and fourth modes consisted of different proportions of happy face images and neutral face images. So these were the modes with additional stimulus variability. And in the second session, we had additional fifth mode without faces, just with meshed pixel picture for stimulation. This is the short summary of analysis pipeline. There is nothing special about it, just it's worth mentioning the parameters of filtering and probably the window in which the P300 was calculated. So the statistical analysis scheme actually consisted of 2 blocks. First was subject-wise, so for each subject and for each electrode independently, we applied Friedman test, and in the second block, we analyzed averaged P3 amplitudes for all the participants. And we analyzed it also with Friedman test for each electrode independently, and also separated the data into emotional stimuli subset, where we had stimulus without variability, so mode without stimulus variability, mode with frequent happy stimuli, and with rare stimuli. And the same was made for neutral stimuli modes. And we could see on this picture the ERP images of deltas. So it's actually not ERP, but target stimulus minus non-target stimulus for subjects at different channels. And intersubject analysis yielded not very typical results. As we could see, there seemed to be difference between rare happy stimuli P3 amplitudes and all other stimuli amplitudes. However, statistical analysis of intersubject data didn't reveal any significant differences. If we consider 2 factors like frequency and emotional valence of stimuli simultaneously. However, if we divide our subset into frequent, if we divide our subset into 2 different groups for happy stimuli and neutral stimuli, so if we partial out the effect of emotion, we could see the significant difference in both factor repeated measures, ANOVA analysis, and post hoc analysis corrected by Bonferroni correction. And as we could see, in many electrodes, it is significant. So amplitudes of P3s elicited by rare target stimuli were significantly higher than all other amplitudes. apart from one electrode. And if we analyze the results subject-wise, so for every channel at every subject independently by Friedman test, which is non-parametric analog of two-way repeated measures ANOVA, we could see that factors of factor of frequency was significant in many electrodes for many subjects. So the numbers you could see here indicate significance, and the numbers you can't see indicate that there is no significant differences. But post hoc analysis interestingly revealed no significant differences between groups. And so we also noted the unusual ratio between P300, P200 amplitudes on this data. So during the first session, as you might remember, I could show the slide again, the P200 amplitude was higher than P300 amplitude. And that's unusual for P300 BCI. And to check if the current paradigm elicited this ratio, we constructed special second session of which I talked about previously. And in this second session, there was additional mode 5 without facial stimuli. So just conventional P3 BCI. And as you could see from these ERP graphs, the fifth mode ratio of P3, P2 peaks is conventional. So P200 is smaller than P300. But in all the other modes, P200 was higher than P300. So this additional stimulus variability somehow elicited higher P200 than P300. And we also evaluated online accuracy, so the accuracy of symbol choice, and it was almost on a plateau, more than 95%, and the differences were not significant. We hoped that offline analysis of accuracy would reveal some significant differences. It's basically cross-validation evaluation of performance with different amount of target stimulus chosen. But as we could see, there were also no significant differences in offline evaluation of accuracy. So the results state that absence of increment in online and offline accuracy of symbol choice could be due to inappropriate classification, inappropriate classifier used. So we used Fisher LDA, and it is not the best choice to use when there are unbalanced amount of stimuli in each classes which we have. And intersubject analysis of frequency and emotion factors considered together didn't yield significant differences. However, in a subset of emotional stimuli, significant differences were in both factor of frequency and in post hoc analysis. And it was not the case with neutral stimuli subset. And it was shown in many papers that emotional stimuli modulate attention, modulate P3, P2 components of event-related potentials. So we might assume that these results somehow correspond to already existing data. And subject-wise analysis revealed that frequency factor was significant for some participants in some channels after accounting for raw effects of different valence of emotion. But post hoc of this test, Friedman test, didn't yield any significant results. And facial stimuli elicited P2 component larger in amplitude than P3. And it is possible to assume that emotional stimuli may facilitate attention. As I mentioned, it was shown in many studies. And so the effect of interest of frequency of target stimuli could be expressed only in only when present in emotional stimuli. and it was not present in when presenting neutral stimuli. And so in combined subset, which contained of different frequency P3 amplitudes of both neutral and happy stimuli, it was masked by effect of neutral stimuli and therefore didn't prove significant in intersubject analysis. And it would be a good idea to use some more elaborated statistical tools which could deal with missing values and with non-normally distributed data which we have, like multi-level modeling or structural equation modeling, and also the use of a classifier which doesn't modulate the probability of stimulus, for example, Riemannian classifiers or maybe regularized support vector machines would be better and could prove or reveal absence of effect of interest. Thank you for attention and sorry for technical problems which made it probably a little bit messy. Yeah, that's it.
Thank you, Andrei. I guess that the technical problems didn't made your speech less important and interesting. It's really cool work. But yeah, regarding the time, we have only time for just one quick question. And if someone wants to ask it really short, please go. If not, we are moving on.
I would like to ask a question. So thank you, Andrei, for the very nice presentation. I want to ask you if you think that the phases are maybe too complicated and because of that you could not see effect from the different emotions, and if you use some other stimuli, let's say, I know, if you just colored the circles in some different colors, you would see some drift in attention because the stimuli is simpler.
So,
Andrei?
Yeah. It's a nice question, and we tried to use different types of stimuli, but considering some literature recommendations, we used facial stimuli because they themselves elicit more strong ERP responses, and so we just came up with the idea that the biggest difference between stimuli would be because we are humans, in different expressions of human faces, kind of. And there are some publications on this topic. But it's absolutely possible to do it with colors or with geometrical shapes. It's just probably not as efficient as with face stimulus, but yeah.
Okay, thanks. We go next. Andrei, could you please stop sharing the screen?
Yeah, sure.
Okay, good, thanks. So, once again, it's Technical University of Munich from Germany, and it's Stefan Ehrlich. And we agreed that Stefan could speak for 20 minutes. So his topic is passive BCI for assessment and adaptation of robotic systems during human-robot interactions. And by the way, for the participants who want to know more about RP and passive BCI, I extremely suggest you to Google and find Dr. Ehrlich dissertation. That's quite a good read, and it's accessible in the internet. You can read the whole PDF. Okay, Stefan, floor is yours.
Yeah, thank you very much, Dennis, for the kind introduction. And yeah, I'm happy to tell you today a little bit about my PhD work, which I did during the last years, focusing on the usability of passive brain-computer interfaces for assessment and adaptation of robotic systems during human-robot interaction. So when we look into the state of the art in human-robot interaction, there are still many unsolved challenges, especially in the domain of social and collaborative HRI. And the main reason for this is that current robot sensory technology can still barely capture the full complexity of human interaction partners. So what if we could silently read out information from the human brain and provide that information back to the robot? Could such a passive brain-computer interface approach facilitate or even improve human-robot interaction? And the human partner's brain is anyways processing all information required to interact with the robot. And as such constitutes a rich source of information useful for improving human-robot interaction. And the question here is rather, can we access this information reliably? But before we develop this idea further, let's have a look at current approaches taken to foster progress in HRI. An approach taken in the domain of cognitive neuroscience and experimental psychology is the offline assessment of robotic systems. And here, typically, human test persons are asked to interact with robotic systems under varying experimental conditions. And the typical measures taken from participants are questionnaire ratings, video recordings or interviews, behavioral measures, and more rarely also neurocognitive measures. To avoid interruption of the interaction flow with the robot, these measures are often taken at the end of the experiment, can furthermore be subjectively biased or are averaged within conditions. As such, the standard measures taken here are usually not instantaneously informative with regard to individual robot actions or events during the human-robot interaction, which limits the transferability of these findings provided by the studies into the domain of robotics. On the other hand, engineers aim at equipping robotic systems with online user adaptive capabilities. The incorporation of human models into robots up to methods for handling co-adaptation. As mentioned earlier, all of these approaches depend on highly effective and robust robot perception and reasoning capabilities, which are to date still an ongoing challenge. And this basically strongly limits the extension of this approach into more real-world human-robot interaction. The passive BCI approach, which I initially introduced, builds on top of both approaches and suggests their combination into a single method. And this combined method could allow the mutual compensation of the drawbacks of both the assessment and the adaptation approach, by first providing implicit, objective, and quantifiable measures immediate to individual robot actions or HRI events, and second, by augmenting robot perception with neurocognitive measures of the human partner without necessarily the human partner being aware of it. And in the following, I will present a collection of works that we have conducted in the last years that provide evidence for the feasibility and usability of this combined passive BCI approach. Specifically, we conducted 3 human subject studies and 1 model-based simulation study. In the first study, we demonstrate the feasibility to decode human intentions to engage with a robot from ongoing EEG signals. In the second study, we show that it is possible to assess erroneous robot actions through EEG signals of the human partner. And the target measure investigated here is the so-called error-related potential, which has been introduced by Victoria Di Mova earlier today. In the third study, we propose and evaluated a novel neuronal-based method to mediate co-adaptation in human-robot interaction. Also here we focus on the error-related potential as the target measure. And finally, in the fourth study, we systematically investigated the usability of this neuronal-based co-adaptation approach in the context of more complex and widespread human-robot interaction. For time reasons, I will only focus on the works on adaptation, since I believe these works are more relevant and interesting for the BCI community. So in our co-adaptation, we were interested to see if we can actually use error-related potentials decoded from the human partner on the fly during interaction with the robot to mediate co-adaptation between the two. Such co-adaptation is highly prevalent in the domain of social and collaborative human-robot interaction, where the human and the robot may have equal roles and need to find agreements to solve the task together. And despite the urge for novel methods to regulate such co-adaptation, it has still been rarely addressed so far and is among the major challenges in HRI. There have been a few works recently that demonstrated error-related potentials to be a useful implicit human feedback signal for reinforcement learning of robotic skills, such as, for instance, teaching end effector trajectories, binary sorting, and the recognition and replication of human gestures. While these works showed the great potential of using the error-related potential for robot adaptation, all of them have in common that unidirectional adaptation of the robot took place. The subjects were asked in these experiments explicitly to teach the robot a specific behavior or skill. What we aim to show instead is illustrated here. The human and the robot are asked to perform a task together. The robot starts with an initial policy that determines its behavioral strategy to solve the task together with the human. The human starts with an initial expectation towards the robot, which may gradually adapt to the robot during the interaction. Critically, we also provide online decoded error-related potentials to the robot to adapt its policy on the fly, such that both human expectations and the actual robot policy can ultimately converge to a consensus policy. The experimental paradigm featured a simple collaborative guessing game. There are 3 objects located between the human and the robot. The robot would start out by secretly selecting one of the 3 objects and subsequently start gazing at the objects. The subjects had the task to infer from the robot's gaze behavior which one of the 3 objects it has selected. Meanwhile, the robot's task was to learn a gaze pattern that facilitates the subject guessing the object correctly. Eventually, the subject would take a decision for either of the 3 objects and subsequently receive feedback from the robot about the true selected object. In that very moment, the ERP is decoded from the ongoing EEG of the human partner and provided back to the robot. And subjects were here deliberately not instructed to teach the robot a particular gaze behavior, rather that they had to find an agreement with the robot. Any gaze behavior was basically acceptable as long as it served the subject to guess correctly. Several measures were taken here to quantify co-adaptation. The focus is here on guessing or inference performance, which is supposed to increase if co-adaptation is successful. The gaze behavior was realized via a probabilistic state machine with 4 gaze states: gazing at the subject, gazing at the object of interest, or any of the 2 remaining objects. The transition probabilities between gaze states determine the robot's gaze behavior. Here we can see the example of a fixation behavior, which makes the robot gaze at the object of interest more frequently or remain staring at it. In the moment the robot provides feedback to the subject, error-related potentials would be decoded and turned into a reward used for updating the current gaze policy via a policy gradient-based reinforcement learning strategy. Each subject started by performing a calibration experiment, which was used to train subject individual ERP decoders. Here, a pre-programmed gaze policy was used that generated the fixation behavior, which I previously introduced. Error responses were elicited by artificially introducing false feedback from the robot. Among the 13 subjects that participated in the experiment, an average cross-validation accuracy of over 80% for the binary classification problem could be achieved. The subject-specific ERP decoders were then used for online decoding of error-related potentials in 4 subsequent co-adaptation runs. The online decoding accuracies turned out comparably high here, with close to 82% average across subjects. In each co-adaptation run, co-learning was restarted by reinitializing the robot's gaze policy to generate random gaze behavior in the first trial. The subject decisions were captured here via key press responses in almost all parts of the experiment. But importantly, these were only used as ground truths to validate the ERP decoder and the co-adaptation performance. To demonstrate that explicit decisions are not necessarily required for successful co-adaptation, we removed the key press responses in co-adaptation run 3. And here subjects were simply observing the robot's gaze behavior for a predefined time during each trial. And therefore, for co-adaptation run 3, no quantitative results will be reported. And this video shows the result of such an exemplary co-adaptation run of one subject. We can see here how the robot's gaze policy evolves while the guessing performance, which is shown as the blue line, gradually increases to up to 100% throughout the experiment. Across all subjects, median guessing performance increased throughout the 50 trials to a median of 70 to 90%, which remained also largely consistent over all individual co-adaptation runs. In addition, we had a qualitative look at the policies that emerged from co-adaptation. Interestingly, here we found 2 recurring policies, one which resembled the fixation behavior used in the calibration session, and a new one, which generates a nodding behavior as if the robot was attempting to establish joint attention with the subject. The fact that we observed 2 different policies, and especially the new one, can be considered a post-hoc indicator that indeed co-adaptation took place. Because subjects appear to have gradually adopted the nodding behavior as useful despite never having been exposed to it before. And very important, these policies were also observed in co-adaptation run 3, which suggests that also there successful co-adaptation took place. In summary, this first work proposed and successfully validated a novel neuronal-based method to mediate co-adaptation in human-robot interaction in a closed-loop fashion. The ERP as a target measure remained informative and well decodable despite volatile human expectations and beliefs towards the robot. Overall, this work contributed a novel approach to the largely unsolved challenge of handling co-adaptation in human-robot interaction, and most importantly, this method does not require any explicit intervention of the human partner. The qualitative results of co-adaptation run 3 indicated that sole mental reflection about the robot's behavior was sufficient for successful co-adaptation. While this co-adaptation study provided promising empirical results, we were left still with a series of open questions which remained unexplored. What are the main factors influencing co-adaptation, and as to what extent can we generalize and scale the approach to more complex and realistic human-robot interaction? And instead of conducting further empirical studies, which can be very time-consuming indeed, we chose here to model the human interaction partner and simulate the integrated human-robot system. This approach allows us to generate new hypotheses and design recommendations in a resource-saving manner and help direct future empirical studies. We focus here again on the experimental paradigm from the previous study. The system consists of 3 parts: the human, the robot, and the ERP decoder as the interface between the 2 parties. The robot generates actions based on the current policy, which are perceived by the human and turned into a belief about the underlying object. Here we use Bayesian inference to model this process. The belief is eventually turned into a decision, for which we use belief thresholding via a decision bound. Eventually, the human receives feedback from the robot and compares it with the decision taken. This generates an internal prediction error, which in fact simulates the error-related potential. This prediction error is used for updating an internal knowledge model via reinforcement learning, and is also furthermore fed into a simulated ERP decoder, which turns it into a reward used by the robot to update its policy. The model has 6 free parameters which aim to capture subject-specific decision-making and adaptation style during the experiment. These 3 parameters were then successfully fitted based on the behavioral experimental data of individual subjects. The results showed that the fitted model was hereby capable of predicting on average more than 70% of all subject decisions during the experiment. With these results, we can now reach out to actually simulate variations of the original experiment. As an example, we can now address if any hypothetical improvements of ERP decoder performance would actually lead to noteworthy improvements of co-adaptation performance. And more importantly, if such efforts are useful or whether there are other more critical factors which should be in the center of our attention. So we conducted in total 5 simulations. In the first simulation, we investigated the expected convergence times. Here we noted that it was rather expected around trial 150, which demonstrates that the initially assumed number of trials in each co-adaptation run were too short. And this may also explain why successful co-adaptation could not be observed in all subject and co-adaptation runs. Secondly, we looked into the influence of human factors described as variations of the 3 model parameters. Results showed, and this was surprising, that variations of these parameters have a negligible impact on co-adaptation performance. This is in fact really exciting, as it suggests the approach to be well generalizable across subjects if we could just stabilize ERP decoder rates. Furthermore, we looked into hypothetical variations of ERP decoder rates. These turned out to have a drastic effect on co-adaptation performance, which was expected. The interesting outcome here, however, was that non-error decoding rates seem to play the major role, while error decoding rates have comparably low impact. These insights give us now some flexibility to stabilize ERP decoder rates, such as by simply biasing ERP decoders to emphasize precision for the non-error class. In addition, we compared the originally used policy gradient-based method for robot adaptation with a standard Q-learning approach. The Q-learning approach not only turned out to be superior, but also less sensitive to across-subject variations. And finally, we looked into hypothetical extensions of the state space. And this turned out to be theoretically unconstrained and are dictated only by convergence times, which may become impractically long. By assuming a convergence time below 20 minutes to be practically acceptable, still allows an extension of the state space to up to 10,000 degrees of freedom. And this as compared to 16 degrees of freedom, which we had in our original experiment. So in summary, this work proposed a computational model that enables the prediction of human decision-making and learning in our exemplary human-robot interaction scenario. The simulation results provided us tangible insights about how to generalize and scale up the approach, such as by employing biased ERP decoders. And with this, I will turn to conclude my talk. In conclusion, this collection of works provided evidence for a series of implicit, objective, and quantifiable measures for the assessment of both intentions and beliefs, as well as robot actions and HRI events immediate to their occurrence. Although only touched upon briefly, these are the single trial decoding of human intentions to engage with a humanoid robot, the human partner's believed social role during interaction with the robot, and the detection of erroneous robot actions. In addition, in our co-adaptation study, we showed that also violations of shared beliefs between human and robot are well decodable in single trial. With regard to adaptation, we demonstrated the usability of neurocognitive measures to enhance robot perception via implicit human feedback that enables the adaptation of robot behavior towards human expectations. Specifically, we proposed and successfully tested the novel neuronal-based method for closed-loop mediation of co-adaptation and showed in the model-based simulations how this approach can be generalized and scaled towards more complex human-robot interaction. Just to give you a brief outlook on our current works, here we focus on the investigation of the limits of observability and decodability of error-related potentials in more ecologically valid human-robot and also more generally human-machine interaction. For instance, we're looking also into autonomous driving and how the driver is perceiving the behavior of the autonomous car and how that car behavior could be adapted. Second, we are also interested as to what extent ERPs are informative beyond the simple binary mismatch. And specifically, the work presented by Victoria Dimova earlier today points towards an exciting direction here, because her findings show that the ERP seems to encode a level of agency human partner assigns to the observed action. And this provides us now a means to decide whether to adapt to the robot or whether we can expect the human partner to adapt. At last, we are working towards gradually formalizing the approach of human-robot co-adaptation within the context of varying scenarios of human-robot interaction. And here we are drawing upon the preliminary proposed human-robot joint model, which I presented at the end of my presentation. And with this, I thank you very much for your attention, and I'm happy to take any questions.
I have a question. May I ask?
Yeah, Sergey, you can go.
Thank you very much, Stefan. It's a very nice presentation and exciting results. I think it's a very good demonstration of potential of passive BCIs. Still, I have one doubt about practical application because it's rather slow technology. Could you please suggest what do you think about the most realistic application of this technology, some practical scenario, for example, in car driving, how to teach the car, so which kind of events will be actually really good anchors for such teaching by event-related, error-related potential?
Okay, yeah, thank you for the question. So you mentioned about the speed of the approach, that it's likely to be rather slow in the adaptation of the system. Is this what you're referring to, or more the examples?
I mean, what do you think, in which practical situation it will be still useful?
Okay, so what we are currently looking into is factory setups of human-robot interaction, performing a task together, for instance, sorting or assembling objects. That's one example. And here we assume that the human partner may have specific preferences for the policy of the robot in order to work efficiently together. So we are looking into this example of a factory setup of collaborative assembly or sorting. In terms of the autonomous driving, we believe that the human partner or the human driver in that case may have specific preferences for the behavior, decision-making style of the car, which may be at which moment the car is making a lane change, if the car is overtaking or not, or braking. So specific actions taken by the car following a specific decision-making policy. And the human in the loop may have particular preferences for the behavior of the car. And we are looking into the possibility of adapting these policies or switching between different policies by including the measures of error-related potentials. Is that answering the question?
Yeah, thanks.
Yeah.
I have one question about the model convergence. So you mentioned that after the convergence, before the convergence, there were some fluctuations, and would it be possible that after the model converged, it would, so to say, overfit the data, and that the convergence would fluctuate beneath the optimal value? So would you set some threshold after which the model would stop adapting, or?
Okay, yeah, that's an interesting question, because the question is about optimality here. We cannot assume the human preference to follow optimality. So I would keep the learning and the adaptation always open and never stop learning, even if the performance is high, because the human partner in the loop may decide to change strategy, and then we want the system to follow, basically to readapt to the currently changed policy in the human partner.
And would it be possible to do it in real time? So after the system learned, to adopt in real time to participant actions?
So I would not say real time in this case, because it's, as pointed out before, a rather slow process. But we had these cases of, or we saw these cases in the experiment of readaptation. So the human and the robot converged to a specific policy, and then at some point a readaptation took place that led to a temporal performance decrease, and then a reconvergence to another policy. So we saw these cases and deliberately kept this open for being able to happen. Yeah. Is that answering the question?
Yep. But if I may ask one more brief question, is it possible to generalize between subjects to make some kind of general probability of optimal strategy, or the learning shall take place only individually and transfer learning is not possible in this case?
So we focused on the individual subjects here because we wanted to see if the interaction of individual subjects with the system would lead to different kinds of joint policies. And indeed, this was the case, as we saw these two different recurring behaviors of the fixation and the nodding policy. So we kept that open deliberately in order to see are different subjects converging to different joint policies.
Thank you.
Yeah, thanks.
Once again, thank you, Stefan, for great research.
Thank you
for speaking here today. Okay, I'm sorry. The next team is from Spain. It's Technical University of Madrid, and from Russia, it's an Innopolis University. The team is Alexander Pisarchik, Path Kolak, I guess, but you can correct me, I'm sorry. And the topic is MEG studies of voluntary and involuntary visual attention using frequency tagging. With no further introduction, because we need to move quickly, please, Alexander, share the screen and we are ready.
Okay. German philosopher Wilhelm Wundt was the first who suggested at the end of 19th century that there exist two forms of attention.
Alexander, I'm sorry, we do not see your screen.
Oh, sorry. I shared, but maybe it's not the error. Okay, let's share. Okay. Now maybe.
Yes, we can see your desktop.
Yeah.
Make the presentation go full screen.
I don't know where it disappears. Okay. Sorry for this.
That's okay. There is no rush.
Okay. Okay.
Yes, now it's perfect.
Mm-hmm. So, Wilhelm Wundt was the first who suggested at the end of 19th century the existence of two forms of attention, voluntary and involuntary. There is already a surplus amount of terms used in the community that overlap with these two forms of attention, such as endogenous versus exogenous attention, also automatic versus controlled attention, and pull versus push attention. According to Prismetal and his colleagues, voluntary and involuntary attention have different functions and are controlled by distinct mechanisms. They supposed that voluntary attention affects perceptual attention and would affect both accuracy and the reaction time. Whereas involuntary attention deals with the response selection decision and is manifested only in the reaction time experiments. To study these differences, Posner and his colleagues have developed a spatial queuing task. In their method, the subjects are asked to detect or identify a peripheral stimulus. The participants are pre-queued to a possible location of the stimulus beforehand in valid trials. The queue indicates the target location, whereas in the case of invalid trials, the queue indicates a non-target location. Since the participants are not allowed to move their eyes to the queued location, the observed differences in performance between valid and invalid trials reflect differences in attention which are independent on fixation. Later, in 2005, Prismatov et al. Introduced the idea of channel enhancement and channel selection in order to show how the two kinds of attention manifest. Channel enhancement is a process driven by voluntary attention and causes the visual system to gather more information from the attended stimulus than from the unattended stimulus, specified by the information fields. It changes the perceptual representation so that the observers have a clear view of the stimulus they attended to. Other researchers also confirmed that attention to the bias in cue improves the perceptual constant of both the attended and unattended stimulus. In this work, we study voluntary and involuntary attention using multi-stable perception. The phenomenon which where the same stimulus can be perceived in more than one ways. With regards to degree of freedom, the simplest form of multi-stable perception is bistable perception, when two different interpretations of the same stimulus are possible. And the switches between alternative percepts were suggested to be driven by stochastic processes in the brain due to random neurophysiological activity or neuronal adaptation, defined as a slow destabilization of currently dominant perception after being active for a prolonged time or due to both noise and adaptation. Each percept can be seen and it has their presentation in the brain activity. In our experiment, we used magnetoencephalographic research, and the MEG recording was performed in the Technical University of Madrid and the Center for Biomedical Technology. As a stimulus, we use the famous bistable image, Naker cube, which phases were modulated at different frequencies, 6.67 Hz and 8.57 Hz. This is frequencies which is equal to 60 by 9 and 60 by 7 frequencies, and where multiple of integral fractions of the 60 Hz frame rate of computer monitor. Each stimulus was presented during 2 minutes, and the time between presentations was 30 seconds. 90 subjects participated in this experiment. The experiment has 2 parts. In the first part, the subject should be voluntarily perceived each of stimulus. They image imagine that the left or the right face of the cube is in the front. And in the second part, they only observed the cube, looking at the center and the center red point, without any effort for stimulus representation. Then the data were analyzed, and for analyzing, we introduced a new measure of visual brain response, which is defined as the average brain activity in the visual cortex for longer than a transient evoked response time durations that are not phase locked to the stimulus. Traditionally used visual evoked field are time locked to the stimulus, and thus one averages the visual brain activity across trials. Since the observed intermediate phase sleeps in experiments with longer time duration, for example, 2 minutes at unappropriate time moments, averaging across multiple trials is not possible. This response is caused by the stimuli, but the time moments of its part and intermediate phase sleeps are not fixed. Therefore, we applied visual induced response as opposed to visual evoked response. Then we used Morlet-based wavelets. We constructed this a mother wavelet with a 1 Hz central frequency at a 12-second full width at half maximum, and we utilize this to obtain wavelet power time series and second harmonics of the flicker frequencies. Then we measure, we multiplied this wavelet time series to their defining frequencies, and we take the difference between their spectral energies and normalize them to its maximum absolute value. The average power spectrum of visual induced field represented the frequencies of touching frequencies in both phases, and the larger energy we observed and the second harmonics of these frequencies. During voluntary intention, we observed that the energy corresponding to the frequencies applied to the left face of the cube was higher when the subject voluntarily fixed attention to this side of the cube. And in reverse, the larger response we observed in the larger frequency, and the frequency applied to the right face of the cube, and we observe respectively a larger response, brain response. The normalized spectral energy, this is the difference between energies between two at two frequencies corresponding to the second harmonics of the tag frequency, also represent the positive difference when the subject focused to the left-oriented cube, and negative when the attention was focused to the right-oriented cube. So then we characterized the attention performance by the difference between these powers in two voluntary attentive states interpretations of the cube. And this difference we called attentional performance. You can see in this graph that every subjects had different attentional performance. And this we decided that, for example, the subject A and B were more attentive than the subject G and H. So this is the first part of the experiments. In the second part, we, when the subject were asked not fixed any attention, just observed cubes. The switches were also observed, but there were involuntary switches in the energy, in the difference between the power energies. And to detect what side of the cube was interpreted, we applied the criterion when this average difference was higher or lower than the standard deviation. Because this standard deviation can be interpreted as a random stochastic fluctuation, which is not connected with the switching or interpretation of the cube orientation. And then when we applied this criterion, you see that the distribution of these switches was not random. Were not Gaussian, and by applying this criterion, we equalized the energy which was higher than standard deviation S1 and which was lower than the negative standard deviation to 0. And we measured the times during which the attention was fixed to the left-oriented or right-oriented cube interpretation. After that, the power spectrum of the involuntary intentions also looked very similar. We observed also two target frequencies and two second harmonic frequencies, and the middle frequency. This is the sum frequency of target frequency. The distribution of the dominance times were similar, but the larger probability we observed on the left-oriented cube, but the difference was not very high. But the more duration time we observed, the time of switching between switches we observed for right-oriented cube orientation.
Alexander, I'm sorry, you have only 1 minute left to finish your report.
Okay. And then in the plot, you see that the difference, that the average time, dominance time of the sum of right-oriented cube is a linear function. This is anti-correlated with the perception with mu, which is a perception performance. And then by other experiments, we also estimated the brain noise. This is a random prosthesis, and also observed that this average time is also anti-correlated with noise. So we summarize that high attention require a larger neural network to process information and make decisions, and therefore brain noise is stronger. At the same time, stronger noise causes more frequent switching between perception state and more frequent response selection, and hence dominance time becomes shorter. To conclude, in this work, we proposed a novel approach for estimated attention performance and classification of bistable perceived states based on wavelet transformation. And we confirmed that high attention performance is associated with stronger brain noise because larger neural network is involved in information processing. So due to high computation disciplinarity, the development algorithm may be promising for non-invasive real-time BCIs for monitoring and control high attention. Thank you for your attention.
Thank you. Very interesting research. Sadly, we've exceeded our time for talk and question and answers. So if someone from the audience have any question, please put it in the chat and discuss it in the direct messages. Oh, maybe we will have some time at the end. Okay, let's move to the next speaker, Alexander, once again. Thank you very much. That's the team from Lomonosov Moscow State University, which is in Russia. It's Nikolai Sirov, it is Sirov,
Yes.
Anatoly Vasilyev, and Alexander Kaplan. And the topic is the effects of mirror box illusion on sensory motor rhythms during involuntary hand movements. So, Nikolai.
Okay. Do you see my presentation?
Yes.
Okay, thank you.
Make it full screen and
Yeah,
you can go on.
Okay. Hello, dear colleagues. Let me present you results of our work in which we studied effect of mirror box illusion on central EEG rhythms during voluntary and involuntary movements. Let me speak in Russian to make my report more concise. I'm sorry. Okay, thank you.
Yeah, okay. Just in case for all the participants in English language, at the bottom of the Zoom, you have this button with translation, and you can select the English voice of the interpreter for your convenience. Thank you.
Thank you, I'm sorry. Итак, зеркальная терапия —
So,
это...
mirror box illusion or mirror box therapy.
Sorry. I have to put off the sound. Okay. Зеркальная терапия — это реабилитация, предложенная еще в прошлом
treatment
веке
is a method
Рамачандром
of rehabilitation also offered by an Indian neurologist V.S. Ramachandran to treat phantom pain syndrome. This method was used for post-stroke rehabilitation. What is this method? The patient makes a movement with an unaffected limb, and the patient is watching an illusory reflection of the impaired limb in the mirror. Therefore, this visual addition creates an illusion of bimanual motion. Many studies have shown very positive effects of the mirror box therapy to restore motion in the affected limb, which is usually related to a decrease of inhibitory signaling on the damaged hemisphere from the intact hemisphere, and also it is credited to mirror neurons. So the mirror box treatment is a motion observation therapy, but we are using this therapy projecting the movement on the computer display, so it is not related at all to the motion of the body, which is traditionally used in the mirror box illusion. Although, despite of this, authors who have been studying both methods report very positive outcomes of both of these methods on, for instance, the excitatory dynamics of motor and sensory motor areas of the brain. So it has been proven through EEG and also has been used together with transcranial magnetic stimulation. So, until now, we still don't know whether there is a significant difference between computer-assisted mirror box illusion and traditional mirror box illusion. At the same time, a lot of the authors use passive motions for the mirror box therapy, engaging manipulators that help move affected limbs of the participants. So in our experiments, we try to determine whether there is a difference between voluntary or involuntary hand movements during the mirror box illusion. In our experiments, we obtained a 30-channel EEG with increased electrode density in the central area of the skull. In our experiments, the volunteers were asked to make voluntary clenching of the
В других
right hand to make a
условиях
fist
эксперимента эти
while
движения
watching or
проводились
not
непроизвольно
watching the
под действием
mirror
функциональной
illusion. In
электростимуляции.
the
Также
other part of the
было введено
experiment,
дополнительное
this
условие, в котором
movement was
испытуемые
involuntary
совершали
and was achieved through
произвольное
electrical
движение кистью
stimulation.
и
So those were,
наблюдали
there were also
видеотрансляцию этого
participants
движения
who were
на экране
watching,
монитора.
who were making voluntary hand movements
Зеркало
and
в
watching these
эксперименте
movements
устанавливалось
on
между
computer
двумя руками
display.
испытуемого
The
таким
mirror
образом,
was placed
чтобы
between the arms
скрывать
of the participants
левую
to
руку,
induce
а
left
отражение правой
hand
руки оказывалось бы на
flexion
месте скрытой левой
illusion.
руки. Функциональная электростимуляция, ее параметры подбирались
Functional
таким образом,
electric
чтобы вызывать
stimulation parameters
безболезненное
were
сокращение
individually
по
set for
времени
each
и
subject
по
to
амплитуде,
achieve
аналогичное
sufficient
произвольному
and
сжатию
painless
кисти.
functional contraction force.
Для сигналов, отфильтрованных в индивидуально подобранных диапазонах частот, которые были
We
реактивны, то есть чувствительны
constructed
к
sensitive
двигательной
special
задаче,
filters to identify
высчитывались пространственные фильтры, которые максимизировали
sources
разность дисперсии между двумя состояниями, между
of
состоянием двигательной задачи и
sensory
состоянием
motor
покоя,
spatial
когда
image movement,
испытуемых
related
находились в
ARD,
покое
post-movement,
и
beta
никакие
ARC for
движения
pairs
при этом не
of
совершались.
all experimental
Из
conditions.
полученных
So when
пространственных фильтров
arms were idle
отбирались
without
те,
making any movements. Using these spatial
максимальная разница
filters,
которых
we
локализовалась
selected
именно в
the
центральных
filters
отведениях.
with
То есть
maximum
таким образом мы были
difference
нацелены
in
на
the
изучение именно
central
сенсомоторных
recording
реакций.
area. Therefore, we
И
were
после
targeting
применения отобранных пространственных
sensory
фильтров
motor
рассчитывались такие параметры, как
events. Then we
десинхронизация и
calculated
синхронизация исследуемой ритмической активности.
desynchronization and
В
synchronization
результате мы
of the
обнаружили,
investigated
что у
rhythmic
всех испытуемых
activity
после совершения
parameters. As a
движения, будь то
result,
произвольное или
we
непроизвольное,
noticed that
наблюдается четко
whether our
выраженная
subjects made
синхронизация
voluntary
в
or
бета-диапазоне
involuntary
частот. Причем данный
movements,
диапазон был
they showed
смещен
synchronization
в
in
область
the beta
более низких
frequency band,
значений по сравнению с
and the
бета-диапазоном, для
range
которого отмечалась
was shifted
десинхронизация
to
во время движения.
lower
Более
frequency
того,
bands.
локализация данной
Furthermore,
бета-активности
the
была
localization of
смещена
this
более
beta
медиально
activity
и в
was
фронтальную
shifted
область
more
по сравнению
medially
с
and frontally
бета-десинхронизацией, для которой
compared to
продемонстрирована
beta
классическая центральная
desynchronization, for
локализация с
which
четко
we
выраженной
demonstrated classic
латерализацией.
central localization with pronounced
При анализе
lateralization.
влияния зеркальной обратной связи,
We
то есть наблюдения
also
отраженного движения
described
испытуемыми,
the
мы
effects
не обнаружили
of the
значимых
mirror
отличий
feedback,
для
and when describing
десинхронизации
this,
как
we
в μ,
didn't
так и
really
в
detect
бета-диапазоне
any
частот.
significant differences
Ни при
in the mu
произвольном, ни
and
при
beta
непроизвольных движениях
desynchronization ranges
Однако
when it comes to
в
voluntary
условии,
or
когда
involuntary
испытуемые
hand
совершали
movements.
произвольное
But
движение
when
и при этом
the
наблюдали за
participants were
движением,
making a
то есть
voluntary
за
movement
видео,
while
где
watching a
транслировалось их движение,
video
мы обнаружили
feed of this
статистически
movement,
значимое
we
увеличение
discovered a
десинхронизации
statistically
ритмической активности
significant
в бета-диапазоне.
desynchronization in the
При
beta
анализе
range.
обнаруженной нами
When
бета-синхронизации после
analyzing
движения,
beta
мы
synchronization after the
видели,
movement,
что
we
этот параметр значимо
found
снижается при
that this
введении
parameter
зеркальной
is
обратной связи.
significantly
Причем
reduced when we
это
provide
наблюдается и
mirror
для
feedback.
произвольных
And
движений,
this is
и для
both true
движений,
for
вызываемых
voluntary
функциональной
and
электростимуляцией.
involuntary
Причем
motions
различие
caused
наблюдается
by
как в контра, так и в
functional
ипсилатеральных полушариях.
electric
В то время как
stimulation,
для
and
условия
this holds
с
true both for
наблюдением
contra
за
and
движениями, такие различия
ipsilateral
наблюдаются только
hemispheres.
для контралатерального
Differences in
полушария.
post-movement beta areas are observed only in the contralateral hemisphere.
Таким образом, мы
Therefore,
на основании наших полученных результатов можем предложить
based on our
такое
results,
явление, как бета-синхронизация в качестве
we noticed
нового
beta
инструмента оценки
synchronization
эффективности развития зеркальной
could be
иллюзии,
used
что может
as a
помочь
new interest to
в
develop
будущем контролировать эффективность
mirror
иллюзий в процессе
illusion, which will in turn
реабилитации
help us
после инсульта.
to control
В то
the
же время мы
effectiveness of the
обнаружили
mirror box illusion
отсутствие
in post-stroke rehabilitation. At the
различий
same
в
time,
эффекте
we
на
noticed
сенсомоторные
a
ритмы
lack of difference
при зеркальной
when
иллюзии
it comes
при
to
произвольных и при
sensory
непроизвольных
motor
движениях.
rhythms when
Это
subjects
на этом
perform
основании
voluntary
предложить
or
такой
involuntary
метод, как функциональная
movements.
электростимуляция в
Therefore, we
качестве
think that
инструмента, который может
functional
быть внедрен
electrical stimulation
в
can be
терапию
used as a tool,
посредством
as a
зеркальной
therapeutical
иллюзии. То
tool,
есть наши результаты дают основание предложить функциональную
Together with the mirror
электростимуляцию
box illusion,
для внедрения
our analysis
в
shows that
метод
functional
зеркальной терапии движения. И это
electrical
позволит сделать
stimulation can
зеркальную
be
терапию
used
доступной
alongside
для,
mirror
например,
box
пациентов
therapy,
с
which would make mirror
двусторонним
box
параличом
therapy
конечностей.
available to patients who
Спасибо за внимание.
have bilateral limb paralysis.
Nikolai, thank you very much for this research and your work and work of your team. Do we have any question for Nikolai regarding this research? I must say that that topic is quite interesting because it's not very popular from my point of view, the direction for the research. Do you have any additional plans or how you can improve all the methods?
Yeah, of course. As I want to say that better synchronization, maybe such activity reflects the inhibition process of primal motor cortex, and we're planning to check this hypothesis by TMS methods, transcranial magnetic stimulation.
Oh, yeah,
yes.
yeah. Okay, so if no more questions, we are moving quickly to the next speaker. Thank you once again, Nikolai.
Thank you very much.
And it's also quite a big team. The next topic is EEG-based silent speech recognition. The importance of this field is, I think, really interesting regarding all the smart devices which are coming to our homes and our lives. And I'll announce the team. It's Alexandra Bernadotte, it's Ivan Menshikov, Nikolai Serov, once again, Lev Yakovlev, Anastasia Bagrova, Piotr Rikunov, Alexander Kaplan, Sergei Markov, and this organization is Sberbank, Sber Devices Division. It's Moscow State University. And it's, I'm sorry. Yes, and it's mathematical theory and intelligence systems from Moscow also. So, Alexandra, if you're ready, please start.
Hi, my talk is called EEG-based silent speech recognition. And actually, we're a team from Moscow State University and from Sber, engaged in R&D projects. The aim of this work was to establish whether it is possible to recognize silent speech. This has been said many times here, but to be precise, I would like to give a definition. The silent speech is words that are pronounced without passing ear through the glottis. As mentioned many times here, the speech activates the motor cortex and the area of the brain responsible for the speech. The research is directly related to the brain-computer interfaces, with the purpose to restore lost function for paralyzed patients with speaking disabilities. And also, non-invasive brain-computer interface has also potential to expand human capabilities in daily life. It has become a real challenge for us to collect the data set in the current epidemiological situation. However, we managed to obtain EEG data from 77 people. The age of the subjects ranged from 18 to 46 years old, with a mean age of 29. We used 40 and 60 overlap channels of the classical EEG. The EEG cap had 42 or 62 wet electrodes. We used system 1010, including 2 grounds. The EEG signals were sampled at 500 Hz. The experimental session lasted 20 minutes when words appeared on the screen, and the subject has asked to look at the screen and read the words silently without making any sounds. And the subject was shown 4 words on the screen for 3 seconds each, for 30 times each, with a pause between words for 2 seconds when the screen was empty. First, for pre-processing, we used independent component analysis and fast Fourier transform filtering to remove cardio, myo, and ocular artifacts to denoise the EEG data. We also used notch filter to remove the power line noise. Each channels of EEG data was presented as 40, 64 at 24 spectrogram size of spectrum. Thus we represented data of 40 channels as 40 at 6 at 20 and 60 channels as 60 at 64 at 24 per sample. The neural network we call 3D residual net. And it was inspired by ResNet and formed from 80 residual blocks and 4 fully connected layers. The experimental with 3D convolution recurrent network, we added 5 additional fast Fourier transform frequently mapped layers on the top of each EEG channel. The residual blocks consist of 3D convolutional layer with 3 cubic kernel, cubic padding, and cubic stride with following Rayleigh normalization and normalization. Each 3 blocks were passing on output tensor to concatenate with the input over 1 block forward, producing aggregation from nonlinear and linear input. We also performed 30% dropout every 3 blocks. For each data, we used 40% of the data as training set, remaining 10% as validation set, and rest 10% as test set. We demonstrate robustness of the system and can report that we achieved 84.6% median watt accuracy level for classification of each 2 watts and 65.3% median watt accuracy level for classification of 4 watts on intact data. We also have tested 5D convolutional recurrent network, adding 5 additional fast Fourier transform frequency map layer on top of each EEG channel with even better results, but with much higher requirements. Here we are.
Yes, that's the end of the talk, right? I got the internet connection. It just a bit dropped.
Oh.
Alexandra, that's the end, right?
Well, it is the end of the talk, but not the study.
Yeah, sure. I just asked for a talk because I've missed the few seconds at the end of your talk. Okay, if we have any question, please, as always, just speak. Yeah, Sergey.
Yeah. Did you estimated the possible contribution of eye movement or maybe muscle artifacts? Because it's especially in your set of words could induce some eye movements.
Right. Thank you, Sergey. It's actually a very smart question because we actually did. We have used classical filtering for higher artifacts and line artifacts as well. But actually, we found we're quite promising not to use those kind of filters in the future study. Because the strongest part of our study, as I see, is from my point of view, is just to get to collect the huge data set. And we're actually progressing quite nicely in this part of study. Because to be honest, we're actually thinking, well, it's a part of the project. We are actually creating a brain-computer interface And we actually would like to avoid any kind of special pre-processing, which we cannot implant in real device. So we actually try to avoid eye movement, filtering, or other kind of noise filtering. Because the hypothesis behind this intention is just we can avoid needs to prepare data if we collect the huge database.
Actually, what I meant is not that you need some special kind of filtering, but it's probably by using powerful neural networks that you will get these artifacts even after very strong filtering. As last year, Vadim Nikulin at a roundtable, he mentioned some study when people made their best to remove all possible artifacts, and because they
still here, right? Correct. And the same
generalized
result, right?
Get very small features from these artifacts, and the problem is that it's possible that it will not go well in different kinds of works. So maybe one possible solution for now to deal with this, actually two solutions. First, to study what kinds of features are used by the network, and the second one is just to use different words. And it's strongly different, such that we probably will not make will not lead to eye movements. Yes. So in comparison.
Well, we cannot actually avoid eye movement in the real life. So we decided just avoid them in our pre-processing. But you're absolutely right. You're absolutely correct when you're telling us about still remaining artifacts, even if we apply some kind of filtering for eye movement artifacts and other notch filters. Notch filters is actually working very well, but eye moving artifacts, and not really, because we are losing a lot of features there on this segment of eye moving artifacts. And we decided, as you said, just to use quite powerful network, a neural network, just to avoid this needs for pre-processing. And talking about another words, right? Well, to be honest, we actually used 4 words nowadays, and now we're switching for 8 words. And the words we are working on now are вверх, вниз, вперед, назад. There are 4 words where 3 of them are very close soundly, and it was made on purpose because we actually wanted to be sure that we can distinguish words from the same sound cluster. And actually it looks quite well. Not really huge, not really impressive results with words when we compare them to other people like Gautam, for example, with their really high score for task of classification, word classification of silent speech. And I actually think that the reason for our kind of fail here was exactly that part of study, the choice of the word, because 3 of them were really close, but we are willing to fight and try to just to classify them correctly, keeping in mind that we still have this amazing possibility to collect the huge data set, and probably, yeah. Well, the short answer here is no, we are not willing to use special words, because the challenge here in our study is to be able to classify very close words.
Thanks.
Thank you.
Yes, thank you very much for the talk and for the questions. Okay, the last speaker is Giovanni Mirabella. He's from University of Brescia and also from IRCCS Neuromed, Italy. And sadly, Giovanni informed us a few days ago that he won't be able to speak today himself, but he's recorded video yesterday and sent us. And right now, our colleagues from organizing committee will start his report. Okay, we can go.
So, first of all, I would like to thank the organizers for inviting me and all the people to attend the symposium and my talk at these difficult times. I must say that I'm not a brain-machine interface person. However, thanks to the collaboration with Professor Lebedev, we developed the following proposal. Brain-machine interfaces must decode inhibitory-controlled signal to produce naturalistic motor behaviors. And we will try to realize this proposal concretely. For starting, I would like to say that I would not record myself speaking because the video would be too heavy, but I put a recent picture of myself here in Trieste. I'm sure that all listeners know very well what the brain-machine interface is. Thus, I will provide the description, but my description is just functional to the message I would like to convey. Well, so brain-machine interfaces allow to establish direct communication between brain regions and assistive appliances, such as an artificial body part or a computer. This is an example of brain-machine interfaces for enabling a monkey to control a robotic arm that reaches and grasps objects with multiple sensory feedback loops. The crucial point here is that neural ensemble activity is recorded in multiple brain areas, sensory motor areas, and decoded by mathematical algorithms to generate commands that control the robotic arm. The monkey then has both visual and here you see, and tactile, here you have it in red, feedback that help it to improve the accuracy of the reaching and grasping movements. Usually, the brain-machine interfaces, experimental brain-machine interfaces, must be trained to perform a task, and this process has two phases. First, there is a training period before the brain-machine interface's usage. Need to select to set the decoder initial parameters, and the second part is the brain-machine control, when brain-machine interface takes control of the situation. And basically, during the training, neural activity is recorded while the subject either perform the task, for instance, overtly movements, or passively observe the task, observe movements of a computer cursor. In the second phase, on the basis of this previous recording, the relationship is evaluated between the neural patterns and cinematic parameters of interest, and the decoder is set to predict the cinematics from neural signals. Using this approach, some great success have been obtained, such as this picture is showing a lady who is able to control a robotic hand in order to drink some Coke. However, subject must undergo long training processes to gain control of his or her robotic limb, and movements are not very naturalistic. You might wonder why this is the case. The possible explanation is that subjects are usually asked to perform tasks in which a key ingredient movement is always neglected. And the key ingredient of movement which is neglected is inhibitory control. You might wonder, what is inhibitory control as the key ingredient of movement control? Well, in the last decade, it became clearer that our goal-directed behavior relies both on action preparation and action inhibition, and this is because we need to select at each instant. We need to select and perform actions whenever they are more opportune, that is, whenever the cost intrinsically associated with them are lower than their benefit. So let's take the example of this guy who decided to surf in a sea crowded with sharks. At some moment, consciously or unconsciously, his nervous system must have performed some evaluation that allow him to answer this basic question. Is it worth it yourself when sharks are around? And if it's some pros, you have some adrenaline and fun, but you can have some cons, the possibility of losing a leg or arm or life. But importantly, whatever the outcome of this decision process, as we live in an unpredictable world, decision bear a certain degree of uncertainty, as you show this case of a surfer who was about to start the race when suddenly he perceived the presence of a shark, and of course he had to change his plans, as you can see. And I will tell you that this is not a fake news, it's something really happened, and he will be able to save himself. Thus, many or all decisions bear a certain degree of uncertainty about the final outcome of an action, and thus we develop the ability to cancel pending actions. The quantitative study of the suppression of ongoing action has been successful study, so this kind of action has been successfully studied exploiting the stop signal task. The stop signal task probes a subject's ability to withhold a planned movement triggered by a go signal when an infrequent stop signal is presented. And here we will quickly describe the implementation of the task I have done, but the general concept is always almost the same. Basically, in the stop signal task, two kinds of trials are randomly intermixed between each other. You have non-stop trials, and in non-stop trials, subjects are sat in front of a touchscreen, a central stimulus appears, they have to touch it as soon as possible, then after a variable time, the central stimulus disappears and appears stimulus in the periphery, and the subject has to touch the peripheral target as soon as possible. Randomly dispersed among the non-stop trials, there are the stop trials that has got the same structure until the delivery of the go signal, but then during the reaction time, that is before the subject has detached his index finger from the central position, the central stimulus reappears and the subject is instructed to withhold his movement, who he was preparing before. And importantly, using this task, it could be estimated using a model developed by Logan and colleagues, the duration of the stop signal, which is the stop signal reaction time. An example of how to exploit this task comes from the following study of my equipe. So we recorded the activity from subdural electrodes placed over the lateral surface of frontotemporal lobes of 5 pharmacoresistant epileptic patients performing the stop task, and here you have an example of the localization of each electrode of the grid, and different color corresponds to different Brodmann areas. I don't have time to explain the analysis. I want to say that for each electrode, we assess the presence of an event-related potential, which was specifically linked to reactive inhibitory control in successful stop signal trials. And actually, as you might notice, on the x-axis you have time, and here you have the amplitude of the event-related potential. On the y-axis, here you have that 0 is the time in which the stop signal was presented, and the dotted pink purple line is the end of the stop signal reaction time. What you can see is that we have a stop event related complex which actually started to increase, to be significant, in other words, significantly different from the baseline, which is 0, before about 150 milliseconds before the end of the stop signal reaction time, as indicated by these gray bars, which indicates when the stop signal ERP is significantly different from the baseline. And being as the stop event related potential starts to be significantly different before the end of the stop signal reaction time, that is, before the behavioral estimate of the stop signal, it indicates that this ERP could be causally related with the inhibitory process. Please, if you are interested in the methodology, write me, you have my email. So basically what we tried to do was to understand how was the distribution of average stop ERP across all patients. And here you have the example of the distribution of the stop ERP across the electrodes of the grade 1 patients. We did not select any electrode a priori. This is very important. And what you can see here, that you have a very large deflection in different electrodes, even though we have that these deflections, the stop ERP, were had a larger amplitude over BA4, BA6, and BA9, close to BA6 actually. Thus, we wanted to get the distribution of the average stop ERP across all patients without selecting electrodes a priori, and thus we decided to assess the distribution of the stop event-related potential with the largest amplitude. And the rationale was, in this case, that the largest stop event-related potential should have the biggest impact. As you can see from this histogram, the most of them were located either in M1, VA6, or VA9, while in the other broadband areas never had more than 2 channels with large enough average ERP. So basically, what we found in this study is that when the movement is successfully cancelled, an ERP complex is selectively expressed in M1, BA6, BA9 before the end of the stop signal reaction time. And very importantly, this and other studies suggest that using an appropriate task, it's possible to extract neural activity related to both movement execution and cancellation. Thus, in principle, training a brain-machine interface to decode inhibitory signals would allow reproducing goal-directed movements in a more naturalistic way. But of course, there are several different challenges. Where to extract appropriate signals from the extended networks observing inhibition? Well, in fact, performance of actions and their suppression do not seem to be specified by independent set of brain regions. Instead, acting and stopping are functions emerging from specific interaction between largely overlapping cortical and subcortical brain regions whose activity is intimately linked to the evaluation of pros and cons of an action. How could the inhibitory network concretely work? In this slide, I will propose a new model. So I will go quickly, and then you can send me questions, of course. Well, what I suggest is that motor cortices, where the motor plans form, can send an efferent copy simultaneously to both the striatum and the subthalamic nucleus via the direct and hyperdirect pathway, respectively. These basal ganglia actually have an opposite effect on globus pallidus pars interna, which is the output station of the basal ganglia related to upper limb movements. The globus pallidus pars interna inhibits the ventral anterior and ventrolateral nuclei of thalamus, whose activity typically precedes movement onset. Thus, when the GPI is very active, it decreases the activity in the thalamic nucleus, leading to the suppression of the movement, or if the movement actually, the GPI is not active so strongly, then the movement is executed. Importantly, the state of activation of GPI will be determined by the race between the signals come from the striatum, which tends to inhibit it, and the signals coming from the subthalamic nucleus, which tend to excite it. If the subthalamus wins the race, then the movement is suppressed, otherwise it's performed. The output from the subthalamic nucleus and the striatum will be determined by the evaluation of the motor plan with respect to the information about the current context and the past memory coming from several different regions in the brain, specifically from the prefrontal, limbic, and parietal regions. That's why many regions can be involved according to the context, according to the kind of the task or the stop signal task which is asked to perform. And this hypothetical security race between the execution and the inhibition of a movement determines whether a movement will be performed or not. Thus, where to record from? Well, even though it's purely speculative, a plausible solution is to record simultaneously from the sensory motor cortex and the globus pallidus pars interna, because, as you can remember, this will allow you to have enough information for determine the behavior of the subject. Thus, in conclusion, the development of inhibitory control brain-machine interfaces might represent a significant step toward reaching naturalistic control of motor behaviors. Furthermore, it could also represent a new frontier from the cure of neurological disorder characterized by pure urge control. Thanks a lot for your attention. So,
thank you, Giovanni. We know that you cannot hear us, but still, I think that we'll send you a hello through some other sources. Okay, that's done for today, for this session, and a few hours have passed really quickly. I'm surprised that we already finished, and we did it on time, which is extremely important for organizing committee. So it's a great job, everyone. Thank you. And I just have two messages, which I think you find very interesting for you. The first one is that right now we'll have a break, but you can enjoy all the poster sessions. So please go and see all the posters using this amazing interactive VR room. Also, an hour, I guess, no, in half an hour, there will be an interactive exhibition also is going with interactive speakers, which is be really cool for you also to go to enjoy all that in 3D and to speak with the exhibitors. Just in half an hour, there will be a lot of participants here. And please remember that in 2 hours, there will be the third part of this symposium, which will be directed by the Brandon Ellison from University of California, San Diego, USA. And it will be available on this exact link. So just go, do whatever you want at the poster session, at the exhibition, and after that, come here again to see and hear all the participants of the third part of the symposium. So, such a great honor to be with you all that time. And I wish you all the very best. And once again, thanks for BCI Samara to hosting all that. This is an amazing event. Bye-bye.
Hello, Brian Jenkins here. Hello,
Hello.
Hello. Can you hear me now?
Yes.
Just, I'm not sure that I correctly use. So I'm Yuri Ivanenko. My talk actually is at the end. I should just click condividere. It's in Italian. Sorry.
No problem.
I need to click this green button, no, to start my
Yeah,
talk.
the share screen.
Is this all?
To me, it says share screen.
Yeah.
That green button.
I think, okay, so no questions.
That should work.
So you can hear me. So my resolution of my video maybe is not very high, but it's my web camera.
That's okay. We do our best.
Okay, I'm ready.
Everyone knows it is a virtual conference, so.
Yeah. Okay, let's wait a little bit.
Yeah, so I spoke with Ilya, and we have 12 speakers. So he said we might let the session last a half hour longer, 30 minutes later, just to make some time for the speakers. So that
I see. Yeah.
Well,
I was busy this morning, but now it's in Italy it's almost 3:30, so it's afternoon. So
yeah, everybody is in a different time zone.
Yeah, I know. Yeah,
that's part of the fun, I think.
Yeah.
This event.
You are exactly where now?
California time.
So I think the difference is maybe 9 hours between Italy.
Yes.
Yeah, I think 9 hours.
Right
so
now
it's morning for you, no? It's something like
morning, almost 7:30.
It's 7:30. Mamma mia.
Yeah. Oh, it's not so bad at all.
Okay.
I will say this in my talk also, that there were many conferences where people had to come to the United States, so it is fair.
Yeah. Okay. There is nobody else?
Nobody yet. We still have some time.
Yeah, 5 minutes, yeah. Okay.
If they don't come soon, then we have a shorter session.
I don't know how it's in US, but in Italy it's very typical 10-15 minutes of delay of the onset of of almost. No, yes, I know. In US maybe you don't have such a rule. In Italy it's almost a rule. People do not start exactly, so there is always a.
Well, that is the challenge that we have with 12 speakers. So if we have 150 minutes, then with 12 speakers, everyone speaks for about 12 minutes, which is not very long.
Yeah.
But I see Ilya is here, so he will speak soon.
Okay.
Hello, everyone. Can you hear me?
Hello.
Hi, it's Ilya.
speaking. Brandon, we have now actually 4 people meeting.
Right.
Andrei Kuznetsov or Daria Kuznetsova. Also Artur Bistenirov and Yelizaveta Okorokova. I will monitor them, and once they are in Zoom, I will promote them as the co-hosts. And on time, we can start with your talk. And the next one would be Nastya Belinskaya. And if Hassan and Andrei, or Daria, who are the number 3 and number 4 is missing, just go ahead and call Pavel Bobrov, okay?
But I cannot hear you so well. Can you turn up?
Probably. So it is okay. So you can start. Can you hear me now?
Okay, I should start.
Yeah, you should start in 3 minutes. And if someone is missing, I will be adding people who are coming to as a co-host, so they could share their screens and all this stuff. And if someone is still missing, once there is their time to deliver the speech, you can just transfer the queue to the next one and delete. So no worries. Okay. So
okay. Yes. We will start in about 3 minutes.
Yeah. Thank you very much.
Thanks. Okay, so if you are still joining us, thank you for being here. And part 3 will begin very soon, about a minute or so. And we have a few changes to the speaker order, and we will get to that later. So I will still be the first speaker, which is in the schedule, and then we will proceed from there. And one quick note is that we have a total of 12 speakers who are scheduled. So we may go a little bit over. I was just speaking with Ilya about this, that we may go over the allotted time just to allow people enough time to speak. It will be difficult for us to stay on schedule if people take more than, say, 12 or 13 minutes for a talk with a little time for questions. And of course, there is also opportunity for discussion later on in the neurobar or elsewhere. Okay, so I guess it is about time to begin. So as I mentioned, I'm responsible for the first talk, and the talk title is about P300 BCIs for patients with disorders of consciousness. And so one of the defining features of a BCI system is that it is a closed loop system. You acquire information from the brain, and as this shows, it might be information from the top of the head, or it might be information from elsewhere. And then you have to process that information, and then that information is sent to a device command. And this was defined in Walpaw et al. 2002, which is one of the most heavily cited article in the field. Everybody knows this one. And if you haven't read it, then you certainly should. And 10 years later, Jonathan Walpaw and Elizabeth Winter Walpaw updated this approach with their book chapter. And they defined different ways that you could use BCIs, different types of applications. So the same loop is there. You're still getting information from the brain, processing that information, and then sending that information to some kind of device. But the goal might be, for example, to replace a loss function, which was pretty well studied as of then. There were relatively many papers, or to restore function to help people become healthier. And I'll be talking about this largely shortly. Turning off the video, just a second. There we go. Apologize for that. So on to the next slide. So what I'll be talking about are different applications of BCIs and BCI-like systems for DOC. For first, assessment. So you can use these tools to assess the level of remaining function that these patients have. Communication, that is, you can establish at least basic yes or no communication with them. And this was presented somewhat yesterday in the talk by Dr. Guger. And so I'll talk more today about some newer directions, which are first prediction, that is, can you predict that patient's clinical outcome? And even in the future, the possibility of rehabilitation, that is, could you help to restore lost function to some of these patients? This is an approach to describing DOC from 2005, and there are many ways to look at this in terms of wakefulness and awareness. But DOC, or disorder of consciousness, includes the minimally conscious state, which is in green, the vegetative state, which is in purple, and coma, which is in red. So if the patient is diagnosed with coma and really does have coma, that person should not be able to respond to stimuli or choose to pay attention to the left wrist or the right wrist or a high tone or a low tone or anything like that. Whereas in a vegetative state, or what's even more close to awareness is the minimally conscious state, the patients may have wakefulness. In other words, they have some awareness of what's going on around them, but they can't respond. And potentially, if you're using EEG measures or other tools to assess their awareness, you might be able to get information that other methods cannot determine. This is a nice illustration of the approach that we used, and it shows that the person has a vibrating tactor on the wrist. So in addition to an EEG cap, you put something like a bracelet on the wrist, and it vibrates periodically to provide vibrotactile stimuli or touch stimuli. So if you put one of these on each wrist, you have a paradigm with two vibrating tactors, and you can ask the patient to silently count stimuli on either the left wrist or the right wrist. And this is essentially a P300 BCI paradigm. That is, the target stimulus, such as a stimulus on the left wrist, is going to produce a good P300 and related ERPs, and a non-target stimulus is not, assuming the person is able to focus on the task by counting stimuli on the left wrist or the right wrist. And this is the actual system that we used, and as I mentioned, Dr. Guger, I mentioned Dr. Guger was presenting some of this earlier. All right, so now I'm on a later slide. Let me go back there. So this was the system we used, and here I hope this is on the slide. Just a moment, please. I'm sorry to see that people lost me briefly. I will continue for now, and as necessary, I can go back. Since we have limited time, I'm hesitant to start over. But I was presenting an overview of different types of VOC, and what this study was showing involved outcome prediction. So the purpose here was to help doctors predict the outcomes of patients 6 months later. And this is an important issue. If you can predict patients' outcomes, that could help you to direct the best therapies to them. You might be able to inform patients' families about what to expect and such. And so you see the top patient, UWS1, attained very good accuracy in 2 different vibrotactile paradigms. And in the right 2 columns, you can see the patient later improved. You can see the patient later improved with an improved outcome in terms of being in the minimally conscious state and the score of the 6 months CRS-R. This also is notable in UWS7 and UWS9. And you also see that in other patients who had a different outcome, the accuracy was not so good. So patients who were later deceased or did not improve did not do so well in the vibrotactile task. So what this indicates is that if a patient can perform well in a P300 BCI task, specifically a vibrotactile task, not a visual task, for example, then that indicates that the patient is likely to have an improved clinical outcome as of 6 months later. And of course, this raises the question of could you extend this for 1 year or longer times? And that's certainly something to explore. And also, could you provide more detailed information? You know, is there a way you could direct medications or other treatments more effectively? And this is, we don't know this from the current paper, but that's an issue for future research. In another paper, which was out earlier this year, I thought it would be interesting to present some results with some atypical ERPs or event-related potentials. So since I like ERPs and P300s, that's how I'm approaching the BCI challenge, I thought that would be noteworthy. And so remember that many of these patients have severe brain damage. In this case, it was traumatic brain injury. And so they may produce ERPs that are not typical. They're not what you would expect from healthy people in laboratories or even most settings. For example, in the top row, you can see that in the first run, you don't really see anything like a typical P300 complex. The green line reflects target response, and the blue line reflects non-targets. The green shaded areas are statistically significant differences between the two. And what stands out is there's nothing that looks like a P3 or an N2 nor other healthy components of a P300 complex. In the best run, you can see that on the right side in C4, you see something that looks like that, and it's fairly robust and usable, but it's still not typical. The distribution from left to right doesn't look healthy. And so what this means is that the person, at least in the best run, was making an effort to perform the task, but due to serious brain damage, did not produce a typical waveform. And this is part of the challenge with this patient group, is how to adapt to these types of waveforms and determine how many trials you need to present and how many days and such to get reliable results. In this case, we perform this BCI-like task over 10 separate sessions in 10 days. And we found that it was useful for tracking patients' activity in addition to clinical scales, and might be useful for other things later, which I'll get to in a couple slides. This is an example of atypical ERPs. You can see that this is, in my opinion, the worst ERP recording from any of the patients. So patient 9, even in the best run, you don't see what looks like a healthy P300 complex. And in this case, it does not seem the patient was reliably trying to focus on the task or indicate conscious awareness. And this was another person with a traumatic brain injury in the teens. So one major issue that comes up in pretty much all BCI research, but this one as well, is the need for more interdisciplinary collaboration across different domains. Global BCI initiatives, so this event is in Russia, this is great. And it's also fair. There have been many conferences in the EU and in the US where people from Europe or from Russia had to travel very far. There are a lot of BCI conferences going on in China. It's not out of the question we'll have one in the Chinese time zone. So these kinds of things are good and can help encourage research. You know what can encourage research even more is money. So funding sources are always welcome. And this was one theoretical connection that I thought I would mention. There is a nice poster at this conference. And what it was doing is reviewing different ways you could, it was reviewing different ways that you could interpret disorders of consciousness. Not much I can do at the moment, I'm afraid. So although my talk today was about clinical assessment, we had other work such as this poster that is of note. Also, I wanted to say that we should avoid bullshit BCIs. These are bad. You should correctly represent what your system does. And my last few slides, I just wanted to go through quickly to get them in there for the recording. So there are a lot of issues. This is not about P300 BCIs or disorders of consciousness, but broader challenges that we have in terms of the BCI community, and especially opportunities for new people to learn. I also wanted to make a nice plug for the BCI Society. So you may have heard that the virtual BCI Society conference will come soon, and some other developments. And I wanted to conclude by thanking the conference organizers for inviting me. And there are some links here, or one link here, and an email with some more information. And we have a little time for questions, and I will stop sharing. And if we don't have a lot of questions, we'll move to the next speaker.
Can I ask a question?
Yes, please.
Hello, thanks very much for your talk. And I'm just currently writing a dissertation in humanities disciplines. And I'm wondering if there are any particular issues or challenges that can be addressed outside of technical disciplines.
Oh, very much so. For example, I had to hide one of my slides just for time, but it should be in the recorded version, or I can email it to you. And what that slide presented were some ethical issues. So ethicists are certainly welcome, even if they don't have a technical background. Also, there are many people involved in healthcare, nurses and therapists, who have more of a medical background. And we also have a note from Info BCI Samara to everyone. Please turn on your video to improve the symposium. So I will follow that instruction. So as far as other non-technical disciplines, another option, there is a lot of interest in design. That is, what is the best way to make a cap so that in this case it's comfortable for long-term use, it looks professional even though the patient typically can't see it, other people can, and also design of the system. How do you present stimuli? In this case, of course, you're working with non-visual stimuli, but with other visual BCIs, there's a lot of work with entertainment and gaming. There is a need for good backgrounds, good art, characters, avatars. So these are some non-technical directions with BCI.
Can I just have a quick follow-up?
Sure.
If the time allows. What do you think about opening up the research of BCI with with just individual like software developers who buying the headsets and just tinkering things? And do you see research outside the laboratories as a good opportunity for just for kind of building a community of builders, and also just having a potential breakthroughs in the individual researches?
No, this is developing quite rapidly, and this was something in my slide about BCI infrastructure that I didn't have time to discuss further. There are a lot of systems and tools now, including open source software platforms, that are designed to make it easy for developers and other individuals who are not necessarily part of a university or hospital or research lab. So if you look online, and there are a few companies here as exhibitors, there are systems you can buy for on the scale of hundreds of US dollars or euros or around there. And you can collect EEG, other signals, you can build different types of BCIs. There are a lot of ways you can download data and signal processing methods. There's a paper, Brunner et al. 2013, even though it's older, it presents some of the different open access platforms. So it's getting easier and easier to do that. Unfortunately, with COVID, these in-person demonstrations and hackathons, which I thought were very helpful, are not feasible. And so that, I think, is a blow. It's unfortunate because this was a great way to introduce new students to the field. Hopefully we can do them again soon.
Yeah, thank you very much.
Thank you. Okay, I think in the interest of time, I'll move on to the next speaker. And our next speaker is Anastasia Belinskaya. And I see that she is here and we can see her video. Hello. So go ahead.
Do you see my screen?
Yes.
Yes. So thanks a lot for giving the opportunity to speak about our neurofeedback studies here. Actually, we changed the topics of our speech today. And now I want to tell you about our recent findings on the impact of feedback delay on training of the parental alpha rhythm. Most likely everyone knows, but I just quickly remind you, neurofeedback is any real-time closed-loop system that allows participants to perceive and control their brain activity. In general, we can decompose this paradigm in 3 steps: data acquisition, signal processing and extraction of target signal, and feedback presentation. And there are a lot of neurofeedback targets, for example, alpha rhythm, beta rhythm, mu rhythm, or some rhythm variation. This technology has been used for about 15 years, and there are a lot of clinical and scientific application of this, and the number of publications in this topic is growing every year. But there is a problem. The effectiveness of this paradigm is still discussed. There are different arguments for an efficacy and efficacy neurofeedback position. For example, the inefficacy argument is small number of placebo-controlled double-blind studies confirming the efficacy of neurofeedback, or low sustainability of the neurofeedback effects, or the large intersubject variability. It means that there is a subject who call non-responders for neurofeedback treatment. And There's argument for efficacy, like animal response to AG neurofeedback but don't respond for placebo, or neurofeedback is an accepted treatment for ADHD and show efficacy equivalent to stimulant medication. But what's the problem with neurofeedback? We have a hypothesis. Our hypothesis is the problem now is in feedback specificity. We know from classical learning theories that the specific feedback for our action can help us to learn faster. There are several factors of feedback specificity. For example, spatial specificity, which electrodes we use for feedback generation, or frequency specificity, which band we choose for training. But now we want to focus on time specificity. Why we think that it's important? One point of view is that the neurofeedback is a reinforcement learning process. In typical reinforcement learning system, delay rewards play a crucial role. In the low picture, you can see the green spoon experiment where 30 seconds delay of knowledge of result greatly reduce the efficacy of learning a motor task. Knowledge of results here, it's just verbal feedback about your movement. And on the right, you can see the modern study showing that BCI delays affect subject sense of agency. Here you can see that the group with greater delay have the smaller sense of agency. But why we think that neurofeedback paradigm have problem with delay? The full NFB circle contains different sources of delay. For example, occasion, filtering, visualization. And as you know, the major source is filtering. Neurofeedback is dominantly based on narrow band rhythm in spontaneous power. And because it's a real-time process, we have to use casual filtering for consistently introduce a delay around 200 or 300 milliseconds. On the left, you can see animation, how it happens. And on the right, you can see that it means that in every current neurofeedback system now, we reinforce our subject only in the downslope or even in the end of activation, which we want to train. Why do we think that it's important to reinforce in the upslope of the burst? Because when we train to boost, for example, average alpha band power, we could change spindle amplitude or spindle duration or number of spindles per minute. But our previous results show that initial trait of alpha burst is the primary changing parameter of alpha band activity. And this may mean that the beginning of the burst is the event that we must reinforce. How could we fix the delay problem in neurofeedback system? My colleagues Nikolai Smetanin developed a novel signal processing method for low latency band power estimation, allowed to flexibly and explicitly control feedback latency. And it's helped us to reduce latency in half with the same accuracy. But to test the hypothesis about the effect of the delay, we conducted an experiment. So we split our participants 4 equal groups, 10 people in each with different neurofeedback delay settings. First of all, it's a feedback 0 condition. It means that these participants have system-based latency delay. It's not a real 0 latency, it's just a system-based delay. The second group with a 250 millisecond artificial delay, which we added for system-based latency. And the third group is 500 millisecond delay added. And the last one, of course, it's mock neurofeedback, where the feedback was generated from the EEG data from different participants. Our training was about half an hour, and feedback feedback looks like a circle, the border of which was even with the positive feedback and shrunk towards to the center with the negative. Our results. First, we quantified the changes in alpha magnitude using a classical linear regression model. And you can see in the mock feedback condition, the learning curve is noticeably flatter compared to the feedback condition. However, in all 4 groups, we found significant positive correlation between mean alpha right magnitude and log sequence number. But as I already said, we can divide the magnitude value into 3 morphological parameters: duration, amplitude, and initial rate. For detailed analysis, we quantify all these metrics: magnitude, spindle, initial rate, duration, and amplitude, and we perform the adaptive Neyman test. This test considers the projection of the difference in t-statistic onto a set of orthogonal basis function. So briefly, this approach takes into account the fact that the observed samples belong to a smooth curve. So you can see, with a simple linear regression model, we found that all feedback conditions had training dynamics that were significantly different from the observed in mock condition. But here it's interesting that feedback 0 with versus feedback mock, t-statistic profile is characterized by S shape, indicating the later one set of positive change and earlier saturation with a subsequent decline. It's really interesting that that test was also powerful enough to detect the difference in the learning curve shape observed in feedback 0 and feedback 500. But unfortunately, we doesn't see the difference for other feedback comparison. And you can see the interesting result that neurofeedback has a strong effect on the alpha spindle initial rate, but not for their amplitude and duration. It's consistent with our previous findings. Next, we analyze the sustained changes in the parameters of alpha spindle caused by neurofeedback. As you know, clinical training, these changes are really important. And we decided to record 1 minute baseline with open eyes before and after our training. And you can see here that an increasing in spindle initial rate in a post-training baseline. But this effect is significant only for feedback 0 and feedback 250. By visual inspection, the effect is stronger for feedback 0, but we couldn't see statistical differences. In order to demonstrate the effect of latency on the efficacy of neurofeedback intervention more directly, we took advantage on the fact that feedback latency can be considered as a conscious variable. So here you see the value of our latency is feedback 0, it's feedback 250, and this is feedback 500. So accordingly, we perform a regression analysis where statistical significance was quantified with parametric and non-parametric randomization test. Here, you can see that only changes in the initial rate significantly depends on the latency, and the sustainable changes were stronger for short latency. Conclusion. First of all, we found that feedback 0, so our lowest latency, the learning curves appear the steps by exhibit and interesting drop in the last of few training trials. It's only in feedback 0 condition that we observe target sustainable changes, and correlation analysis revealed dependency between magnitude and sustainable changes and the delay. So it means that hypothetically, in the neurofeedback paradigm, the minimization of delay should improve training efficacy, especially in the automatic learning it means that strategy-free feedback scenario. So, thank you for your attention. Any question?
Are there questions?
I have a question. Thank you for the very interesting talk. I was just wondering if you could talk a little bit more about the technique that you use to, instead of the bandpass filtering, to kind of reduce this delay. And if you don't do bandpass filtering, how do you know that you specifically detect alpha oscillations and not any other frequency?
Actually, we do the special filter before. So, do you want to more explanation about our method? Yes.
Right.
Okay, so we use a CFIR filter, and you see that convolution gives you ABC value, and the accuracy was in the same level for the classical filter, like Hilbert filter or something else. So if you want to read more detail, you can see the Coller's article about his method. You see the reference on the slide.
Thank you.
Okay, are there any more questions? Okay, thank you very much for that talk. And just a very quick announcement before our next speaker. The fourth speaker in the current list, which was Nadia Kuznetsova, will be speaking later. So our next speaker will still proceed, but we have a slight change there. And that's all. So our next speaker is Hayan Ayaz, sorry. And I see that you are here, so please proceed.
I started sharing my screen. Okay, so, all right. Hello, everybody. It's morning here, evening over there. Greetings from Philadelphia. So I would like to thank the conference organizers for this opportunity. So I'm an associate professor at the School of Biomedical Engineering, Science and Health Systems here at Drexel with courtesy affiliations at Department of Psychology, as well as University of Pennsylvania and Children's Hospital. And today I will be talking about optical brain imaging, which is a different kind of method than EEG, and it measures a different perspective of the brain function. And in my lab, we focus on using this and various other techniques to measure the brain activity in real-world contexts. And we develop new kind of hardware, software, algorithms, and methodologies. And we are seeing that this is also growing into a field that we call neuroergonomics. So before I start, here is my disclosure statement, basically saying we have patents and equity for various spin-offs that came out of the lab, and manufacturing research systems, also medical devices for brain scanning. Okay, so let's get right into it. So I mentioned neuroergonomics. So what it is, actually, it is the study of the brain, and you may think that there's already a lot of methodologies. Traditional neuroimaging and neuroscience research is already doing that. But I would argue that although the conventional tools and traditional neuroscience approaches are providing us amazing details about the inner workings of the brain, the problem is that they are mostly assuming that the brain is in isolation. However, in real world, the brain is almost never in isolation. So inside an MR machine, for example, you can only run artificial simplified tasks, but this is far from what we do in real life. And the information that we get about the brain function is hence limited. So we cannot have, for example, two people communicating or doing social interaction and many other kind of everyday tasks. Observing the brain in such natural tasks require neuroergonomic tools and approaches. And in fact, we have demonstrated with optical brain imaging that we can see brain-to-brain synchrony during successful communication. So in effect, our body impacts our brain, and both actually are needed to understand the behavior. And these have not been all incorporated in previous research fields altogether. One or two have been emphasized at the expense of the other. So what's unique about neuroergonomics is that we want to take into account all of them and also incorporate the environment in a continuum. And all these are in fact tightly integrated, but quite overlooked before. So how we think, make decisions, solve problems are all modulated by our environment and our physiological conditions. So we need to monitor the brain in realistic and real-world complex settings in order to both do basic and applied research. So here are some tools that we use quite often. As you are familiar with brain activity recording, EEG, and FNIRS, and also we can modulate the brain activity externally with electrical or magnetic stimulation. I mentioned here TDCS, and we also use TMS. And actually, we have demonstrated some of the first ways of doing these all together simultaneously, like FNIRS and TMS, FNIRS and TDCS, and we do quite often EEG and FNIRS together. So in this presentation, I will focus on some recent studies that we have done with FNIRS. Okay, so in order to get to the ideal brain-computer interface, I would say wearable and mobile systems are definitely important. And I believe these are three big milestones that we need to accomplish in order to reach that big vision. So the first one is the sensors. We need to get to this cost-effective, accurate, practical, and comfortable sensors that can be applied in everyday life condition, and also can measure the brain in unrestricted, kind of settings, like from office, lab settings to anywhere, like outdoors. So I think there's a community we have reached there, and in terms of FNIRS, we have developed very, very miniaturized systems at the moment. And the next challenge is about the signal itself. We need improvements in signal processing, data analysis methods to better attenuate the noise, extract more meaningful information from these measurements. And that's also quite, I think, advanced at this point, that we can monitor people outdoors. And finally, making the link between brain function or dysfunction, both in health and clinical conditions, to enable diagnostics, prognostics, and therapy assessment. And just in my lab, we have studies from mental health to neurological conditions at various levels that we are trying to understand the diagnostic and therapy assessment feature of brain signals, particularly from FNIRS. So I would like to share a success story of a mobile neurotechnology that is now in routine use. So we have actually developed this first of its kind optical brain imaging system from concept now to a novel life-saving solution. Infrascanner is the first optical handheld brain bleeding detection device, and it's already deployed in many countries in both military and civilian hospitals for traumatic brain injury in emergency care and even in ambulances and even at the site of the accident. And it's already becoming the standard of care in some countries. We have also focused on developing mobile optical imaging systems for brain function measurement. So this technique called functional near infrared spectroscopy, FNIRS, is now a mainstream, I would say, neuroimaging modality that hundreds of university researchers are using. And these images are from our studies spanning the last decade, demonstrating the trend from artificial, highly restricted environments 2 decades ago on the lower left corner to high fidelity, realistic settings, and from there, most recently, to real task settings where we actually do our typical work. So in the photos showing moving platform flight simulator, to measure the brain function, we simulated the flight settings for a pilot while they are using this from there to actually measuring the pilot during a flight and using the brain signals to decode the mental state. So the aircrafts that you see is part of my colleague and good friend Frédéric Dehaye's lab in Toulouse, France. And he's an aviation researcher and has a lot of interest in neuroergonomics. Similarly, we have been doing the same for many other industry partners as well, like using the brain activity to optimize financial investment platform interface, and from there to coffee machine, and from there to air traffic controller radar screens. So it's a diverse array. And speaking of aviation, we have over 10 years of research looking at brain activity of operators, like air traffic controllers, to first understand how the brain activity changes with different parameters of the air traffic control systems, and then after understanding the signals and solving some of the challenges like noise issues, we moved into decoding the mental states. And we have done this both in simulators, like flight simulators, and from there to real environments, like where they actually work, like the tower and etc. So let me give you a couple of example studies. This is one of the first study that we have incorporated FNIRS to FAA's William Hughes Tech Center in Atlantic City, New Jersey, and we have actually monitored the brain activity with FNIRS while they manage realistic air traffic control scenarios under typical and emergent conditions. The primary objective of this study was to use neurophysiological measures to assess cognitive workload as a passive BCI using the new interfaces developed for air traffic control systems. Throughout the study, certified professional controllers actually completed these air traffic control tasks with different interface settings, so we assessed which one actually induced a lower level of activity. The results actually gave us, first we gone through a series of studies to verify using classic tasks like MBAC, working memory task, and to enable us to understand that we can really measure the workload. And we use that later in a model, the classical paradigms brain activity, to help us gauge the more complex tasks brain activity using this personalized model for each subject. So let me move to another example where we actually investigated expertise development with practice and in complex piloting tasks. We used FNIRS to investigate the relationship of the hemodynamic response in anterior prefrontal cortex to changes in the level of expertise and task performance during learning of unmanned aerial vehicle piloting tasks. So novice participants without any prior experience participated in a 9-day training program where they used flight simulator to execute real-world maneuvers. And the results indicate that in the dorsolateral and ventrolateral prefrontal cortices, there was a concomitant change with the practice, that there was a decrease in the prefrontal area of the activity, that as they practice, they get more confident and with less attention needed on the task. And as we used this to create a model of neural efficiency using both the behavioral data and the brain activity data, we were able to create this individualized trace that they shift from lower efficiency to higher efficiency regions as they go through. So we published these over several years ago, and this is another example where we implemented an online passive FNIRS-based brain-computer interface to discriminate 2 levels of working memory load during highly ecologically valid aircraft piloting task. Here you're seeing Frédéric Dohe, me and the team in Toulouse, France, in front of the aircraft that we used. And we used a serial memorization task consisting in repeating series of air traffic control instructions, both easy and hard, and in both high fidelity simulators, as well as real flight condition up in the air. So we tested the same concept, both done in a high fidelity simulator and also in the real setting. The single trial working memory load estimator provided high classification accuracy in both cases and was over 76%. So the results demonstrated the feasibility of monitoring cognition in extreme and complex real-life situations, even during aircraft piloting tasks, showing potential benefit for future flight safety programs. So another example is related to brain-to-brain coupling, defined as the intersubject correlations in the hemodynamic response. And this was a collaboration with Yuri Hasson at Princeton University. And we actually had the speakers and listeners both monitored, and the listener's brain activity was correlated with the speaker's brain activity with a delay. This between brain correlation disappeared when verbal communication failed. Also, the FNIRS and fMRI recordings of listeners comprehending the same story were compared, and we found that a significant relationship between the FNIRS oxygenated hemoglobin and fMRI both signal exists. This cross-modality consistency further highlights the reliability of the spatiotemporal brain activation pattern as a measure of story comprehension. So these findings indicate that FNIRS can be used actually in novel brain-to-brain coupling during verbal communication. And as a follow-up to this study, actually, we looked at the brain activity of individuals and to be able to estimate what they are listening to. So we showed the first evidence that perceived speech can be identified from listeners' brain signals using FNIRS as a variable sensor. So we applied machine learning to train predictive models using FNIRS data from a subject pool to predict which part of a story that the listener was attending to, and then a new subject not in the pool, based on the brain's hemodynamic response, was tested using the FNIRS data of that. To overcome interpersonal differences in measurements, a generalized canonical correlation analysis was adopted to extract latent variables that are shared among the listeners before applying principal component analysis for dimension reduction and applying logistic regression for classification. So over 74% average accuracy has been achieved for differentiating between 250-second long stories, and 44 average % accuracy for differentiating 4 25-second long stories. The results suggest the potential of FNIRS for building a speech decoding brain-computer interface for new types of neural prosthetics and other uses. So in summary, we showed diverse studies confirmed also by other labs that cognitive workload can be monitored with variable optical neuroimaging, and even for physically active ambulatory individuals. And we can use this information to improve complex machines, from aircraft cockpit to coffee machines. And we can develop implicit and explicit brain-computer interfaces. And we can use this to enhance the human-to-human communication or improve the human-to-machine interaction in a variety of ways. Of course, there are still many challenges exist in the field. First of all, the spatiotemporal resolution needs to be improved, and this is true for all all neuroimaging systems to get more information from the brain. Also, there is the issue of noise and nuisance signals. Although FNIRS is relatively resistant to motion artifacts, still it is not immune, and it receives a lot of those. And also the signals contain physiological signals as well. We need to eliminate that in pre-processing. And there's also the common issue of non-stationarity and time-varying aspect of the brain activity. And of course, the common BCI challenge is the calibration. So we need to get very large amount of calibration to really get very consistent kind of BCI typically, but can we do it in shorter period of time reliably? So that's the big, I guess, question for many BCIs. And also in general BCI, BMI issues, there are different aspects like safety and reliability versus for a company like fast innovation and financial sustainability. On the other hand, open research versus IP protection, and different discussion points like clinical regulation, as well as we need consumer regulation. There are different systems out. There is also public interest versus private interest and different approaches in different countries and intercultural differences. And these are some issues that we have discussed at the IEEE Neurotechnology Committee and trying to put together a kind of guideline for development of standards towards BCI as well. That's another initiative that some of you may be familiar, and that's a process started. And another kind of new information is our new journal that we just launched actually on neuroergonomics. It is focused on the studies of understanding the brain in using mobile and portable neurotechnologies. So I hope you can also consider this as for your upcoming papers. And we also have the neuroergonomics, our neuroergonomics conference postponed to next year due to COVID. So it will be in Munich, Germany. So I hope to see you there as well. And that's it for me. So if you have any questions, I would be happy to answer.
Thank you. So actually, we should move on to the next speaker in the interest of time. I certainly agree neuroergonomics is an important direction and has often been underappreciated, especially real-world applications. But just to keep up with the schedule, if you do have questions, of course, please send an email or there's the Neuro bar later and such. Our next speaker, it will be Pavel Bobrov. And so please go ahead.
Hello, dear colleagues, can you hear me? Can you hear me?
I can hear you, yes.
Okay, great. So let me share my screen. So I'll talk about the use of brain-computer interface based on motor imagery for rehabilitation of motor function impairments in different patients, and in particular in patients with in children with cerebral palsy. So this work was done by our group in Pirogov Russian National Research Medical University together with Russian Children's Clinical Hospital, which is a subdivision of the medical university. So historically, what we have is this a chair with exoskeletons, which are controlled via the EEG-based brain-computer interface. And here is the experimental setup, which we used for healthy subjects and post-stroke patients in our earlier clinical trials of this technology. So I have reported some of the results of these trials during the previous BCI Samara conference. And now I would like to talk about our methods for processing the EEG and for results we obtained from the group of children with cerebral palsy. So basically, the paradigm is that a person tries to imagine his hand movements, in particular opening their hand, and the BCI allows this exoskeleton to produce the actual movement, providing not only a visual but also tactile and proprioceptive feedback. And what we have CAM2 is this a method for processing the data we obtain from such experiments. First of all, there are experiments or procedures with the BCI, and then we use several signal decomposition methods such as ICA or blind source separation method or common spatial patterns. Then we use some source localization techniques to estimate if the obtained components could be adequately approximated with a single dipole. Then as we obtain a lot of these components, we use an attractor neural network to cluster them according to their similarity in their spatial distribution and their frequency domain. And then we estimate the relevance of this component for the work of the classifier. And thus, we can somewhat summarize what are the most typical patterns which allow our classifier to work, and thus we can investigate the brain activity. So we use these EEG decomposition techniques, which can be represented like a sum of source activities. So we can use different ICA or common spatial patterns methods, which are either blind or non-blind, but in general, what is important that the signal is decomposed as a sum of these components. Each of them is characterized by their spatial distribution, which provides the contribution of each component into the signal obtained by our sensors, and it's a temporal activity which we can study. So there are a lot of methods which could be used. So here are the methods we used in our work, and as you can see, even the principal component analysis could be treated as this method when we don't throw away any components. So we can also say that even principal component analysis provides such a decomposition. And first, we also try to use individual head models for localizing these components, because the contribution of each component can be interpreted as a distribution of electric potential over skull. And thus, we could try to localize its source. And also, so we now present the results obtained for healthy subjects with who undergone the BCI experiments. The analysis here, the slide here presents the most typical EEG components obtained for these subjects by all of these used methods. So the cluster analysis, of course, revealed the components related to blinking and eye movements, and maybe some of you know that there exist even some classifiers which allow to detect and eliminate these components from EEG signals, even not related to BCI. As far as I know, EEG Lab uses such a technique, so this is something you might seen already. And also, there are components related to occipital alpha rhythm, which doesn't exhibit any particular specificity for motor imagery. And here there are power spectra presented at these graphs, and red lines and green lines correspond to motor imagery, while blue lines correspond to resting state. Here are typical components which can be described as a mu rhythm, and they exhibit the desynchronization when people try to imagine their hand movement. These experiments, as you can see here, often in our experiments, the rhythm suppression can be observed in both when contralateral or ipsilateral hand movement is imagined. We think that this is mostly due to the design of our session, where the patient or a healthy subject has to maintain their motor imagery state for a longer period. He doesn't have to imagine this once and repeat these trials. Rather, he has to maintain this motor imagery for 10 to 15 seconds. There are also components which could be localized, but this is a more questionable one, as activity in premotor areas, also a supplementary motor cortex, and activity in precuneus. So all these sources are typically observed in healthy subjects. And as you can see, there are a lot of areas, brain areas, which activity is specific for motor imagery, not only the primary somatosensory areas where neurorhythm desynchronization is observed. So these results are in agreement with different studies and also fMRI observations, which provide the information that there is a vast network which is involved in motor execution and motor imagery. Then this slide illustrates that we really see the activities from the areas I mentioned, because here there are results of localization pulled from subjects with individual head geometry into MNI space. And here are the sources for neurorhythm, precuneus, premotor areas, and supplementary motor cortex. Well, this picture illustrates the importance of using the individual head geometry to avoid systematic error, because these neurorhythm sources, when the standard geometry is used, have moved into frontal areas, which is clearly an error. And so thus, these results allowed us to compare what we get from healthy subjects to the results we obtained from post-stroke patients. And in post-stroke patients, we did observe the components related to neurorhythm desynchronization. And here, this slide represents a typical situation. In some patients and in intact hemisphere, sometimes the picture is almost like in healthy subjects. There is a typical upper alpha band frequency peak and observed rhythm desynchronization. So in some patients, there is also a dominance in beta frequency domain, while in many patients, the peak frequency of alpha rhythm is typically lower than that of the healthy subject. And this is important when you, for example, try to use some narrowband filtration for BCIs targeted for the patients. You could easily miss this peak because you would go for something like 10 Hertz, while their peak frequency may be even lower than 8 Hertz. And this is the case of severe lesion, which illustrates that there exist two sources of neurorhythm in the damaged hemisphere. They do exhibit the specific desynchronization, suggesting that there still is electric activity, which is also stimulated by BCI training. But which is interesting that these sources, there are two sources obtained by different methods. So different ICA methods see these activities as two sources, suggesting that there may be distortion in synchronization, in rhythm synchronization at this area. So the network responsible for motor imagery and execution may have lost some connections. And so these two sources are somewhat desynchronized, but they do still exhibit activation when the movement is imagined. And what is also interesting that in this case, the case of this patient, the rhythms in intact hemisphere and in precuneus are like those observed in healthy subjects. We also observed the activity in precuneus, supplementary motor area, and premotor areas in post-stroke patients. So this also shows that our method could allow to extract these typical patterns, and the brain-computer interface based on motor imagery does indeed provide the specific EEG activation, brain activations. So it does really target this motor network. So now, what about children with cerebral palsy? A couple of years or so ago, our colleagues from Crimean Federal University started to use the device you saw for treating the children with cerebral palsy. They had very promising and prominent results, and that also allowed us to, it was very interesting, so we took interest in this. And here is the group of children. Well, one of them was 19, but others were aged from 10 to 17 with different hemiparesis. These children are suffering from cerebral palsy. There were 7 girls and 7 boys who participated in the study, and they also undergone the procedures with this brain-computer interface, with this device. Their clinical outcomes show that there were some improvements in different clinical scales and different tests. There is some, for example, ARED scale shows that they had improvement in overall score, which is significantly different from 0. There were improvement in grasping and gripping movements, and also improvement in a total Fugel-Meyer score, and also they could better manipulate with light and light-weighted cans in Jepson-Taylor test. So these are some clinical outcomes, which are, of course, of course, more research and more participants and control groups are required to say that this procedure does have a clinical effect, but these results are promising. And so to process their data, when we started processing the data, we also noticed that they are prone to artifacts when compared to healthy subjects and even patients, because children sometimes do move and they couldn't still sit still compared to the grown-ups. So we used this adaptive mixture of independent components with the ICA method, which also allows somewhat automatic segmentation of EEG into models with different statistical properties to eliminate the artifact, the EEG epochs contaminated with the artifacts related to movement. And after that, we used all other decomposition methods and also studied the patterns, EEG patterns more typical and more significant for the classification. We could extract the components related to the mu rhythm, and we investigated their occurrence, their ERD expression, and peak frequency of the rhythm. What is interesting that here, as you can see, the sources of mu rhythm were extracted in both so-called lesion and intact hemispheres. I put this in quotes because in some children they were diplegic, so they had both hemispheres were lesions. But it's so interesting that we do see these mu rhythm sources which exhibit a specific activity to motor imagery, which is in agreement to available with data available from other groups who are saying that children, and in particular children with cerebral palsy, do exhibit abilities of motor imagery, which is an interesting result by itself, because one thing is that a grown-up can, even with lesion, with a brain lesion, can imagine the movements. They move their limbs in they have experience of moving their limbs, while children with a cerebral palsy often do not have so much experience in moving their limbs, but somehow they still manage to produce this activity. But this is, of course, it is of course necessary to investigate this in more detail. And here the slide shows the BCI control accuracy for these children when compared with healthy children who controlled the same exoskeleton, or just imagined movements without it, or performed real movements also without exoskeleton. And as you can see, sometimes these children with cerebral palsy can have even very high accuracy of BCI control, and they have results comparable to the healthy children. But here, healthy children had only one session when compared to the children with cerebral palsy, and maybe when trained for, say, 10 days, they maybe could provide the higher BCI control ability. We also showed that the ability of controlling the BCI in these children with cerebral palsy depended on the new rhythm source occurrence, the event-related desynchronization value, and in both intact and paretic hemispheres. So thus, the motor imagery BCI is a very promising tool for children with cerebral palsy, but more research is required. More clinics are required to maybe conduct such investigation. And here, I think I'll finish my talk, and thank you for your attention. And I thank the organizers for the opportunity to present our results at this conference. Thank you.
Okay, yes, thank you for the talk. And again, I'm sorry to all the speakers that we don't have a little bit more time in the session. As I mentioned earlier, we might go up to 30 minutes overtime, or that's the best estimate that we have right now. And just to keep things moving and keep on schedule, we'll move to the next speaker. And it looks like our next speaker is a slight change in the order. The next speaker will be Lyubov Vasileva. And I also wanted to quickly mention Nicole. Oh, sorry, go ahead, please.
Can you hear me?
Yes, I can hear you.
So that is my screen demonstration. My report is about chronic brain implants and how they influence nerve rehabilitation and basic research. So chronic single unit recordings date back more than 60 years, and they started in the late 50s when Strumpasser implanted microwaves into the brain of ground squirrels and recorded single units in the reticular formation for 4 days.
Sorry, do you have slides here? Because we don't see anything.
Oh. Yes, I demonstrated the slides. Can you? Don't you see anything?
We don't see your slides here.
Oh, okay. I will fix it.
Please push совместное использование on the right.
Okay,
can you see my
excellent.
slides now?
Yes, thank you.
So I told you about the Schumacher work on ground squirrels, and they managed to record the single gene for days chronically. And since then, there have been many advantages in chronic single gene recordings. There were discoveries of plate cells of the grid cells in entorhinal cortex, single neurons of Jennifer Aniston, and brain gate neuroprosthesis. There were also technological improvements in single gene recordings, and I will tell you about it in a minute. And I also want to mention an article by Elon Musk, who built a method from the microelectrodes to implantation robots and recording device to record about thousands of channels. So there are still issues in the chronic recordings, and among them there are low multiplexity. We still need more recording sites and more implanted electrodes to get more neurons. Also, microelectrodes are foreign bodies for our brains, and neuronal system demonstrates tissue reactions, and we still need some approaches to mitigate it. And also the third one is instability, because sometimes neurons change. I mean that in the most cases we can't record the same neurons for longer times, and we need such an improvement. So first I will mention about various types of recording devices. There are I can name 3 types of them. So conventional microelectrodes, those are metal electrodes that resemble those ones that we used in the 50s. The next one is the silicon-based probes, and they integrate recording and preamplifying parts. And the third one is next generation electrodes, and they share mechanical properties of the brain, because other microelectrodes are too stiff for brain tissue, and they have drive neuroinflammation and tissue reaction, and soft materials cause lower immune response, and seem to be better friends. So neuroinflammation is a response for foreign body, which is microelectrodes, and we can't avoid it at all, but we can control it. And there are many strategies how to mitigate the TC response. The TC response includes the acute and chronic stages, and those stages they're after and microglia play roles in those stages, and there are several neuropharmacological approaches to control them. So there are studies on dexamethasone, antibiotics, cell targeting, inflammasome targeting, and others. There are certain restrictions of this kind of this types of approaches, because drugs have a limited time of action, and we need other doses of drugs to control the response. And also I can name drug side effects among the disadvantages of such an approach. So I'm moving to stable recordings, and stable recording is a kind of chronic recording with when a single unit is recorded for days, weeks, and even longer, and the recording doesn't limit to one recorded session. It is a very useful approach for brain-computer interfaces, because for example, for 3D arm, we need several degrees of freedom control, and single unit signal is a good type of signal to get all those types of signal for the artificial arm. Here I show a picture from an article by Downey and colleagues. They recorded from motor cortex of tetraplegic patient, and they established that units, single units exist on channels for weeks and months, and it is a very interesting fact, because we having the same neurons in the recordings, we don't need to maintain the brain-computer interface often. I mean that we don't need to a special technician to maintain it and to change the algorithm, and that's it. And as well as for brain-computer interface, stable recordings are also useful for basic research. Here I show a picture from a paper of mine, where colleagues and I recorded from monkey motor cortex and assessed longevity of stable recording. And we showed that the maximum duration of single gene recordings was 94 days. Also, at the lab of David Leopold, they recorded with similar electrodes and found neurons were stable for months, like here. So in the picture you can see stable waveform and stable interspike histogram of this neuron, and it was stable from December to March of the following year. And in the next picture, I show a stable neuron. Amplitude of the spike is different, and you can see that responses to stimuli are so I would like to finish with future directions of recordings, and there are three directions that I can see. So stable neuronal recordings will solve some ethical reasons of animal regulatory arts, because the recording of the same neuron within a long time will allow the experimenters to test that neuron with the various conditions and more animals to do that. Also, chronic stable recording will lead to building single gene-based computer interfaces with longer lifespan, and even this time will be comparable with human lifetime. And studies of brain mechanisms also can benefit from chronic stable recordings, and especially long-term memory and aging research. That's it. Thank you for your attention.
Okay, thank you. We have time for one question.
I've got a question.
Please.
So I'm sure many of you are wondering now, where does Neuralink probe stand in terms of chronic implants? What do you think about it, and how good would that be for human brain-machine interfaces? Thank you.
Could you repeat your question, please?
The question is about the recently developed Neuralink probe, and whether it stands its place in brain-machine interfaces, in either animals or humans.
I think it has a great future in animal and human research, because I can see their ambitions and motivation, and it is very perspective, I think.
Okay, thank you. And before we move on to the next speaker, we have a quick announcement. We would like to announce a poll for the best speaker. So we'd like to ask the participants to choose, or sorry, the poll for the best poster. So after when you have a chance, please select up to 3 posters that you liked at the exhibition. And also, since BCI Samara is here, would you like to add anything quickly?
Thank you, Brendan. You told everything absolutely correct. So we are running a poll now, and please choose 3 posters that you would like most if you had a chance to visit the poster area. And if you didn't have a chance, please take this chance tomorrow from 6 to 8, as I remember, or for, yes. So please, if you did have a chance, vote. If you didn't, do it tomorrow. Visit the poster area. Thank you very much. Sorry for interruption.
No problem. Thank you. And yes, this is important. If you're a conference organizer or if you're a poster author, it's nice to have a Best Poster Award. So I agree, everybody should vote. And so the next speaker in the list is Yuri, and I see that he is here and looks like he is ready to chat. Many people already know that the Santa Lucia Foundation is well respected in BCI research, and I'm looking forward to his talk. Please go ahead.
Can you hear me? Can you see my screen?
Yes, I can hear you and see your screen.
Just about screen. I cannot launch my PowerPoint. Okay, so now we switch to a little bit different, not topic, but example, let's say, of BCI. Just a couple of words about myself. So yes, I work at Santa Lucia in Rome, Italy. I'm the head of GATE laboratory. And I'll talk today about BCI approach based on EMG signals to the control of lower limb exoskeletons. Basically, why I said that it's a bit different example. Now we switch to the control of locomotion. In contrast to BCI applied to brain, to control of arm movements and consciousness and so on, locomotion is also largely controlled by the spinal cord. And this makes a bit of difference when we talk about application of BCI. Basically, today I'll present some of our investigation studies during, let's say, last 10 years related to specific application by using, let's say, arm-leg coordination for the control of exoskeletons and namely using EMG signals. My talk will have 2 parts. The first one is a kind of brief excursion to the basic control mechanisms and, let's say, why we chose EMG signals and what is the rationale actually of our approach. And second part is related to basically implementation of this approach. So in essence, this introduction is related to those 2 sentences which you can see in this slide. So we try to use biologically inspired control mechanisms, not just artificial, and so on. I will come back to this later. That can also reinforce central pattern generation circuitry. And second, why EMG signals? Because it's a kind of measurable output of the CNS. Briefly, some examples of what I mean by biologically inspired. No, everybody knows, but I would like to emphasize still these points. No, some examples. First of all, neural coupling between upper and lower limbs is supported by cross-limb reflexes, facilitator effect of arm movements on leg movements, and basically the presence of rhythmic activity of upper limbs during normal walking. In the following slides, some examples. We did some research in neonate stepping, and this neural coupling can be seen as early as actually during in neonates. In this example, you can see this neonate is 2 days old, basically, stepping on the treadmill. You can see there's a synchronous coordination between upper limbs and lower limbs. it's a kind of diagonal gait. So left arm is in synchronous with right leg and so on. If you compare with adult stepping, walking, so it's basically the same diagonal gait. The only thing that orientation of the upper limb is, let's say, almost horizontal in neonates, in contrast to vertical. But the face diagram is basically the same. Half of the cycle shift between ipsilateral leg and arm. This concept of quadrupedal gait actually is rather popular, and in the more recent studies, this group from France actually, they even argue that humans are born as functional quadrupeds. They performed some experiments using this skateboard and recording crawling in neonates. I'm talking about not just infants, but neonates. So this, and I would like to emphasize that neonates, the control is basically spinal. The control of stepping, not cortical. So that's what I want to say, is that this arm-leg coordination is not only innate, but it's really something automatic and very strong in a sense. As example, we did some other experiments recently and during last year. So arm movements can facilitate leg movements. In this example, we use this exoskeleton in the gravity neutral position, so it's a horizontal ear stepping. You can see that legs just, they do not touch any treadmill, and the advantage of the system is that it's frictionless. So a small rhythmic activity of arm movements activates actually central pattern generator in the lumbosacral spinal cord, so that the legs start to move in most subjects, basically. So then finally there is a obvious, as I mentioned already, example, evidence of arm-leg coordination, the presence of EMG activity. One can see, since arm movements are controlled by cervical spinal cord and leg movements are controlled by lumbosacral, so one can see actually the coordination between motor pulse by mapping EMG activity of many muscles to the spinal cord. Because we know innervation of muscles in the spinal cord, so that one can reconstruct motor neuron activation in the cervical and spinal cord. And in the next slide, you can see the result of this study. We published it some even more than 10 years ago. If you see here a spinal map of motor neuron activation during normal walking, it's one stride, stance phase, swing phase. You see that in the cervical spinal cord, there are some loci of activity which are synchronous with lumbosacral loci of activity. So we even know the phase and of this coordination. What I would like to emphasize is that during normal walking, mainly proximal muscles are active, not distals. For example, wrist muscles, forearm muscles are not so active. And they are active during many locomotor-related movements like skiing, crawling, etc., not just walking, running. So proximal muscles is the target, in a sense, for using them for automatic, natural coordination and control of leg movements. And this natural involvement is very important. And this makes also a difference from approaches to control exoskeleton related to the usage of EEG signals, etc., etc. I'm talking about locomotion. Because if you want to use EEGs, maybe you need to think about each step. So you need to, cortical involvement is really major. So you need to think, you cannot do anything else. So you mainly need to think about left legs and move right leg, so it's continuous thinking. In contrast, if you use shoulder muscles, it's really automatic. You can walk, you can talk, you can even read something. So it's really automatic. It's much easier and perhaps for patients would be to use it. So these are small differences to defend, or let's say to explain why the rationale of our approach. So my second part is related to implementation. This slide illustrates just the scheme of our approach. So we use EMGs of shoulder muscles. Then we use different approaches, something like or to use DRNN or to use directly EMG signals. I'll come back to this just a bit later, to predict kinematics. And then when we can predict kinematics, we can control or virtual reality or exoskeleton, virtual reality for some training basically, or even working in the exoskeleton. And those two approaches, one is related to the pulsatile nature of EMG activity. So just say there are bursts of activity, which is rhythmic activity, actually locomotion is rhythmic activity. Second approach is in contrast is DRNN, using the dynamic recurrent neural networks. So actually this work has been started as initially as a MindWalker project with collaboration with many people, actually in some group in Belgium in particular. And with this group we did, we applied first DRNN. So to predict kinematics, first we need to find us to associate EMG activity with kinematics. So we recorded different conditions like normal walking with enhanced upper limb movements, so you can see that the amplitude is a bit high, or during stepping in place, or even during posture. So we tried different conditions, but basically to associate EMG activity with natural coordination of upper and lower limbs. So DRNN, I will not talk about the details, but basically there is learning phase and there is prediction phase. During learning phase, you try to associate for this specific recording, so EMG activity. And prediction actually is not so bad if EMG activity is prominent. That's why sometimes we need enhanced arm movements. I'll just explain it. And then there is a prediction phase when we use unlearned EMGs to predict kinematics. As you see that the error is relatively small and correlation is relatively high. Again, if EMG activity is more or less prominent. And in the next slide, just an example of what I mean by prominent. This normal walking, but still at high speed. And well, everybody knows that arm movements during walking depend on speed. For example, at 2 kilometers per hour, basically there is no arm oscillations, and the EMG activity is basically noise. At 3 kilometers per hour, there is EMG activity, and I think in this slide maybe at 4 or 5 there is activity. But if you slightly enhance movement, there is no problem actually. There is the same phase, but EMG activity is much more easy to interpret and to associate with like kinematics. And you can see this again, there is a higher prediction. Yeah. This study has been done offline. And still it has some disadvantages because the learning requires some time. And if you produce learning for one subject, then it's a bit, because of inter-individual variability in EMG patterns in arm movements actually, then it's not so easy to transfer this DRNN from one subject to another one, only to some extent. Sometimes we could manage, but sometimes we failed actually. That's why we applied the second approach, which actually is much more efficient. And surprisingly, it's really, most subjects can do it very easily, but without much of training, which is related to pulsatile nature of EMG activity, like because EMGs are active in bursts. So we can use this temporal structure to predict the next step, the forthcoming step, in real time, basically. So we implemented in LabVIEW, this is just an example, and using small wireless Delsis EMG sensors, which are just very small, just 3 by 4 centimeters. You can put it inside, I mean, nobody hide it inside T-shirt or whatever. It's really, it's no wires. It's extremely convenient for the patient. Mine is. And in the next slide, there is brief scheme of the algorithm behind this approach. If you want to look at details, you can just read the papers. Basically, I already said that it predicts the special temporal kinematic pattern of the forthcoming step. based on the rectified and smooth EMG activity of deltoid muscles, proximal shoulder muscles, I already mentioned it. For example, here in this example, actual kinematics, shank and left and right leg, and you can quite predict the durations relatively well. This approach can be applied for gait initiation, because if there is no activity, there is no exoskeleton movement. To gait termination, also control speed, because basically by changing the rhythm of this EMG activity, you can control stride duration very, very easily and control speed to some extent. And it is rather protected in the sense that the problem actually of many EMG of BCI approaches for the exoskeleton is we need to avoid undesirable movements. So, for example, if we have some activity which is or ESG activity or EMG activity not related to gait, then there might be some input to the exoskeleton that we need to avoid. This approach is very actually robust. So, because if there is no alternative movements, there is no the kinematics, the output is zero, and it will be immediately terminated gait, and so on. If you move only one arm, also nothing would happen. Also, it controls to some the window, the searching window for those peaks. So, if it is too much out of window, some unexpected burst, then it also stops. But if you just move it naturally, because I already said that it's a natural coordination of arm and legs. That's why this approach is robust. We implemented this, and when we recorded EMG activity during different speeds, 3, 4, 5 kilometers per hour, and apply different low-pass filtering. Actually, the best maybe fitting is the best prediction at relatively slow speeds. But anyway, it's most subjects actually were successful in producing predicted kinematics very close to actual. Correlation is extremely high. There is some effect of filtering, but still it works. Then we also use variable walking speed, not just constant. So it was a ramp velocity profile. So, and it's really also even good prediction of variable speed from stride to stride. I mean, higher correlation. So it's not just you can control walking speed by this method. And finally, we implemented in real time, both in the virtual reality setup and during working in the exoskeleton in some pilot experiments. So on the left, you can see this example of virtual reality. So you see this when you do not move anymore, then you immediately stop. It takes a couple of oscillations to start movement, because you predict the forthcoming step based on the last, let's say, half of stride, last step or last 2 steps. So, but with the delay of one second, you basically start movements. This exoskeleton walking, we implemented in a few subjects only, who were trained first to walk in the exoskeleton, because the limitation of this approach, or at least one limitation, is related, when we talk about exoskeleton, is related to using crutches during exoskeleton walking for stability, because most exoskeletons do not provide stability when we when we use exoskeleton, for example, for spinal cord injury patients with complete paralysis, etc., etc. This exoskeleton experiments we did on some healthy subjects, but still they could easily control both walking speed, initiate, terminate, etc., etc. Well, this is a summary. If you want, you can read it. But basically, we managed to implement this interesting approach, at least alternative to other, and which is biologically inspired. And if we engage cervical spinal cord for the control of exoskeleton, it has also not only assistive technology, but also rehabilitation technology. Thank you for your attention.
Okay. Yes, thank you. And work with gait rehabilitation, stroke rehabilitation. There's been a lot of that here.
Yeah.
And so we have an announcement, and it looks like we have a change in the speaker order. But first I will get to the announcement. The announcement is that we want to invite people to chat with companies and posters tomorrow from 18 to 20 at GMT +4 at the end of the session. And also, I believe we have a speaker that was scheduled just before, Alexei, but let me just double check with info BCI Samara if you have a preference for the remaining speaker order. Otherwise, we'll proceed with Alexei as the next speaker.
Okay.
Okay, then let's proceed. Go ahead, Alexei.
Okay, at first I need to some apologize because due to some misunderstanding, I prepared my short speech in Russian, and then I, if you let me, I speak in Russian, and yes. Our English guests, please push button translate in the right and down on your Zoom, and I start my presentation.
Okay, go ahead. Thank you. Da.
Еще раз добрый день, дорогие друзья. Я постараюсь просто говорить быстро, мне уделили 12 минут. Я постараюсь более короткий срок. Дело в том, что я здесь выступаю в огромном количестве ипостасей. Я ведущий нейронедели. Я выступаю в качестве докладчика на симпозиуме. У меня будут еще несколько научно-популярных и других выступлений. Я еще здесь научный журналист. Я не совсем ученый. Вот мои все аффилиации, и здесь, вот в этом докладе, я представляю, получается, два учреждения. Во-первых, портал нейроновости.ру, на котором появятся новости про все наши выступления, все доклады, ну, про большую часть в течение времени. А во-вторых, я еще и заместитель руководителя Центра компетенций национальной технологической инициативы по технологиям новых и мобильных источников энергии. И вот в этом качестве я делаю свое небольшое выступление, которое является не столько научным докладом, и не столько о том, чем мы занимаемся, хотя я об этом тоже, а скорее некоторые постановкой проблемы, постановкой вопросов, на которые стоит обращать внимание тем людям, которые разрабатывают интерфейсы мозг-компьютер и нейроимпланты и думают об этом на какой-то длительный промежуток. По-хорошему, да, конечно, можно считать, что мой доклад представляет собой некий ответ студента. Вы помните, тут замечательный анекдот, когда студент подготовил билет по блохе, на экзамен по биологии ему выпали рыбу, он говорит, если бы у рыб была шерсть, у него появились блоки, так вот о блохах. И я, видимо, здесь рассказывал о топливных элементах об источниках питания, как-то привязав к нейроинтерфейсам и нейроимплантах, но на самом деле это не так, потому что проблема, которая стоит сейчас перед всеми носимыми медицинскими устройствами, она действительно большая. В чем она заключается? Мы понимаем, что когда у нас есть некие имплантируемые устройства, они требуют источников, они требуют энергии. Такие устройства появились достаточно давно, это еще с 50-х годов первые имплантируемые механические электрические устройства. И, естественно, они могут питаться по-разному. Они могут, источники питания к ним могут находиться на поверхности тела, на одежде, и могут быть имплантируемы. И, соответственно, они могут по-разному отличаться по типам источников энергии. Это могут быть первичные источники питания, то, что в русском языке называется батарейка, которая не заряжается, а просто имплантируется в тело на какой-то срок. Это могут быть вторичные источники питания, перезаряжаемые батарейки. И могут быть то, что на русский язык называется, не имеет перевода, на английском языке называется power harvesters, то есть это устройства, которые получают энергию изнутри, разного типа энергии. И вот смотрите, прекрасно в этом сентябре этого года был опубликован прекрасный обзор, который дает такую некую таймлайн, некую шкалу технологий и технологий внутренних харвестеров энергии и технологий и приложения, которыми они появляются. Вот смотрите, первым появился, естественно, сердечные кардиоимпланты. Это сначала кардиостимуляторы, затем это искусственное сердце. И уже сейчас мы имеем с этими уже сильно обкатанными устройствами несколько проблем. То есть если это у нас кардиостимулятор, мы имплантируем внутрь, чаще всего с ним первичный источник энергии, которого заявлено, что его хватает лет на 10, реально они служат примерно 3-6 лет, и потом требуется операция по замене всего источника питания, кроме самого электрода, который сейчас стоит примерно замены $30,000. Немало. Вот. А если у человека искусственное сердце, там вообще проблема, потому что оно жрет очень много энергии, и в итоге эти люди живут с аккумуляторами, перезаряжаемыми на поясе. И даже у этих людей возникает фобия сна, они боятся проспать зарядку, что у них просто становится А харвестеры бывают разные. Они потребляют разные типы энергии. Самым первым появились устройства, которые преобразуют радиочастотную энергию в электрическую. Они очень маломощные, тем не менее. Они все, в принципе, достаточно маломощные. Потом появились термоэлектронные генераторы, которые преобразуют либо энергию в тело, в электрическую энергию, в крайнем случае это такие атомные батарейки, которые фактически небольшой кусочек плутония, который распадаясь, нагревается и дает электричество. Следующим появились биотопливные элементы, которые работают на ферментах. Затем появились пьезоэлектрические генераторы. Вот справа вы видите прототип, который называется нейродас, такой вот небольшой чип, который может быть имплантирован на периферический нерв, на кровеносный сосуд. Он, в первую очередь, периферический нерв, он может считывать информацию и стимулировать нерв. Пока что удалось достигнуть объема примерно в 6 кубических миллиметров, то есть очень небольшой, хотя надо, конечно, гораздо меньше. Вот такие крохи пока что считаются пьезоэлектрическими генераторами, то есть их нужно питать ультразвуком. Вот. Ну и последние, буквально в 90-е годы появились, в конце 90-х годов появились фотовольтаические элементы, которые преобразуют энергию света, то есть фактически человек с солнечными батареями. В принципе, это тоже хватает. Количество ассортимента устройств тоже сильно увеличился, но, опять же, все варианты появились уже в 70-х годах. То есть это и кохлеарные импланты, это и ретинальные импланты, это помпы с лекарствами, и последний нейроимплант тоже уже в конце 70-х появился. В чем возникает проблема? Ну, вот сейчас считается, что самым перспективным вариантом будет у нас биотопливный элемент, энзиматический, как называется по-английски, или ферментативный. То есть что это такое топливный элемент? Топливный элемент — это тоже электрохимический источник тока, который обладает достаточно высокой удельной энергоемкостью, то есть, в принципе, может много энергии запасать, но в данном случае он берет энергию из глюкозы кровотока, преобразование глюкозы электрохимическое и получение из него электрической энергии происходит под действием фермента. Речь идет о глюкоксидазе и ее вариации. То есть эти вещи появились, первый такой вот прототип EBSS появился еще в 1960-х годах, но за это время до сих пор ни одного нормально работающего топливного элемента, который бы питал импланты, особенно нейроимпланты под действием, используя глюкозу организма, не удалось создать. Почему? У нас тоже работают в нашем центре над такими устройствами, но пока что у нас во всем мире ничего толкового не получается. Почему? Проблем есть несколько. Во-первых, когда мы влазим в кровеносный сосуд, у нас возникает проблема тромбоза, то есть обрастания этих самых штук. Тромбоз. Во-вторых, сами ферменты, они не очень стабильны. Они зависят от pH, они требуют постоянной температуры, поэтому когда человек заболевает, у него может все закончиться. Плюс происходит вымывание ферментов. Поэтому в итоге пока что это очень большая проблема, ее пытаются решать по-разному, ее пытаются решать, например, вариантом генной модификации, то есть модификация самомолекулярной белковой модификации фермента, модификации ферментами маломолекулярной, модификации ферментами частицами золота и так далее и тому подобное. Но пока что, вот, как говорят специалисты, не при нашей жизни это будет сделано. Но, тем не менее, на это тоже нужно обратить внимание, то есть этот вариант возможен как источник питания для нейроимплантов. Возможно, что-то удастся найти какое-то радикально новое решение, которое будет одновременно сравнительно дешевым, безопасным и стабильным. Но пока что, как говорят, даже биосенсоры, которые основаны на том же самом ферменте, глюкоксидаза, они стабильно работают 2 недели, 3 недели, но не больше, чаще всего. Вот, то есть это большая проблема, которая... Что можно еще сделать? Можно вернуться к батарейкам. Если мы говорим про кардиостимулятор, вообще про все стимуляторы, которые используют первичный источник питания, сейчас используют максимально возможные, максимально емкие цинк-воздушные элементы, потому что емкость, удельная емкость, это в данном случае единичная вещь. Конечно же, пока что больше всех нейроустройств используют стандартные литий-ионные аккумуляторы, потому что это максимально пока что допустимое, если мы говорим про перезаряжаемое устройство, максимально допустимая, возможно, достигаемая емкость — это 250 Вт-час на килограмм, это достаточно много. Вот. Вариант второй. Сейчас буквально 2 года назад были созданы совершенно новые фторид-ионные или лантан-фторидные аккумуляторы, которые позволяют теоретически достичь плотности энергии чуть ли не втрое больше. И вот сейчас в наших лабораториях мы начали работать над подкожно вживляемые фторионные аккумуляторы с подкожной зарядкой. То есть они подкожные и с дистанционной зарядкой. Заряжаются, такие варианты возможны. Ну и возможно, если мы будем имплантировать крупные устройства, требующие много энергии, возможно, возможно использовать топливные элементы, твердооксидные топливные элементы, которые можно заправлять быстро. Заправлять приходится газом, но, в принципе, это решаем проблему. Можно заправлять пропаном, и этого хватает, у них еще больше удельная энергоемкость. Поэтому вот такие вот проблемы, которые сейчас пока что не состоят, потому что большинство BCI и всех остальных используют стандартные источники энергии, потому что нет долгоносимых мобильных устройств, но к этому придется нам прийти. Спасибо, дорогие друзья. Если есть какие-то вопросы, на них отвечу. Такая вот постановка проблем, постановка вопросов, может быть, приглашение к коллаборациям, потому что у нас некоторые работы в этой области тоже ведутся. Спасибо. Thank you.
Okay, thank you. We have time for a question.
Есть время на вопрос, один вопрос.
Are there any questions before the next speaker?
Будут ли вопросы, прежде чем я передам слово следующему выступающему?
Okay, thank you.
Okay, thank you. And yes, just for future reference, people can speak in Russian or ask questions in Russian if they prefer. Obviously, if the speaker does not speak Russian, then that person will not understand you. Anyway, our next speaker is Lisa Okorokova, and please go ahead. Mm-hmm. I can see your screen. No problem.
Such as due to spinal cord injury, for example. So first of all, I'm sure many of you have seen great examples from the literature in which monkeys or humans were able to operate either a virtual environment or a robotic hand with their brain signals. And this is all impressive, but if you look slightly deeper into this, you will immediately realize that those movements are really not as great as what we humans can do with our biological hands. So for example, here the monkey in the virtual environment is only operating 2 degrees of freedom, the shoulder and the elbow. And here the woman with the implants is doing a slightly better job with 7 degrees of freedom, not only the arm, but also the wrist rotation and the aperture of the hands. Yet our biological hands have 27 degrees of freedom, and that allows us to do a very varied variety of tasks, including dexterous manipulation of objects. So the idea in brain-machine interfaces is to move from a few artificial postures, few degrees of freedom, into a continuum of hand configurations that in turn eventually could lead to dexterous intelligent behaviors such as handwriting and holding objects. Another thing that is really important in brain-machine interfaces is closing the sensory motor loop. What this means is when we get signals from the motor cortex, we translate them into movement of robotic hands, but then once the arm moves, we also want to know where it is and what it touches. So information about its position and about contact events should be fed back to the somatosensory cortex via a number of electrical pulses. So that way the subject will always feel what he's doing and what he's touching. To demonstrate this point, here is a video from our collaborators in which a human subject, is implanted with 2 arrays. One of them is in the motor cortex, and it drives the movement of a robotic hand. And another one is in the somatosensory cortex, and it delivers stimulation about the contact events with an object. And as you can see, with stimulation on the left, the subject is able to do the task much faster and more efficiently. And this concept has been established both in cortical brain-machine interfaces and in peripheral ones. However, there is also one other somatosensory sense, which is called proprioception, that has been completely ignored by brain-machine interfaces. So this sense tells you where exactly your limb is in space and informs you about movement even if you're not looking at your hand. So because there is no feedback about where your limb is at the moment, the subject has to constantly rely on their vision. And this is a problem, especially if the hand is occluded by an object or the subject is not paying attention to what he's doing with the hand. So to address these questions of increasing the number of degrees of freedom and incorporating proprioceptive feedback, we in our lab study non-human primates and the ways they move naturally, so the ways they reach and grasp objects. And we want to know how exactly neural signals translate into movement so that we can use these insights to create better brain-machine interfaces. So for that, we created a task in which monkeys were grasping 35 different objects while we were tracking their hand kinematics, cameras, and motion tracking markers so that we could infer up to 30 degrees of freedom of the arm and the hand. At the same time, we were recording activity related to the hand in motor cortex and somatosensory cortex. And here is one of the trials, several trials actually, in which the monkey is reaching towards the objects, and you can see those markers on the hand of the monkey that are tracked by the cameras. And if you can hear it, I'm not actually sure, but if you can, there's also a neuron firing in the background, and this neuron is really dependent on movement. So this neuron and many others are going to be used in decoding later. All right, so this is how the data looks. 3 example objects and the postures that I used to grasp them, and we get continuous kinematics from 30 degrees of freedom. And at the same time, we also record neurons from motor cortex in blue and somatosensory cortex in orange and red. And interestingly, the kinematics elicited by this grasping behavior was varied enough between objects that we can pretty easily discriminate between objects with far above chance performance. So what can we do next with those signals? We asked the question of what we can tell from those neural signals about the objects being grasped. So this is called classification, whether you can tell apart what object it is just based on neural population responses. And another question, which is complementary but much more complex, is whether you can continuously decode kinematics simultaneously from just based on neural responses. So I'm going to show you results from those 2 approaches, and generally they are pretty complementary. So just a proof of principle that we can do that with our neural signals, here is performance from motor and somatosensory cortex in terms of classification of 35 objects, and as you can see, even for a very small population, it's far above chance. And obviously it increases with increased population size. And a very similar result happens in continuous decoding, in which performance of all the joints is actually pretty high, so we can track continuous kinematics reliably. But the interesting question here is what we can do with that. So what questions can we ask? One of the questions was related to the nature of the task. So as you've seen in the first introductory slides, many BCI studies up to date were concentrated on reach, which is just transferring the finger or the hand from one point to another, whereas our task was related to grasp of different objects. And those 2 tasks are completely different biomechanically. So the purpose of reach is just to transfer from one point to another, whereas the purpose of grasp is to pre-shape your hands, all of your 27 degrees of freedom, to the conformation of an object. And because of those biomechanical differences, we thought that there might be also differences in the ways we need to decode for brain-machine interfaces. And we did find the difference. Historically in reach literature, it was found that it is much easier to decode velocity of the endpoint of the hand rather than position, so gray versus white bars over here. Whereas in the grasp, we did the same thing, comparing velocity and positions, and found that it's right the opposite. So positions are much better decoded than velocities. So that tells us that if we want to incorporate decoding on the hand and the BMIs, we might need to develop different approaches for the upper limb and the lower limb. Another observation that we found was related to somatosensory cortex. So before we go into that, let me give you a slight anatomical background. So here is somatosensory cortex in purple, and if you take a cross section over here and look at it, here's what you'll see. Area 4 is M1, and all this pink thing is somatosensory cortex, which is divided into 4 different areas, 3A, 3B, 1, and 2, and those areas differ in terms of inputs. So we know from single neuron studies that area 3B and 1 generally receive inputs from receptors in the skin that respond to gentle touch. Area 3A, on the other hand, receives inputs from proprioceptors located in the muscles and joints. And area 2 is a higher order area, and it receives inputs from all the 3 other areas. So in our recording, we were lucky enough to have neurons in all of those 4 areas. So we split the populations into 3 categories. One, area 3A, which is about proprioception. Second, area 1 and 3B, about touch. And third, area 2, which is who knows what, a combination of those probably. And we compared decoding performance for those 3 populations. And in both classification and decoding, we can see that area 3A performed much better than either area 2 or tactile neurons from area 1 and 3B. The same result holds for continuous decoding, where area 3A can track kinematics much more reliably. So what this says is if we want to incorporate proprioceptive feedback, we would want to stimulate probably in area 3A during movement. What is interesting, though, is that all that results hold before contact with an object. During preparation and movement, area 3A is better. But once the contact was established, suddenly area 2 becomes much better at decoding. What this says is that area 2 is probably, because of its higher order, incorporates information about both touch of the object and the conformation of the hand around the object. So it carries much more information about what exactly is being grasped. And what we think that could lead to is our ability to discriminate objects just by the sense of touch. But this is a completely different story for the next time. So to sum this all up, here in this talk, I've showed you that we can decode in principle high number of degrees of freedom of the hand that can be later translated in the commands of the robotic hand. For now, this result is limited to the fact that we do not really have very good robotics and sensors, but we're getting there. So there are lots of research on how exactly to make robotics move all those degrees of freedom simultaneously, and also how to incorporate as many sensors as possible on the surface of the hands. Another thing I showed you is that if we want to provide proprioceptive feedback, we would need to go into area 3A, where we have most information about hand movements. Unfortunately, now it's not possible to do in humans, because the only array that is approved for the humans is the UT array, and as if you can see, the pins are very small. They're only about like 1 millimeter long, which is not long enough to reach area 3A. It's deep in the sulcus. So the only thing we can do now is stimulate area 1 or maybe slightly area 2. But the technologies are moving forward, and we saw Neuralink probe with very long shanks, and also there are other probes that are okay for primates, and using those can be a big step forward to provide proprioceptive feedback to the patient during BMI. So fingers crossed. And with that, I would like to say thank you to my lab, and in particular my PI, Slim Vansmea, and my co-PI in this project, Nico Hatsopoulos, as well as all the students and people from the University of Pittsburgh for providing the video of human BMI subject. Thank you, and I will take any questions.
Yes, thank you. Are there questions?
Hi, I have a question. Very, very interesting talk. I was just wondering, since you said that area 3A from somatosensory cortex, it receives the information from the skin sensors. Is it the information that you decode, is it maybe decoding of the texture of the object rather than the shape of the object, or the texture was similar across the object that you were using?
I'm sorry, you're asking about area 3A or in general, or all somatosensory cortex?
3A, because you said, I think, that your decoding was best if you took the neurons from the area 3A, right?
Yeah, it was best during movement. So that means that this area has the most information about kinematics of the hand. And there is no contact there. This is prior to contact. So the only information we get is how the limb is moving.
Okay.
Yes. Relating to this figure. And yeah, area 2 has some information about the kinematics as well. So the performance is above chance. And tactile units, I think what is happening here is when you move, you stretch the skin, and because of the stretch, tactile efferents also activate, and that's why it leads to above chance performance of the decoder as well.
Okay, thank you.
Thanks.
Okay, thank you. Is there one more question?
Mm-hmm.
Okay, then thank you. I also really enjoyed your talk and your well, I'm curious to talk more about some of this, but certainly I agree with, in the beginning of your talk, we don't want to imply that only non-invasive or non-implanted directions are useful, and so I'm curious to see more. And that might be a good segue onto our next speaker, who I'm pretty sure is ready because she just asked a question. So Please go ahead, Yekaterina.
Thank you.
I can see your slides.
Can you see the screen now?
Yes.
Okay. Hi, everyone, and thank you very much for giving me the opportunity to present my work to you. And I'm studying the dynamics of reciprocally inhibitory neural circuits called half-center oscillators. And half-center oscillators typically consist of two non-oscillatory neurons or group of neurons connected by reciprocally inhibitory connections. And if they wire together like this, they can generate rhythmic output in the absence of any rhythmic input. So half-center oscillators are the building blocks of many central pattern generating networks that produce rhythmic motor patterns, such as, for example, chewing, swimming, walking, and many other different types of patterns. So despite the apparent simplicity, those circuits are high-dimensional circuits and can generate a wider range of different outputs, ranging from synchronous activity that you can see here, antiphase spiking, and antiphase bursting, that's, as I already mentioned, called half-center oscillators. And during my talk, I'll be focusing on this particular pattern of activity, which is really important for this antagonistic motion pattern. So our overreaching goal is to understand the mechanism of motor pattern generation and consequently how the movement is initiated and generated, and to gain insights into how neural networks are able to produce reliable but yet flexible output in order to adapt the activity to environmental needs and challenges. And this is probably very relevant this year because we face a lot of challenges and we have to stay resilient. And to be more specific, the question that I will be trying to address is how this neural output is shaped by the intrinsic properties and altered by modulation and external stimuli or perturbation. So one way of exploring the mechanism by which synaptic and intrinsic properties interact to shape the output of the circuit is to have a control over these critical parameters for the output of the circuit. So I used the dynamic clamp technique in order to connect biological neurons and a computer and generate the hybrid network that can produce these half-center oscillations. So briefly, the dynamic clamp technique is the technique that uses this real-time interface between the computer and biological neurons or group of neurons in real time to simulate nonlinear currents or to create a hybrid network. So how does it work? So we intracellularly record the activity from a neuron, then amplify it and pass it to the software that contains a model of a desired current or multiple currents that depend on the voltage. Then we generate the current and inject it back into the neuron in real time with the sub-millisecond resolution or into another neuron to create this artificial connection between the neurons. And so the neurons that I'm recording from are from the stomatogastric ganglion of the crab. And here you can see the picture of the stomatogastric ganglion, and little circles here are the neurons. So the neurons, when they pharmacologically isolated from from other inputs and from other neurons, they just pretty boring, they're silent at baseline. And by creating this reciprocal artificial connections through the dynamic clamp and adding some positive feedback in a way of adding hyperpropagation activated inward current, I'm able to create this alternating burst of activity. So previous theoretical studies has shown that there are two main mechanisms that produce alternating bursting pattern of activity, which is escape and release. And here you can see the voltage traces from two biological neurons, and horizontal red line is the synaptic threshold, which corresponds to the half activation voltage of the synaptic function. So the synaptic escape mechanism is characterized by the inhibited cell depolarizing above the synaptic threshold and thus terminating the activity of the active cell. While the synaptic release mechanism is characterized by the depolarized cell falling below the synaptic threshold and thus releasing the second cell from inhibition, allowing it to rebound. And so by shifting the synaptic activation curve or synaptic threshold, it is possible to switch between those mechanisms, and that's what I did using the dynamic clamp. So we explored the parameter space of the synaptic current conductance and of the hyperpolarization activated current conductance for the half-century oscillators with different mechanisms. So I varied synaptic and H conductances in steps and generated these maps where the color corresponds to the frequency of oscillations and the white space corresponds to the parameter sets for which there were no stable oscillations. So as you can see from those maps, the parameter space for which stable alternating bursting pattern of activity are quite different for release and escape mechanism. With the escape mechanism, the half-century oscillators mostly exist along the diagonal, and the synaptic and H conductances have to be pretty tightly correlated to create the stable oscillations. While for the release case, the half-century oscillators are mostly in the right top corner of the map, and parameters don't have to be as tightly correlated. And interestingly, the frequency is conserved along different directions for the release and escape case. It's because the increase in H current produces the opposite effect on the frequency of oscillations. In escape case, increase in H current increases the frequency of oscillations, and in release case, it decreases the frequency of oscillations. And as you can see on this example, voltage traces. In real biological systems, half-century oscillators are likely to rely on the mixture of mechanisms and not just on pure release or escape mechanism. And additionally, it's been shown that neuromodulators are able to shift the synaptic threshold and thus affect the mechanism of oscillations. So we were interested in to see how the maps look like for the mixed mechanism that corresponds to the intermediate thresholds. So here you can see the evolution of the synaptic and H parameter space as the synaptic thresholds gets more hyperpolarized. So I'll play it one more time. So here are the maps for release, escape, and the different balances of the escape and release mechanism. And interestingly, you can see that evolution is not very trivial. With the mixed mechanisms, there are very few half-century oscillators, and they only exist at the very edge of the map. And most likely it happens because in real life, biological neurons, they're never identical with respect to the intrinsic properties, meaning that the balance between the mixture of the mechanisms will be slightly different for two neurons, leading to the situations when for some parameter sets, one of the neurons will be stuck constantly firing and always suppressing the other neuron. And that's why you have this kind of situation. So this tells us that the mixed mechanism, even you would think it probably has the bigger range because it can move in either direction. It would be more robust. It's in reality turns out to be less robust to either of the release or escape mechanisms. And based on these maps, we can make some predictions in terms of how various substances that affect some of the properties of these currents, how they will, for example, serotonin or dopamine, how would they change the output of the circuit? So after getting some idea on how intrinsic and synaptic currents shape the output of the circuit, we investigate how circuits respond to external perturbations, and temperature is one of the natural perturbations to consider as it affects all the processes in the organism to various degrees. And for the survival of the animal, it's very important for the center pattern generators to be robust to these temperature changes. So dynamic clamp allows me to independently implement the temperature dependence in the synaptic and H currents and to study the individual contributions to the output of the circuit as the temperature changes. So I created half-century oscillator with the escape mechanism at 10 degrees Celsius, and then I slowly ramped up the temperature to 20 degrees Celsius. And as the temperature being ramped up, you can see that both neurons hyperpolarize with the increase in temperature, so that the top of the slow depolarization gradually gets closer to the synaptic threshold, so shown in red here, meaning that the mechanism of oscillation switches from the escape mechanism at lower temperatures to the release mechanism at high temperatures. And based on what I showed you previously, at different temperatures, it will have different responses to other perturbations or changes in the current compositions. And what you can also see remarkably that the frequency of oscillation stays constant even though all the processes, all the intrinsic currents and the time scales are changed dramatically. And only when the neuron switches to the release mechanism, you can start to see the increase in the frequency. And as you further ramp up the temperature, the half-century oscillator will break down because the stable oscillations are only found when the synaptic threshold is within the envelope of the slow wave. So this raises the question then how these circuits maintain robustness as the temperature increases, especially if they operate at the release mode. And turns out there are multiple mechanisms of robustness ensuring stable oscillations at a wide range of temperatures, and one of them is neuromodulation. And it's been previously shown that a lot of different neuromodulators and neuropeptides, they activate a current with the same voltage dependence, which is also similar to an MDA voltage dependence, and it's called IMI. So I could use the model of the current and implement it with a dynamic clamp to inject in biological neurons and study its effect on the circuit output. So I created the half-century oscillator in the release with the release mechanism at 10 degrees Celsius and quickly ramped up the temperature to 20 degrees Celsius. So as the temperature being ramped up, the oscillations attenuated in amplitude and stopped existing at 20 degrees Celsius. But by aiding this neuromodulatory current, I was able to restore the oscillations. Though the simple depolarization, such as constant current injection, could also restore the frequency of oscillations because all you need to do is to depolarize the neuron above the synaptic threshold. However, this stimulus is less effective as neuromodulatory current because you can see that the overall oscillations are more depolarized, meaning that hyperpolarization activated current is less active and the oscillations would be less stable. Finally, it turns out that there is an inbuilt mechanism of the stability for the circuits. So all the conductances, including this artificial conductance that I generated, they depend on the temperature. And up to this point, I didn't include the temperature dependence. But here I assume that the Q10 is equal to 2, meaning that the conductances increase 2 times as the temperature increases by 10 degrees Celsius. And as you can see, doing that, we also restore the oscillations and dramatically increase the amplitude, but reduce the frequency of oscillations, which is kind of opposite to what you see in biological central pattern generators as you increase the temperature. But the frequency could be increased by taking into account that the temperature also increases the timescales of all the processes. So by increasing timescales of H of synaptic current 2 times, I was able to create very stable oscillations with the high frequency at the high temperature. So just to summarize it briefly, increase in temperature produces opposite and differential effect on the frequency of oscillations and release and escape modes. And release mechanism-dependent half-century oscillator is less robust when temperature increases. However, addition of neuromodulatory current can rescue the oscillations. And with that, I would like to thank my whole lab for help with the project and on the inputs. And of course, I would like to thank Eve, has been a wonderful mentor, and Peter, who's a technician in our lab and who works together with me on this project. And thank you for your attention.
All right, thank you very much. And are there any questions?
I see there is a question in the
Okay,
chat.
maybe I'll ask. No, can I?
Yes, please.
No, just very naive question. I'm sure that you discussed it. You came from the very excellent actually group. You talk about fictive locomotion, but in real situation, of course, frequency of oscillations highly depends on sensory feedback. So it's a bit, to me, too much artificial. If I want to apply it to, for example, spinal cord injury, whatever. Some comments about it?
Yes, I think the sensory feedback essentially affects the neuromodulatory system, and obviously a number of different neuromodulators, they will affect the frequency of the half-century oscillator too, depending on what kind of currents they activate. So for example, of course, you want to be able to adjust your walking speed from like walking to running, and by releasing these modulators, you can modulate the frequency of oscillations. So for example, by serotonin, and depending on the mechanism of oscillations, you can either decrease or increase the frequency. So kind of my idea was to try to dissect the circuit and understand how how would you adjust the frequency and how you would modulate this output of the half center depending on what is the underlying mechanism.
Okay, thanks. And yeah, we do have a question in the chat room, but we should move on to the next speaker. And so people are welcome to ask and answer questions in the chat room. Please remember, just in terms of time, I'd mentioned before that we're going to take longer than planned for part 3. We had a couple additional speakers near the end, and we're not so bad given that. And our next speaker looks like he is here. So just to make sure, Artur, are you available?
Yes.
Yes. Okay. So please go ahead and share your screen.
Видно, да?
Yes, I can see your screen.
Коллеги, я буду говорить на русском. Извиняюсь, что...
I'm going to be speaking Russian. It will be easier for me to speak Russian. Let me introduce to your attention our work devoted to stimulation of the spinal cord in rehabilitation of patients after the spinal trauma. But in the future, this technology can be used with BCI for future progress of our project, for the use of it in clinical practice. Let me start by saying that when we stimulate the spinal cord, when we treat chronic pain syndromes, we show an example of a patient who had pains in her loin, and after the stimulation for a few hours, the patient removed her crutches, and there was a significant reduction of the pain syndrome. And here we started with the use of to treat spasticity, and it was due to the fact that here in Russia there are difficulties in the use of ITB technology, which is the golden standard in the world. It's because in Russia there's a big territory, lots of remote areas where patients are sort of locked. For them to travel to a bigger city, they have to move, they have to spend lots of days on the road, but this is a technology with lots of complications and side effects, and the patient has to be near a hospital for the first 24 hours if there is something wrong. If something is wrong, when spinal stimulation was just invented in the 60s and 70s of the previous century, spinal stimulation was used quite actively to treat spasticity. But when pumps were invented, they disappeared, and I don't think it was justified. Disappearance of this technology. We conducted a study. Yes, of course, the pumps are more sensitive to spasticity, but there are lots of patients that responded well to simple spinal stimulation. And let me remind you of our first work, and where we showed comparative study of spinal stimulation of ibuprofen with homogeneous groups of patients, and we came to certain conclusions. According to those conclusions, when there's a clinical break in the spinal cord, and whereas there's not obvious spasticity, they had a good response to the spinal stimulation, and this response was quite comparable with the response when we use the pump. There was a group of patients with whom we tested the stimulation. If there was positive result, we implanted the stimulator. Otherwise, the patient used the standard protocol for the use of ibuprofen. And this is a clinical example of a patient. She has a really severe spasticity. You cannot unbend or flex those legs. She cannot really move in the wheelchair. She cannot really sleep very well. On the right-hand side, she is on the left-hand side. She is before and the procedure, and after. On the right-hand side, she is with the implanted stimulator. Now I can move her legs on the right-hand side much easier. And we kept progressing. We kept developing our technology. But we faced the situation that the rehabilitation is all about damage to the spinal cord. How pronounced is that damage? Is this the anatomic break or just incomplete trauma? But they found out earlier that in 90% of cases, when we have a complete anatomic break, the patients still have some tissue or fibers left that are still connected to the cerebrum. And based on that, we discovered that some center of working activity is there, and when we launch it, we can get some kind of locomotive activity. Before me, there was a presenter who showed a baby, newly born baby, running on the treadmill when held up. And the center of working activity, if we raise the baby in our hands, we see how the baby begins to move the legs. At the initial stage, those movements are not very nice. Then the brain learns to control those movements, and the baby begins to walk. And this is due to the work of that walking activity center in the nervous system. And in recent years, there's active work in that area. There were a number of articles confirming that when you stimulate this walking center, you can adjust or restore some kind of control of the brain over one's movement, even with patients who originally had a clinical paraplegia, full anatomic break. And last year, together with the Kazan Federal University, And the Mayo Clinic, we did the first clinical trial like that in Russia for the first two patients. The study design is shown here. I'm not going to stop there. Stage 1 was the selection of the patient, physiological studies, then there was a stimulation of the spinal cord, then we implanted a testing electrode, and then implanted the permanent stimulator. This is how we selected patients. We had 2 subjects for physiological testing. We confirmed that the patients had clinical anatomical break of the spinal cord. We used the technology of mapping of the spinal cord, which is nowhere described. That's a very interesting procedure. We're trying to find the optimal location of the electrode along with the spinal cord. You see there was 2 different patients. That position, that location was different due to their specific anatomy. Last year we had this project. We were able to do some serious work of combining efforts of a number of large universities. We had a surgery on 3 patients, and the 3rd patient was there as well with the spinal cord tumor. And these are some of the videos. Originally, this patient was paraplegia, had no ability to move at all. This patient was not in the spinal group, but his spinal cord tumor has been removed, and after we implanted the stimulator, the first time in 20 years, he could move his feet.
Пример некоторой физиологии, то есть.
So here you see some physiological examples. You see how the patients are now able to execute cyclical motions when suspended, pre-implantation, 1 week after the implantation, a month after implantation, and 2 months after implantations. Patients are usually able to gain control over their movements and to even do this movement voluntarily. So we managed to kickstart this gate center, but unfortunately we still cannot truly manage it, but we do hope that BCI technologies will be very useful for us in this regard. A lot of you know that there are BCI interfaces that allow people to control an exoskeleton, which had been developed in the Higher School of Economics. You have probably all seen the video by Professor Lebedev. This video shows that we can predict movement in monkeys using BCI technologies. And of course, everybody saw the presentation delivered by Elon Musk a month ago, where they predicted movements in pigs. When it comes to spinal stimulation and possible convergence with this technology with BCI, I think that it opens up a lot of very interesting prospects. Of course, a number of theoretical problems remain to be resolved. We need to carefully approach experiment design. We have to be extremely careful about devices, because unfortunately we still don't have a device that we can use on human subjects. Well, at least what I mean, these devices are not available in Russia. In the United States, there is access to these devices, but unfortunately there are no Russian companies that manufacture electric stimulators. And as a pinnacle of my report, I would like to tell you about the deep brain stimulation technology in patients with Parkinson's disease. You see that non-invasive BCI technology was used in patients with exoskeleton. Another positive way to use this technology to stimulate the spinal cord is using BCI in telemedicine. Maybe we can have a possibility for remote management and remote troubleshooting of this technology. You know, a lot of the patients couldn't travel during the COVID epidemics. Here you have one of our patients who had this device implanted back in 2016 to address severe spasticity. So we tried to troubleshoot the device remotely, and we managed to be really successful. We managed to initiate the gate center by stimulating the foot on the contralateral side, which goes to show that probably this patient doesn't have a full anatomical rupture, and this patient can look forward to achieving good results. So this is our team that works with me, and this is our university. Thank you very much.
Okay. All right. Well, thank you for that. And are there any questions? Okay, and again, people are welcome to ask questions and answer in the chat room. So I see people are doing so, and that's good. And then we're on to our next speaker, who I see is here and ready. So Igor Lavrov, please go ahead. Hello, Igor. I can see you, but you are muted.
Okay, can you hear me now?
He just did.
Yes, yes.
Oh, awesome, awesome. Thank you. Thank you. Let me share screen now. And okay, is it okay? It works. Okay. So anyway, I just want to start with I want to say thank you for introduction. It's a really great conference, and just want to briefly comment last slide from Artur's presentation. This really interesting case, patient with complete tetraplegia demonstrated rhythmic response and on stimulation.
I cannot see your slides, excuse me.
Okay. Can you see slides?
Yes.
No?
Right now I just see you and not the slides. Maybe that is only me.
Let's see. Let's see. Strange.
It might be only me.
Okay. How about now?
Right now I only see you and still not your slides.
Okay, let me try to share screen again.
Okay.
Okay, how about now?
I still only see you. Can anyone else see his screen?
No.
Strange. Because I'm pressing sharing screen, green button here. And I actually see that desktop 1. Okay.
Wait, now it's just started. Now I can see it.
Awesome, awesome, thank you.
Okay, go ahead.
I think it was on my end. Some mistake with software. Anyway, so is it okay now? Awesome.
Yes, so, right now it is great.
Awesome, excellent. So again, I just want to say that this case with tetraplegic patient is quite unique because he was able to control some rhythmic activity, initiate and terminate when electrodes have been placed in the lumbar segments, and he got very high level of cerebral injury for almost 10 years. So my talk will be related with spinal cord interfacing. And I will try to summarize what we're doing and how this could be connected with previous talks. So I want to start with a question that my son asked me a long time ago. Basically, he asked me how those guys could walk when this movie just came out, because they have so many legs, and especially those guys. And I guess the question here that our brain is not really equipped, like we discussed yesterday, to deal with multiple arms or legs. But in a matter of fact, we still using multiple segments when we walk, and we don't even think about this. So our motor control is pretty much organized the way we process multiple sensory inputs and trying to produce the most efficient motor outcome. And most of previous talks, of course, been focused on BCI and some level of recording and controlling some robotic devices and providing feedback to the brain. So what I want to emphasize, some speakers mentioned that most of the activity could be extracted from those areas. And in the same time, even stepping or some rhythmic patterns could be extracted from cortex, but taking activity doesn't mean we can control those patterns, right? So because of this issue, we can't really use most of currently available BCI to flexibly control rhythmic patterns like stepping, running. So I want to give you another example. In clinic, we see sometimes patients who have epilepsy, and when they have seizure, they may develop some level of rhythmic activity, like walking or chewing or lip smacking. In this case, we also can see some areas in the brain, like, for example, in premotor cortex for locomotion, related to this type of rhythmic activity. And some studies show that if we stimulate those areas back, it cannot produce this rhythmic activity. It must go through epileptogenic zone first. So that means likely we have some pattern generators located much deeper, integrated with this complex, which actually have to be interacted by somehow. And again, since we can't really measure this, I'm trying to focus my talk on how we can get approaches to pattern generators primarily on spinal cord. So the idea of central pattern generator, I think, was introduced initially by Graham Brown and acid circuitry that control flexion extension in some rhythmic pattern. So I think it was one of the first diagram explaining what is CPG. And there are, of course, multiple examples of CPG, and I want to show you one that I think one of the best, because it's very clear that here we have just about 3-4 spinal cord segments. And when we add some pharmacological agents, we can control this activity. And we did multiple studies on this model to understand specific receptors which play a critical role in this activity. And right now, most of the species, and even a human, we know, have this type of network. So CPG could be located in one segment and also distributed across multiple areas of the brain. What is critical, CPG is under consistent sensory control. So in most of the cases, sensory input is the most important part to initiate and to modulate central pattern generators. So most of my work for the last 20 years has been related to interfacing spinal cord in a way to produce some access to this circuitry. So initially we did multiple studies on a cat model to stimulate different areas from MLR in the brain, which coordinate multiple CPGs and different parts of the spinal cord. At that time, I think most critical finding was that we found a capacity to provide local stimulation and activation of circuitry with epidural and interspinal stimulation. In this case of epidural stimulation, we activate very local segments and can get activity in just hind limbs in the cat. So again, in this system, we activating locally just a few segments and get this local CPG. So another approach, interspinal stimulation, could be used to activate more complex circuitry. Here we put electrode in a specific area, which project fibers all the way up to the brain, to MLR area, and activate forelimbs and hind limbs at the same time. So, and this results helps us to understand more about how spinal cord organized. And since that moment, we've been focusing primarily on epidural stimulation because it's less invasive. And as we know, primary activates through the CSF dorsal roots. So we've done multiple rodent studies, primarily at UCLA at that moment. And I want to focus just on one study that quite close to BCI approach. So my colleague Park got suggested to bridge the spinal cord injury by taking activity from forelimbs in rats, amplify activity, and recognize pattern. And then as soon as we see repeat pattern, we could send signal below the injury. So rat in this case can walk again. This example of kinematics and imaging. In this case, rat just staying, so no forelimb activity and no hind limb activity. And when rats start to use forelimbs, it sends signal to circuitry and activate S1, in this case, a segment to provide adequate support for initiation of stepping. So again, in this case, we have dealt with very basic non-specific activation of circuitry with just one electrode. So based on rodent studies, several centers started to use epidural stimulation to initiate type of rhythmic activity and volitional control in human subjects. The main finding out of the studies that patient with motor complete injury regain some level of volitional control. This example of patient implanted at Mayo Clinic, and on the first stimulation we've been able to let him volitionally control some movements. So in this case, I asked him to induce some type of biking activity, and he's able to slowly increase intensity, speed. He can stop, he can modulate activity very well. So what is important here, in this case, we use just a midline position of electrodes. When we shift electrode to one side, like here, we can get primary his control over right leg, but he can control left leg same way. When we move electrode on other side, we can get control for left leg, but not for right leg. And again, this patient has age A, so he has no motor control without stimulation and no sensory control. So he's able to regain this control only when we provide certain facilitation with stimulation. And again, this is still gives us some level of specificity, but not enough to what we want. So we decided to go to peak model, and Demens and Carl helped me a lot with this study. So we actually use swine model, because anatomy-wise it's much closer to human. And you can see here, even if you just simply move electrode across midline, as soon as we come close to the roots, it's basically this area, we have very strong muscle response. As soon as we come in the space between roots, and you may see in a few seconds when the electrode will be here, the response goes down. You can see it now. And it was very consistent. And the issue is in swine or human or monkey, it's very hard to see what is under dura, because it's quite thick. So this is actually a good technique to evaluate where we are. And this example of data, as soon as we put electrode on top of the root, we have huge responses. As soon as between, it's very low. So basically, we can say that if you move electrode in just 5 millimeters, we have huge difference. But if you move electrode in 3 centimeters, we may have no difference at all. And again, all muscles pretty much involved in this response. So when we realize that we have to be much more specific with our stimulation, we also realize that there is no single study on human spinal cord anatomy. And indeed, there is at that moment no actually studies being performed this way. So we spent quite a bit of time to get very precise anatomical data from 9 cadavers. And we found that both dorsal and ventral roots have very segment-specific orientation, which is different for cervical, thoracic, lumbar segments. And what is really cool, the variations across all the segments was very consistent across all subjects we tested. So basically, those data likely could be expanded to the whole population. So we also did correlation between spinal cord measurements and bone marks to provide some level of navigation approach, where you can use CT or fluoroscopy to reconstruct the spinal cord anatomy. And this is pretty much where we are right now. We're trying to use this human mapping to develop a navigation system to insert conventional electrodes or some type of pedal electrodes, which are also important to adjust if you know exact anatomy. And we're also trying to develop segment-specific electrode array to be more precise in our interfacing. So I want to say a little bit about how we can record from spinal cord. Overall, there are a few techniques. One is, again, electrical activity that we can record with electrodes. Carlos, actually, before he joined our team, he did excellent work on a cat back in Mexico, where activity from the brain, kind of scratching activity from the brain, propagates across multiple spinal segments and can be recorded as a pattern and inform our knowledge about circuitry related to this activity. Another way to record what's happening in spinal cord is evaluation of hemodynamics. So in this case, we used so-called functional ultrasound, where FUS transducer can send and record sound waves in a very fast and dense way. And in collaboration with Dr. Song, Dr. Tang, Dr. Chen, we did this first study where during stimulation of the spinal cord, we identify very local changes in the spinal cord hemodynamics. What is cool here, we realized that this technique is more sensitive than EMG or other electrophysiological approach we can use. So here's EMG, and we have pretty much no response, just a little bit. And we have a very clear response on FUS. And this is another example where we send those bursts of stimulation, and you can see immediate response in hemodynamic. So we also found that with this approach, hemodynamic changes really depends on parameters of stimulation, like different frequencies. So we can really talk about neurovascular coupling in spinal cord with stimulation. So those two techniques pretty much noisy, and we did a lot of work to reduce noise to get it done.
Шум.
But our current work is primarily connected with clinical trials, and we always trying to think about what potential way we can interface. So it's all about closed open loop spinal cord stimulation, which again we're trying to collaborate with colleagues to integrate this with brain-machine interface and interfacing with some peripheral devices. And this could be also looped with feedback control and some coordination with homotherapy, rehab with epidural stimulation. And as Artur just mentioned, it could be integrated with some telemedicine and remote patient monitoring. So again, all those levels are quite important for future steps. And I want to emphasize that in this scheme, we have a great potential to interface spinal cord using those specific targets, and specifically dorsal ventral roots. So I'm almost done. I just want to show maybe just last few seconds of this video. Let me see if I can do it. So, okay, but somehow I can't really. Okay, now I can do it. So I just jump it right here. It's just something we did a few years back. We tested different type of electrodes to insert in spinal cord with different materials. So this is a type of plastic material. And this actually was probably one of the best electrodes made by Dr. McCreary based on parts of neuronexus device. And again, it produced very good insertion and stable position. What I want to emphasize here that we still have access to different areas of spinal cord with multiple techniques, but we may get better options to control and record from spinal cord if we get more precise interfacing with dorsal and ventral roots. And I think it's something we will improve in the near future. So just to finish my presentation, I want to rephrase my initial question to what BCI and spinal cord computer interface should like to control something very useful and complex, or maybe to control something entirely not useful like this machine in Burnt Man. So thank you so much, and please, any questions, I'll be happy to discuss.
Maybe can I ask? It's Yuri. Just, you know, if we have time, just, no, Igor, thank you very much. Actually, interesting, very interesting. I'm a bit curious about redundancy and flexibility of the spinal circuitry. For example, maybe you're familiar, you know that there is a recent paper of Edgerton in the Journal of Neurophysiology. So what they found that if you repeat the movement, so they labeled interneurons, if you repeat the locomotion, this is at the same speed. So only 20% of interneurons are the same. So just simple repeat. So it means that you can produce the same locomotion movements with different interneuronal circuitries in the spinal cord. So there is a lot of redundancy. And I wonder, with your electrical stimulation, when you repeat the same stimulus, do you observe sometimes very different responses, or they are quite stereotyped?
I think it's an excellent question. I think it really opens big discussion. I think part of your question, to what extent we understand what we are doing and how much difference we can see with all variations in parameters we use, right? And functional state of the spinal cord. And I think this type of information still need to be classified and analyzed. For example, we may start stimulation when we just implant electrodes to get good response in patients with a high voltage. Then over time, we can decrease it to very low intensity and it still works, right? Then sensor cues is very important. Like Artur mentioned, for these patients with tetraplegia, we've been looking for the trigger zone. Usually those patients, even with paraplegia, they easily to initiate some volitional control when we look for some sensor input in addition. Like we can ask him to control right leg and we can stimulate with pen or some cotton ball skin, right? And this can facilitate sensory feedback. So combination of those factors is probably very critical, but to what extent this help circuitry to produce motor pattern is really different, depends on functional state. Maybe because we have a lot of redundancy in circuitry, it helps to adjust and to really provide such flexible mechanism. Another question here, and we're trying to address this right now on animal experiments, what level of circuitry is really critical? For example, Dr. Edgerton, this paper, been focusing primarily on circuitry below the injury, right? On circuitry related with CPG and those. But in fact, I think most of the data we have right now showing that even in motor complete injury, we have those fibers crossing injury, right? And even if you put scaffold after complete transaction, we see a lot of fibers growing up and down. So over time, we likely have to talk about transvisual network, circuitry which distributed across multiple segments, not just below, but also above the injury. And it's also at some level, not just redundancy, but level of connection between multiple segments to improve this pattern. So I guess like our brain design based on parallel connections, right? Same should be in spinal cord. Yeah, I'm not sure if I address a question. I'm just trying to speculate based on what.
Thank you. In any case, yeah.
Okay, yeah, and it is an ongoing question, of course. So.
Yeah.
Okay, so we had a speaker who did not speak earlier today, and so that speaker is now available and will move on to be our last speaker. So thank you all for staying with us so far. And after this last speaker, we just have some brief announcements from the organizers, and that will be that. But again, I encourage people, if you have questions, there's the Neurobar, or you can contact the speakers or chat. Okay, so our last speaker is Andrei Kuznetsov, and please go ahead.
Здравствуйте. Слышно?
Hello.
Андрей Кузнецов не смог, поэтому я его жена.
Andrei Kuznetsov was unable to take part, and that's why I'm his spouse, his wife, and I'm going to be replacing him.
Okay. Yeah, I can see your screen.
It's full screen. Yes. Буду выступать на русском языке. Так. Наш проект — разработка реабилитационного комплекса на основе VR-технологий и электромиографии для восстановления двигательной функции верхних конечностей при центральном парезе различной этиологии. Более 10 миллионов случаев инсульта. В 2013 году насчитывалось более 25 миллионов лиц, перенесших инсульт, живущих с его последствиями.
Извините.
Ага.
Да, Дарья, говорите немного погромче, пожалуйста, вас плохо слышат переводчики.
Ага, хорошо. В последние десятилетия широко используется показатель
In the last decades, there was this global burn disease of how many years were lost, and it's 113 million years. According to official statistics in the Russian Federation, every year we get more than 400,000 cases of stroke, and most of them are quite severe. And people lose their functions. This is our hardware-software set. It has virtual reality goggles, two-channel electric myograph, virtual environment software, and a software to synchronize their work. The basic program is open BCI, and accordingly, in the virtual environment, we visualize the extremity that we want to rehabilitate. What's new about it is that we combine VR technology and electric myography by visually demonstrating the virtual reality movements, which activates the mirror neurons, and through the attempts of patients to make some movements, this method activates biological feedback. Thus, new motor forms of movements are formed. Here we show the design or pipeline that describes the entire process of rehabilitation. In the beginning of any study, we calibrate the device. We register electric signal amplitude in the calm state at under load. The amplitude is proportionally dependent on the number of motor units in the muscle. Then rehabilitation starts after we register the signal from the muscles that participate in the movement. The signal is processed. Depending on the amplitude, you change the visual image of the rehabilitated extremity. The amplitude signal from the muscles and the amplitude of the movement are directly proportionate, and the virtual image will appear only if the patient is trying to make this movement in real life. And the movement in virtual reality match the movement of the healthy limb, even if in real time it's impossible. Thus, the patient actively participates in the process of rehabilitation. When we use this set of equipment, all sorts of plegias and paresis of upper extremity, severe and acute, subacute stages of stroke. This rehabilitation can be done in inpatient hospitals when the patient is still there and the compliance is better. And we use it with paresis of upper extremities of under 3 points and a chronic phase of central nervous system disorder. You need sufficient cognitive abilities to understand the doctor's instructions. The patient shouldn't have spastic limitations in the rehabilitating extremity of no more than 2 points under Ashworth scale. He has to have vision to send signals from the VR, and the patient should be motivated. And when we don't use it, is the overall severe conditions, high temperature, fever, hemorrhage, endocrinology disorders, and cardiovascular diseases, psychic disorders, spastic limitations of more than 2 points, and epilepsy. This software hardware complex can help us deal with such issues as adjustment of the movement of upper limbs, helping to normalize them, make them as close to normal as possible, to normalize coordination properties and proprioceptive feelings, ensure contracture prevention, activation of neuroplasticity, and forming new motor formulas of movements, and improvement of the movement of the damaged extremity. There has to be daily sessions. The patient has to be motivated to get the result. You have to individually fine-tune the equipment for every patient, and the load should match the data that we get during the calibration. This hardware software stack is better than video, the device's video tracking. It intensifies biological feedback. The patient is actively involved in the process at all stages of rehabilitation. Because of the direct relation between the amplitude of the signal and the speed of visualization of movement in VR. And also we improve motivation and adherence of the patient to real life, since in real life they cannot make those movements full scale. And that's it from me. Thank you for your attention.
Добрый вечер еще раз. Hello.
Good evening once again.
I'm sorry, I will turn on the video. Brendan, are you here?
Yes, I'm here.
Yeah. So, Brendan, will you tell something?
No, I was just, my comment was that at the conclusion, we wanted to mention, of course, that, you know, other events like Go and Chat, and you had an announcement to make as well, but I didn't know if there were also other questions or discussions, so I thought I would wait a moment.
Okay, so maybe I can go with my announcement. Yeah, thank you very much. So just a very short one, because it's a little bit late. Tomorrow we kindly invite everyone for a series of workshops, which starts at 10 Samara time, which is GMT time +4. The first one will be about neurofeedback. It should be a very interesting one. And the last two ones, but last but not least, will be about transcranial magnetic stimulation and electrical stimulation of the brain. It will be a demonstration of practical cases, and we encourage you to participate. And at the end of the day, at 16:30 Samara time, which is GMT +4, there will be an exciting panel discussion with Jonathan Wolpow, with Sliman Bensmeya, and some other folks that you'd better know tomorrow. And it will be about invasive neural implants, about Neuralink, but not only about Neuralink. And afterwards, there will be a neurobar, and we welcome everyone to join all 5 events that I was announcing. So welcome back tomorrow. We will be looking for you. Thank you, and have a great night.
Thank you. Have a great night, and see you at the rest of the conference.
Thank you. Thank you very much, Brendan, for being our director and host and everything today in California.
Depends on where we are, but yes, and thanks to all the speakers, thanks to the organizer, and again, Ilya, should we go to the Neurobar if we want to have more discussion?
Sure. Tomorrow, the Neurobar is made for discussions. It will be the greatest adventures of Neurobar. A student can talk with the patriarch like John Wolpow in the same room, in the same language, about the same topics. So it's a very rare opportunity, and I would suggest to everyone to come.
Everyone, yeah, you can learn from John Wolpow. Aside from his papers, he is an excellent writer. If you look at his writing in his 2002 paper or other papers, it is outstanding English writing. Anyway, that is the end of our session, and so I will see everybody later, and thank you.
Thank you.
Thank you. And please keep an eye out for the Brain-Computer Interface Society. We will have a virtual conference next year, and that will be on the BCI Society website. These virtual conferences are nice. There is no travel cost. All right, I see you.